Okay, my usual question to people who are on the phone rather than on the laptop or desktop. Are you, is everyone able to see the size of this font? Should I make it a little bigger? Is it okay? If anybody has a difficulty, please let me know. I can actually make it a little bigger. So you can either unmute and tell me, or you can type it in the chat box, which I'm always looking at. This is the size of font normally. Is it okay with everybody?
So far, no one.
No one has. Okay, good. Then I will go back to it.
Okay, so once again, good morning, all of you. On the third day of the so-called second campaign of the PtRC project outreach training program. After last 2 days of evening programs, essentially we had just 2 talks each, and today it is going to be a kind of bonanza or a festival, I must say, because you are going to hear from 8 faculties, very senior faculties, talking to you on very, very important aspects, starting from the general concerns that one has on environment, sometimes a lot of misconceptions, a lot of myths, and what are the frequently asked questions about this project, which, they keep on hearing about this. And we can promise by end of this day today, you will have all of those individually answered, and you must make a good use of, in case the speaker missed some point, you should feel free to kind of ask question. And it doesn't matter. There's nothing like unreasonable question or reasonable question or good or bad. Whatever you feel like, you should be able to ask, and I'm sure the speakers, the faculties will be able to answer them. We are also going to hear a little bit more about the bolts and nuts of the INO experiments, which are going to come up in, of course, in Pottipuram, and also the engineering modules that are, one is already built and the other one is going to be built in Madurai. And later, maybe, our students of more of your age are coming and going to talk about how the research on neutrinos and the research that one needs to build, to build detectors and instrumentation, electronics, and so on and so forth. How is it going to help people on street? How is it going to, what are the kind of spin-offs? What are the kind of byproducts sometimes people call, other than doing neutrino research? And with all this happening around at our own backyard, at our own place, how this project is going to benefit our local communities, our people from Pottipuram, people from Teni, people from Madurai, people from Tamil Nadu, and so on and so forth. And you will also learn something very interesting, a nice lecture on how to improve your speaking skills, communication skills, public interaction skills. How do you impress upon someone with your talking? I mean, talking just doesn't mean only talking without content, but of course, once you have good content, how to communicate well with people. This is very important when you talk to either on behalf of INO or yourself when you express things. This is an important thing. So you are going to hear a nice one talk on that. And at the end, the most important one is at the end, where you freely talk to all the faculties who are on the call today and ask once again all the questions which are left unanswered, and anything, science or some other aspects of the project, right? And also sometimes you can ask about your own career. What do we do? What is the best thing to do? What subject we should take? Which college we should go, etc. So it need not be only about science, but also could be about your career and how to make, because these people don't come on with you every day, right? But today is a great chance, and so many of them are on the screen today. So please make a good use of it. Okay. With that, all the best, great learning. And so over to Professor Indumathi from Institute of Mathematical Sciences, Chennai. She's going to start today's session. Indu, please unmute.
I just started. I said the very nice motivational speech, Satya. Thank you. I got inspired listening to it. I wish you had been giving that afternoon talk. Satya is the, core of INO. He keeps everything going. So I'm very happy to, I wish I could see you all in person, but at least I'm very happy to see you all on a Saturday morning. And I just want to tell you all that this is an English session, but I think the people who are around speak English, Hindi, Telugu, Tamil, Kannada, Marathi. So, or you can chat, use the chat box. Please do ask questions. You know, we are here actually to answer your questions. And of course, if we don't know the answer, we will say that we don't know the answer, and then we will try to find out. So this talk today is divided into two parts. I'm going to give some highlights, and then Professor Murthy will make some additional comments. As you see, the title is Facts and Fiction, because there's a lot of fiction going around, a lot of misconceptions, a lot of misunderstanding about what this project means. So I will first start out with saying that the proposed project should come up at Pottipuram in Theni. You must have seen this mountain before. So this is the hill at the back. Below that, 1,300 meters below that, with the tunnel going through the mountain in a horizontal fashion is what we are proposing to build. And what is it that we want to study? You have already heard that we want to study atmospheric neutrinos. And I need to tell you just that cosmic rays come in, hit carbon dioxide, nitrogen, whatever nuclei are there, produce pions and muons. And these muons are the troublemakers for us because they're deeply penetrating. I will show you some details. But both pions and muons decay to produce neutrinos. And what we are interested in is in the muon type neutrinos and the muon type antineutrinos. And the neutrino gives you mu minus, antineutrino gives you mu plus, and you have a magnetic field, you have magnetized iron plates. So the mu minus and the mu plus bend differently, so that from the bending, you know whether you produce a mu plus or a mu minus, and therefore you know whether you had a initiating neutrino, which was a neutrino or an antineutrino. And from this information, what we want to find out is information about the mass hierarchy. So the whole of INO physics or ICAL physics in one place, whether the third mass eigenstate is more massive or the least massive of all the three mass eigenstates. So for this, what is it that we want to build? We want to build a massive detector, 50,000 tons. As I already said, it needs to be magnetized. It should have 30,000 plates of RPCs and almost 4 million channels of electronics. So you already heard all this. And this is the bending. This is from the prototype. And so you need, okay, there is some information you can, very nice. We can take a look at it later. So with this as the background, what is it that we need to build and how are we going to do it? And how do we inform people about what it is that we want to build? So first of all, you think about the size of the detector. It is huge. You have already heard this is a 5-story building because it is 14 meters high. So 15 meters is roughly a 5-story building, ground plus 4 floors, 5-story building. And so what you want to build is an access tunnel and a huge cavern which can accommodate this large ICAL detector. So why is it that you want to go underground? That is the first question. So I already talked to you about the cosmic ray background, and the cosmic ray background that I'm mostly interested in are the muons that are produced in the process. So these are the muons. And what are muons? We remember our physics. So electrons, everybody knows, they are fundamental particles. They are present in all atoms. And in the core of the atom is the atomic nucleus, which contains protons and neutrons. And protons and neutrons are not fundamental objects. They can be broken up further into small particles called quarks and gluons. You must have heard this also. We'll come back to the muons. So where do the muons fit in? They are not part of matter. So it turns out that in the universe, there are lots and lots of particles which do not make up ordinary matter. So our ordinary matter contains electrons, protons, and neutrons, but they don't contain these muons. They don't contain these tau, and muons and taus are actually heavier versions of electrons. So we all are familiar with electrons. We know their mass is 500,000 electron volt. We've understood what is a million electron volt. So the mass in units of mc squared is 500,000 electron volts, but the muon is actually about 100 million electron volts. So it is much heavier, 200 times the mass of an electron, and the tau is even heavier. In fact, the tau is even heavier than a proton. And these are the 3 types or flavors of these kinds of particles: electron, muon, tau, and with each of these particles comes an associated neutrino. But even though we say that the muon is a heavier version of the electron, it has one property which is very different. And this is that muons are extremely penetrating. Now, all of you know about earthing, right? All of you have used a geyser or an iron box, istri potti, or anything which has a 3-pin plug, right? So you have 3 pins, and the top pin is fatter, and it's called the earth pin, right? And why do you use the earth pin? In case there is a mistake or a problem with the instrument, instead of yourself getting electrocuted, the current that is leaking simply goes through the earth pin and literally goes through earth. That is why it's called the earth pin, right? And why is it safe when it goes through the earth? Because the earth, being a huge body, can absorb any number of these charged particles. Okay, so these cosmic rays which are coming from outside, right, like protons and heavier nuclei, all get absorbed by the earth. And within a few centimeters or meters of the earth's surface, all these very high energy cosmic particles have all been absorbed, but not the muons. So what do we understand about muons? So here is the diagram. I am sorry, at some point I should improve the quality of this. It doesn't matter. If you look at the red dot, that is the proposed INO at Pottipuram in Bodhi West Hills. It is about 1.3 kilometers underground. And the old Kolar Goldfield detector, if you see the cursor here, was about 2 kilometers underground. So we are looking at this x-axis is just telling you how deep you are under the ground. And on this log scale, you are seeing how many muons are present in per square meter per year. Okay, so this number is something like 10 million. So if I just put a detector on the surface of the earth, I will get 10 million muons. How many neutrinos will I get? I will get, tens of thousands of crores. I mean, we don't know, some very, very large number. You have already heard how many neutrinos come from just the sun, and then from stars, and from the atmosphere, and from reactors. And so you have some uncountable number of neutrinos coming on the surface of the earth. However, because these neutrinos are so low, so weakly interacting, you will only get 3 neutrino events per day in the ICAL detector if I place it on the surface. So with all those billions and billions or crores and crores of neutrinos, there may be some electron neutrino events we are not interested in, but of the muon neutrinos that I talked about, we expect to see about 3 events per day. But what will I see actually? I will see the cosmic muons, because what do these neutrinos do? These neutrinos produce muons. Okay. And these muons are what I detect in the detector. Now, if I have muons coming from outside, which are part of the cosmic rays, and they are millions in number, then how do I find these 3 neutrino events in that millions of cosmic muon background? It is going to be very hard. So if I come 1 kilometer underground roughly, what will happen is that those millions of muons will reduce to 3000 muons per hour. Okay. This we can still deal with. Of course, what happens to the neutrinos? The same number. There is no difference in the neutrino sample, whether you're upstairs or downstairs. It is the same number of neutrinos, but the muon background is reduced. So this is the reason we have to go underground. All neutrino detectors around the world are underground. There is one under the water in the Mediterranean Sea, and there is one under the ice in the South Pole. But they are all under the surface. So this is the main reason you need to go underground. And there are a lot of statements that INO will be built underground to store nuclear waste. And in fact, it is exactly the opposite. We want to run away from the surface cosmic background radiation. And that is why we need to go underground. So this is the first point. We need to go underground for this reason. So now that you want to go underground, what is the site that you will choose? So first of all, there are 3 requirements. The first requirement is how deep you want to go. We just said we want to be deep enough so that we can cut down the muon background sufficiently. So this is determined by the physics. The next is that you want to be in a safe place. You want this see, when you build a university, right? You don't want to build a university for 5 years or 10 years. You want to build it for 50 or 100 years, right? So you must have good quality of rock with the safety aspect. And the final requirement is that you must choose a place where it has minimal environmental impact. So what is the place that we have to look for? The geologists have told us that very good quality rock, which is called Chanakite rock, is found below 13° north latitude in India. Where is 13° north latitude? If you draw a line between Chennai and Bangalore, that is roughly 13° north latitude. So you must look for Chanakite quality rock south of that, which means Kerala and Tamil Nadu. But if you look on the Kerala side, there is very heavy rainfall. The mountains are extremely green. There will be a lot of environmental impact if you build on the Kerala side. And if you look at this particular place in Pottipuram, this is on the eastern side of the hills. It has very low rainfall. It has less than 100 centimeters per year. You can see from the picture that we showed you that there is very little greenery here. In fact, we will not even need to cut one tree over here because of the low rainfall. And because there is very low rainfall, there are also very few animals over there. So fewer plants, fewer animals. And the environmental scientists who did the study believe that this is the good region to hold such a project. And this is in contrast to people saying that the INO site selection was not transparent. So next, you must have heard a lot about this earlier. How will we actually build this tunnel? So a lot of people think that you start from the peak of the mountain and then build 1,300 meters vertically, but it is not so. Actually, what you're going to do is you're going to build something which looks like a road or railway tunnel. So the entrance is on this side. This side is Tamil Nadu. This side is Kerala. And the mountains actually go north-south. I will show you a map. Maybe I can show you the map right now. Okay. I'll show you later. I don't want to close the flow of it. Okay. And you will build a horizontal tunnel about 2 kilometers long. At the end of it, you will have your cavern complex. Two questions are there. One is that it will be vertical and therefore will deplete the groundwater. It's like a well. You have a 1 kilometer deep well, and so surrounding groundwater will flow inside and the surrounding areas will have no more groundwater. But this is not true because you're going to build a horizontal tunnel and there will be no impact on the groundwater at all. The next is that some people say if you start digging the mountain, the whole mountain may collapse. How can you be sure of that? So if you look at the scale of this tunnel is about 7.5 meters high. This is 1,300 meters. Okay. So if you look at the scale of it, and even if you look at the lab cavern, it's about 35 meters. It's like saying that I have a house which has a 10-foot high wall. And in that wall, I want to make a little hole. And through that hole, I want to bring a water pipe with a tap so that I can bring water into my house. So nobody will imagine that bringing a water pipe into the house will make the whole wall or the whole house fall down. Okay, because it's a small hole. The wall is big enough to completely support such a small hole. And the proportion of this cavern to the height of this mountain is exactly the same. So then you can easily make this excavation, and the rest of the mountain will not even know that you have actually drilled inside. So there will be complete safety, and that is exactly what you require. Was there a question? Okay, I will proceed. So now that you've chosen the site, how will you do the environmental management? So I don't want to go through all of them. The studies which were done by the Salim Ali Center for Ornithology and Natural History said that, and the reason is of course because there is very low rainfall, wildlife is rarely reported in the portal area. Portal means the entrance to the tunnel. Okay. And what about the rest of the place? We are not going to set foot above ground. Through the tunnel portal or the tunnel entrance, we are going to access the lab. And in this region, there is very little wildlife, and therefore the impact of whatever activities we have on wildlife will be very small. Even so, we have been recommended and we plan to adopt the best practices with active environmental monitoring. Now, there are some more issues. I don't want to go into them, but there are a lot of small things that we have been told to make sure of, and we will make sure that we do all of this. This slide will be available, for example, noise levels, how to do local species planting. We will get in touch with the local forest department and we will take their advice on what kind of trees and we should plant over there. And when the contract labor comes, we should be, we should not let them burn firewood, but we should provide them with LPG. So many recommendations are there, and we are going to implement all of them. Okay. Now, one big issue that has come up recently and has been in the press for some time now is about this tiger corridor. So we have applied for wildlife clearance regarding this tiger corridor, and we are still awaiting this. And there has been some controversy about this. So what is this what is this tiger corridor? So for that, let me actually show you the Google map. Okay. If you can recognize those people who are, I don't know if you can see, this is Bodhi Nayakanur. Okay. This is Andipatti. And if you keep traveling east 100 kilometers, you will reach Madurai, right? It's exactly east-west. And then if I keep zooming in over here, you will find that this little protrusion over here, you can see this is Kerala and this side is Tamil Nadu. Okay. And if I keep zooming in over here, you will find that it says over here, India-based neutrino observatory. This is actually, it's a little bit below over here to the south, but you can see that the mountains are essentially, you can see the dark line over here are the mountains. Okay. And here you find what is called the Matiketanshola National Park. And if you go further south here, you will find, it's a little further south, you'll find the Periyar National Park. And if you go to the east, you will find Meghamalai sanctuary. Okay. So there are 3 sanctuaries. So what this tiger corridor does is that you can see Matiketanshola, just outside the viewpoint is Periyar, and on the east here is Meghamalai. So this tiger corridor is a way on the top of the hills. So that is why I showed you this map. This line are the hilltops. So on the top of the hills, this is a corridor that has been envisaged to allow free movement of both tigers, elephants, large animals, anything, so that they can be sharing of wildlife between the various wildlife sanctuaries. It's a very lovely idea, because if there is an excess population in one area, the animals will simply migrate freely to the other area, and both-way migration will be made possible. So this is the tiger corridor. So where are we with respect to the tiger corridor? We're actually in this place. So I've now zoomed in over here. You can see that this is the same place. Okay, this is the peak of the mountain. Under this peak will be the cavern. Sorry, there is a spelling mistake at cavern. And it's not on the top, but it will be at the bottom of this. And here is the tunnel portal. Okay, and this is the water tank that has been built. Talked about that. And this, if you look at it, this is the direction in which the tunnel goes. It goes around northwest, and there is a small line over here. If I zoom in, you can see, can you see the red line over here? So this is the eastern boundary of the tiger corridor. So all this on the hilltop is a tiger corridor. And when we start over here, we will be outside the tiger corridor. So by the time we reach the tiger corridor, we will be going horizontally. We will be deep underground, and therefore there should not be any disturbance to any animal, tiger or any animal going above. So I showed you this already. And so how are you sure that when you're this deep underground, that there will not be any disturbance? For that, you have to ask the engineers. So what are the engineers saying? This is the map of this location of the site. This side is Kerala, this side is Tamil Nadu, and you can see that actually the seismic zone index says that Kerala is mostly, that is because of the hills. The Ghats are in zone 3, and we will be in zone 2. And this is the lowest zone in India. There is no seismic zone 1. Okay, so we're in the lowest seismic zone. It doesn't matter whatever the seismic zone may be, wherever in the world you are building, the vibrations due to the construction depend on the rock quality at that site. We said that we have extremely good rock quality. So based on the rock parameters, which the engineers have studied, they have given us this little graph. What does the graph say? First of all, suppose I want to build something over here, and I want to do it with controlled blasting. So this blasting is a really bad word, because in Tamil especially it is translated as wedding, which means like a Diwali fireworks, it just goes, atom bomb goes boom. But controlled blasting is a very different thing. What controlled blasting does is the following. Suppose I want to make a tunnel. I always keep forgetting to put the shape of the tunnel. Suppose I have a rounded top of the tunnel. You must have seen a lot of road and railway tunnels, I'm sure. Okay, somewhere, at least in the picture or in the movie or in real life, you must have seen the picture of a tunnel which has a rounded top. So what happens is that these charges, the blasting charges, are actually placed in small amounts in a very regular shape in that same shape as the shape of the cavern you want to build, or the shape of the tunnel you want to build. Okay, and the amount of charge that you want to keep is all computer calculated. And the blasting is also done through computerized mechanism. So the switch ensures that all the blasts go off within milliseconds of each other. And so it is a controlled blasting, completely different from quarrying. In quarrying, all the time you will hear blasts. Here you see what you will have is that maximum 2 times a day from in the outside, and only when you go to the interior, 3 times a day in the interior, you will have the controlled blasting. And each lasts only few seconds. That means suppose at 7 a.m. you have one blast which lasts say 5 seconds. Then at 4 p.m. you will have another blast that lasts 5 seconds. And that's all the blasting disturbance that you will have in the day. Okay, that's all, only a few seconds. And what about the vibrations due to that blast? If you're here, if the blast happened at zero point 0 meters, I don't know if you can see this axis, but this is 500 meters, half a kilometer away. This is 1 kilometer away. If you're 500 meters away, the vibration is less than 2 millimeters. So the ground will vibrate maximum amplitude of 2 millimeters. And if you're 1 kilometer away, it will be less than 1 millimeter. 1 millimeter is so small. And the closest villages are more than 2 kilometers away. So the people will not even feel the vibrations. And so for wildlife, which is about half a kilometer above, in fact, under the cavern, they are 1.3. That is exactly the end of this slide. Above, they will just feel a vibration of half a millimeter. It will be very, very small. So they will not have feel any disturbance at all. And even the small disturbance lasts only a few seconds. So this is not like conventional blasting in quarries. It is completely different. And so the fiction that INO construction will damage the nearby fields, villages are all completely wrong. So next we come to underground tunnels, because the next question was, okay, fine, maybe nothing will happen in the immediate neighborhood, but a lot of people have said that the Idukki Dam will collapse when you start building INO. Okay, so for that there are two examples, and I will actually only go over one of them because they are very similar and it's the same story everywhere. So all I want to highlight is that tunneling is a routine activity. Okay, if anyone is in a big city like Chennai, Bangalore, Mumbai, Calcutta, they have all seen the metro. Metro actually dug literally under houses and buildings with no damage. So there is no problem at all. And even in Tamil Nadu, the Tamil Nadu Electricity Board has built more than 100 kilometers of tunnels, especially in the Western Ghats. And why have they built this? They have built this because they want hydroelectric power. What is hydroelectric power? You have a dam on the top of a hill which contains water, because that's where the catchment area is. Then somewhere at the bottom, because you need a height difference. What is a hydroelectric project? Water falls on the turbine and turns it, and that generates electricity, right? So you need a level difference. So from the top of the mountain, you have to bring the water to the bottom of the mountain, and it will fall on a turbine inside a cavern. So you have to, many of these places, because they're very green and forested, the tunnels are themselves underground, the caverns are also themselves underground. And so many tunnels and caverns have been built by the TNEB. This is one example. If anyone is from the Nilgiris, they can go and see actually Singara and Nilgiris. But I will take the other example since everyone is talking about the Idukki Dam. It's a very interesting construction. So first of all, Idukki is a huge dam. I wanted to keep the Google map open, but I forgot. It's okay. You can see that it contains a reservoir, that is the water dam achieves. It achieves a reservoir of water, which has a capacity of 2000 million cubic meters. 2 billion tons of water, just unimaginably a large reservoir. Okay, so you construct the dam to hold the water, and that Idukki Dam was commissioned in 1973. Now, after commissioning this dam, the hydroelectric power project was planned afterwards. And how do you build a hydroelectric power project? You need to bring that water to a lower height and turn a turbine, right? So it was done using a 2-kilometer tunnel. Okay, and that 2-kilometer tunnel led to two 1-kilometer shafts underground, each taking water to an underground powerhouse, which was another 700 meters below in the Pottipuram Valley. And what happens when the water turns the turbine? The water has to go out somewhere, right? And that going out is called a tail race tunnel. That is a 1-kilometer thing. So how many kilometers of construction? And where does it start with? It starts under the dam, right? It has to start under the dam because the water from the reservoir has to be channeled into this tunnel so that it will fall on the turbine. And that was completed 3 years later in 1976. So the dam was finished in 73. The tunnel construction, hydroelectric power project was commissioned, completed in 76. And so there was no damage to any of these dam structures, even when you constructed these tunnels and powerhouse caverns completely under the dam. Okay, so there is this engineering is very well known. There is no difficulty in it. And the other example is all the, Konkan railway tunnels. So there is no problem. The fiction that dams can be impacted is false. And the other thing they say is that once you start doing controlled blasting, you will cause earthquakes, and the earthquakes can impact the dams. But you see that The so-called earthquake that you generate is only 1 millimeter or 2 millimeters, and that too very close to the site of the blast. And in fact, recently the government has actually inaugurated the Shenkote Punalur new railway line, upgraded railway line, which has a lot of tunnels along its path. And this was constructed and completed recently, just a few months ago. It was commissioned, and there was no damage to any of the dams during this construction. So we do not see any fear for such constructions. These are very routine. Now, there is a little peculiarity about this muck. In Tamil, it is called kalavu. Muck storage yard is required, and this muck is a technical word. It comes from blasting. So when you blast the rock, you get muck out. However, what you must understand is that this is very, very strong rock called charnocite rock. So when you blast such rock, you will not get muck. What you think of as muck in English word or even kalavu, the Tamil word, is something that is waste. Okay, but this is not waste. You will get 95% will be chunks of rock, and only 5% will be powder. Actually, both the powder and the chunks of rock will be useful as construction material because it is simply a granite substitute. It is exactly like granite, except it is stronger. And even though you get a huge amount of this rock chunks, which is about more than 2.25 lakh cubic meters, this is something that is actually very useful commodity. And since most of it, as maybe I should have shown you over here in this map, I forgot to show you that in this map, this region is completely Porumbok or revenue land. It has been given free of cost from the Tamil Nadu government to INO to construct. There'll be some surface facilities like some offices, some student housing, some places will be there. And up till this portion is also all open revenue land. And what is called reserve forest only starts afterwards. So we are going to be deep under the forest land before we actually enter the forest land. Okay, so we are not going to do any construction in the forest land at all. We will be underneath the forest land. And the reason I'm saying this is that because we are under the forest land, the majority or the large part of the project is under the forest land. The forest department has said that this muck belongs to them because it's coming from under the forest. It is forest produce, and so they own it, and they will actually take it away from us, and they will dispose of it as they please. Okay. Only thing is that if they do not do it in regular intervals, then it will become a difficulty, and it can cause pollution. So for that reason, we are going to have a storage yard where temporarily these rocks or muck or chunks can be deposited until the forest department takes it away. And even then, you can see that they will be retaining walls, they will green it, they will be wetting of this because the little bit of dust should not disperse and cover the surrounding area or the fields or the villages and cause them pollution, air pollution problems. So they will actually wet the muck before putting it over here. And so this is a way to neatly dispose them. And so the INO muck will not cover the fields and will not destroy the crops. So that is fiction. Okay. So there is various kinds of disaster impact assessment, and I only want to highlight one of them. There is no impact at all. Radiation, a lot of people are talking about storing radioactive waste and having radiation damage because of neutrinos, but neutrinos are not radioactive. No radioactive materials will either be used or produced. You have seen now all the working parts. You will see some more of it in the talk that is coming next. And tomorrow you will actually go and see that prototype yourself, and you will see what kind of materials go into producing it. No radioactivity at all will be there. And so it is completely untrue. It is a fiction that dams can be impacted by radioactive contamination of water. Neither the surrounding groundwater nor the dams will be impacted because there is no radioactivity. Okay. So this is something that is a technical thing. A lot of people have said that some high energy neutrino beam from Fermilab will be beamed towards INO, and they will be intense, and it will be like a defenseless weapon. Now, all of you have learned physics. It's a neutral particle. It has no charge. I cannot collimate it. I cannot make a beam of it. Even though photons are chargeless, you can collimate them because lasers they have a special property, which neutrinos are fermions, they do not have. So there is no way I can collimate this beam. And even if I manage to collimate the beam, you can collimate to a certain extent. We know that neutrinos are so weakly interacting Beams of neutrinos are coming from the sun, from the stars, from our own atmosphere, and we are standing in the beams throughout our lives. And as I said, the probability that during our entire lifetime we will even interact with one neutrino is not even one. Okay, we will not interact with even one neutrino in our lives because we are so weakly interacting, which is why I need 50,000 tons, which means 50 million kilos of detector to get 3 neutrino events a day. And I don't weigh, I mean, whatever I weigh, I don't weigh 50 million kilos. Okay. So the probability of that happening, so if you multiply day by 365, you get a year. Even if I live for 100 years, that is only a factor of 36,000. So I will never get to that kind of number. You can see that there will be no probability of any neutrino beam, wherever it comes from, actually harming anybody at all. It's simply, neutrinos simply cannot harm anybody. This is total fiction. So all this we have said many times. Uh, uh, we have been having outreach programs for a long time. This was taken in 2009. This was a very large meeting with about 1,200 local villagers, which was actually organized by the district collector, Mr. Murthy. At that time, local MLA was there, the Pottipuram Panchayat president was there. About, you can see in the front are the 40 press members were there. Apart from about 2,200 local villagers, we told them about the project, and they actually gave us the consent to build the project there. So it is a really sad thing that after 2010, when we had the consent of the villagers, that it is now 2021, and we still, they have so much confusion in their minds. They have been told so many things which are completely misleading about INO. There's a lot of, whether it is genuine or otherwise, there has been a lot of negative statements about INO. And this meeting, this workshop is actually an attempt to correct this narrative and to tell you that this is a project, whatever else you may look at, here is an opportunity for students. Instead of going to Fermilab, instead of going to CERN, yes, there are some Indian students who go to CERN, who go to Fermilab, who go to Bell and do other experiments abroad, but that can only be 1 or 2 or 3 or 10. Okay, if you have a detector located in India, and you can just say, this Saturday I want to go there and spend a few hours over there. And what a difference it will make to the way we can understand physics, to the way we can train students, to the way in which we can do technology transfer with local companies, and that technology transfer can be used to improve technology in India for whatever it is, local household goods, anything that is required. This is something that I think is really the main goal of INO, to have something located in India, something where we can do good quality physics, where we can reach out to the local industries, to the local people, and make a change for the better. So this is what I think I will stop here. I will leave Murthy to make a few more remarks. If there are any particular questions about that have been propagated, or some myths that have been propagated which I have not addressed, I will be happy to answer them, or Murthy will answer them. So Murthy, shall I stop sharing, or do you want to just make a few remarks? Murthy? What is the current stage of the project? Okay, should I take questions? Okay, can someone just check on the participants list and see if Murthy is there?
He's there, but he's muted.
Okay, you're muted, Murthy.
Okay, sorry.
Sorry. Okay, sorry. Okay, so 1 second. So Akilan, I will answer in a moment, but I think Murthy wanted to add a few remarks, then we will take the questions.
Right. But Amol, you have to leave early. Do you want to make any remarks now? Amol?
No, I don't want to make any remarks now. You can go ahead.
Okay, thank you. Actually, Professor Indumathi has covered most of the points about this misconception and myths about the INO project, and has clarified all the things to you. I will make only a couple of remarks. One is that there is a question that is asked of us wherever we go. Why is this project under Department of Atomic Energy? Because there is this idea, there is this concept that Department of Atomic Energy is devoted to constructing nuclear reactors, generating nuclear power, and other applications. That is a general belief in the people. What they don't know is that historically, Department of Atomic Energy has been involved in the development of basic sciences in the country, especially physics and pure mathematics. Professor Homi Bhabha, you may have heard about his name. He was the one who was instrumental in starting this Department of Atomic Energy. And he himself was a theoretical physicist. And in fact, he was the one, you have heard about M.V.N so much, he was the one who recognized for the first time the signature of muons in cosmic rays. He called it heavy electron. In fact, the name muon came much later. He should be credited with the discovery of this particle called muon, about which you have heard so much in the last 2 days. So he, while starting the Department of Atomic Energy, he also realized the importance of mathematics, theoretical physics, and other areas of physics in developing atomic energy establishments in this country. So, by a parliamentary resolution in 1964, the development of physics and pure mathematics is actually assigned to the Department of Atomic Energy along with the Department of Science and Technology. So this project is not just a Department of Atomic Energy project, it's a project supported by both Department of Atomic Energy in its role as the developer of basic sciences and also Department of Science and Technology. So this is a myth that because it's Department of Atomic Energy, there is something secret about it. There's nothing secret about it. They are just doing, these departments are doing just their job in supporting this project. Okay. Now, secondly, wherever we go, sometimes we are asked this question, why didn't you do your environmental impact assessment by a recognized agency? Why didn't you do a official public meeting through the Pollution Control Board, etc., etc.? So this is again a misunderstanding of the whole process of environmental clearance. In fact, when we first approached the department, the Ministry of Environment and Forest, they were not even aware of what category this project comes, because there was nothing listed among the various categories which require environmental clearance. So, for example, coal mining or any other mining activity will require environmental clearance. And you want to build a very large project of a huge area, you require environmental clearance. But there was nothing which said that a basic project, the basic sciences project requires an environmental clearance. So in the beginning, when we went to Ministry of Environment and Forest, they said, why do you require environmental clearance? Then we explained the project to them. They said it involves tunneling and construction of the cavern. So please check if we need any such clearance. Then after about 6 months of discussions, they came up with a category, which is the category 8A, which relates to large projects where the area of construction exceeds 20,000 square meters. Okay, if you put tunnel area and the cavern area in our case, it exceeds the 20,000 square meters by a few hundred square meters. So we said, okay, you can do the clearance under this, we will apply for it, and we were then asked to apply for it in 2007. And that was, at that time, we were in a different site, which we had to change for various other reasons. In any case, that category was given, we applied. Under that category, you need to apply for the environmental clearance, but you do not formally require an environmental impact assessment. You also formally do not require a public hearing. But in any case, what we did was that, okay, even though it is not required, let's do it. So we went to Salim Ali Center, a well-known institute of excellence under the Ministry of Environment and Forest, and we asked them to do the impact assessment, which they did. And they did it for the site in Bodhi West Hills, in near Pottipuram in Theni district. And we also had, as Indumathi mentioned, a public meeting. We cannot call it as public hearing because there is no formal requirement for a hearing. But nevertheless, it was indeed formal in the sense that it was organized by the collector. The Panchayat president was present, as also the various officials of the government, like the superintendent of police and the district forest officer. All of them were present at this public meeting attended by 1,200 people. So we went beyond the call of duty here, that even though we were under Section 80A and not required to do all these things, we did it. We commissioned the environmental impact assessment by Salim Ali Center, and then we also had a public meeting, like in any other categories, though not required. So after this, the environmental clearance was given in 2011 for this project. Okay, so there is some confusion, and many times you read in papers or in blogs or probably in social media, about which I don't know much, that we haven't done environmental impact assessment by a recognized agency, and all these questions are asked, and sometimes these are genuine questions, and the answers are very clear that we were not required to do any of these things. Nevertheless, whatever we have done is there in the open, and you can see these reports on our website, and you can check for yourself what kind of environmental or ecological impact that this project will have. So this is one thing, and these questions come up, and there were some legal challenges, but then it was clarified by this thing, National Green Tribunal in South. When the question came up, they said, okay, there are some questions, but your environmental clearance is kept in abeyance. You may have to do something more. So go to the center and do it. So we did the environmental clearance again to answer that specific question that had to do with wildlife and the presence of Mathiketta National Park. So we went to the ministry again and we did it. We did the environmental clearance. And then that again was questioned in the National Green Tribunal in Delhi, in the main National Green Tribunal, and the National Green Tribunal said that everything is in order. Now, that again has been questioned, and now this is in Supreme Court. It is going to be taken up sometime in the next few months. We hope we will be able to answer all the questions and get through this phase also. So this is about the legal questions. I have been very brief, but you can find all the reports that I mentioned on our INO website. Now, there is also one more question that Indu did mention, which is about how we deplete the groundwater resources. Okay, this is an important question for local people, and it's a very it will be asked, and it has to be asked, and we have to answer it. So the answer to that question is that if you look at the hydrogeological map of Theni district, there are no aquifers in the mountainous areas, especially in the specific area that our project is located, which is West Bodhi Hills. There are no aquifers according to the hydrogeological map prepared by the Central Water Board. This map is available on, you can Google it and you will get the map, and you will see that there are some green areas and there are some brown areas. And the green areas where all the water resources and aquifers are situated. The brown areas are the ones where there are no aquifers, and the INO project is in the brown area. So there are no aquifers here. So when you are tunneling, it is unlikely that you are going to meet any big water pocket or an aquifer which will be depleted because of the construction of this project. The fact is there are no aquifers, there will be no depletion of any groundwater from that particular site where we are going to do the tunneling. And as Indu mentioned, our tunneling is horizontal, and therefore there is no question of water coming from other places and collecting it. There is no way. And if that is the case, then we can't even have the project in that place. It is also a question of our own safety, safety of our students, our faculty, and our scientists and engineers. So therefore, there is no problem with that. So there is no question of groundwater depletion. So these are the 3 points I wanted to mention. And I think if there are any questions.
Yeah, so there's Akhilan asked, what is the current state of the project? You want to answer? Shall I answer? I mean, basically nothing has been done yet. We are still waiting for clearances. The only thing that we have done is the prototype, which is there in Madurai, and that I guess you'll see soon. So you'll know that is the state of the process. A lot of R&D work has gone on. Prototype has been built, but at the site, nothing has happened. Now, there's another question for Professor Indumathi. It is apparent that the project and its proceedings have been very transparent since the beginning. So why do you think there's a large amount of prevailing misinformation, and what do you think was the starting point for these controversies? Actually, the starting point was very clear, and maybe I didn't actually highlight it. It is to do with this muck, which is translated as kalavu, and the nuclear kalavu, the nuclear waste, right? So waste became nuclear waste. And then there was an article in the Current Science, which is a very, very good, one of the reputable or more reputable Indian journals, that INO will cause radioactive damage, will cause this damage, that damage. And that article actually caused a lot of damage. And the only reason was that they tied up this thing, statement of waste to the Department of Atomic Energy, and they said that since Department of Atomic Energy is trying to build Kudankulam, they will have a lot of nuclear waste generated, and therefore this will be the cavern in which to store this nuclear waste. And kind of a conspiracy theory was started at that point. And I think that really, to be very frank, I really don't understand why so much controversy has surrounded this project. But there's also a history of such protests in Tamil Nadu. And unfortunately, INO got dragged into the list of projects that were being opposed in Tamil Nadu, and it became very hard to actually straighten out this misinformation campaign. And there is another question about, is there any chemical contamination of groundwater resources due to chemicals used in tunneling? So the statement is the following, okay? We have said that we will not use any groundwater because there is very little water in that area. And we have promised the locals we will not touch the groundwater. So we have to bring water from outside. So what we need is, and if you look at the chat box, we will need this much, 340 KLD of water per day, kiloliter per day of water, okay? And this is the maximum requirement if we build twice the size of INO. See, normally when you're budgeting for something, you can't actually keep adjusting every day, because when you go to the government and say, I want this much requirement of water, you don't give the minimum amount, but you give the maximum possible so that you're always comfortable. So roughly what we will need is, if we build the entire double detector, then we will need 320 per day of water, plus 20 for the use in the residential complexes. And actually, therefore, what we need is 160 KLD for the 50 kiloton ICAN. Now, this much water sounds like a lot, because kiloliters is actually sounding like a lot. So it's like 320,000 liters per day of water. But this is roughly the amount of water that, for example, Madurai Kamaraj University uses. In fact, if you ask what is the use of water used by IIT Madras, which is actually sitting in Chennai, it is 2.8 million liters of water per day. Okay, so that is 2,800 KLD. So you can see that it is much larger, 10 times larger than what INO will use. So this water amount sounds large, but it is not large, and it is being brought from outside. Okay, so the water is coming in pipes, and the water comes from far away. In fact, the only thing, someone asked about the status of the project, the only thing apart from the compound wall that has been constructed in Theni is that the TWAD board, the Tamil Nadu Water and Drainage Board, has actually brought the water, built the pipes and built a sump, which you can see on Google Maps, for this water. So now you come to the question of what about chemical contamination? So first of all, the groundwater is very deep below. So how will groundwater get contaminated? Suppose you have an aquifer, which I said is a water-bearing rock. So while I'm drilling, when I'm drilling, I'm placing charges, which is whatever this dynamite or gelatin or whatever they use, the modern versions of all those things. And therefore, when you blast it, there will be that dust also, that chemical contamination will be there in the air. Now, if there is a water pocket in that rock, then that chemical will mix with that water, with that aquifer water, and that water will flow out because you've actually made a hole in the rock, right? And it will mix with the groundwater, and that is a potential contamination of groundwater. But this is the reason you have Chanakite rock. This is hard rock. There are expected to be no aquifers, no pockets inside this rock, no water-bearing content at all, and therefore nothing to transmit that chemical contamination from inside the mountain to the outside borewells. Okay, and therefore there will be no chemical contamination of the groundwater during the tunneling project. Okay, so this is one. Then is there any other question?
No, Indu, there is also this that because the tunnel is in reverse gradient.
No, but while constructing the tunnel, it is not yet in reverse gradient. So in the beginning, it says if you find the problem, so they will not be. That is the whole point.
But generally, as you go inside, the chemical contamination due to the blasting, if any, has to be very localized because of the reverse gradient, and we can safely take it out.
So basically, if there is water flow, the water will actually bring it out, right? But there will be, there is expected to be no water flow because you have chosen the rock which doesn't. See, the Himalayas, you cannot guarantee this. Actually, we have been to a lot of mountain tunnels in our search for INO. And if you look at the Himalayan rock, wherever they build tunnel, the water is simply flowing down like waterfalls on both sides of the tunnels, you see. A huge amount of water. Then you cannot stop the chemical contamination. That is the problem there. No, I mean, let us not go there at all. We will stick to INO and we will say that we will try to build it in a safe manner, and we are not going to have these kinds of problems. Okay. Are there any other questions? Yeah, so I mean, it's sad. I mean, it's sad that after 10, 11 years, we are still struggling to get clearances, and we are hoping that by talking to people like you, young students who also know the physics and can appreciate it, that really this is a basic sciences project. And that there is nothing hidden, there is nothing secret. Every document that Murthy talked about, our environmental ecological impact assessment report, the detailed project report, our physics report, everything is there on that INO website. So you can please take a look at it, okay? Everything has been there since the beginning of time. Since when we actually started applying for clearances, it's been there. So. In fact, if there are no more questions, we should stop because we are going over time.
Yeah, just one last sentence.
Tell.
Okay, so it's not a question. It's a request to all the students. In fact, what we want you to do as students of science is to take this message that you understand this project and this does not pose any danger to anybody anywhere. And especially if you are from TNE, please spread the word. Thank you. You will be our ambassadors in that promoting this project. I mean, please understand the project first, and if you are convinced by all our lectures and statements, please spread the word.
So there's another question. How will you arrange for there to be no dust on roads? So there is only one road that is actually being built for INO. Okay, and the reason to build that road is to go away from the villages. See, when we explored the site, we went through the village to go to that site. Okay, but this road has been half built. In fact, the most popular picture you will see of INO when the article is opposed to INO is this particular picture taken from a suitably low level. So it looks like huge amount of construction is going on. There is no construction going on in the INO site. In fact, you can even go and see over there. What is being built is the Tamil Nadu Highways Department had arranged, we had paid them to actually build the access road so that it will bypass the villages and will not disturb them. So this is one road only. Okay. Now, how will there be dust on the roads? If I am drilling something, if I am doing controlled blasting and getting the muck out, the powder content of that rock can spread in the air and cause dust. Okay. And this is why the wetting, it's a very, very simple and well-known technique. Before you bring the muck out, because the muck is actually inside, right? You have to bring it out in trucks. So when you load it in the lorry inside the tunnel, you wet the whole thing so that it settles down, cover it with a tarpaulin, bring it out. then there will be no dust on the road. Similarly, when you want to take it out from the muck storage yard to wherever the government wants to take it out, same thing has to be done. You wet it. So once anything is wet, once sand, or not sand, but this is rock dust, right? Once dust is wetted, it simply settles down. And so there will be no dust on the roads. So the thing is this, one thing we have to very, very clearly highlight, okay? This is a construction project. It's a large construction project. 2 kilometers of tunnels is not normally built by a university. We are like a university. We're just 20 universities put together, right? Normally, universities don't construct roads and tunnels, but engineers do. For them, it is a very small project. 2 kilometers is something that, usually you build more like, 10 kilometers, or railways will build 100 or 1,000 kilometers. So they know how to do this very well. But there is actually, during construction, there is disturbance. All this that we have listed, we have to be sure that we implement all these things. We are very keen on doing this right. See, we are scientists, and we believe that we also understand that we should be concerned about the environment. We should be concerned about the local people, which means that it is in our interest to make sure that all these are implemented. When you give the contract to a contractor, we must make sure that he implements all these things. It has to be done correctly. But we want to be completely open about it. Here is the problem. Here is our solution. And we actually 100% believe that we are going to implement it like this. Okay. This is the statement that we want to make.
Okay. Indu?
Yes, sir. We are done.
Done. So we need to take a short break, right?
Yeah.
But
so thank you very much, everyone. Yeah. And if there are more questions, there will be a session in the afternoon where you can actually have a free interaction session.
Right. So we'll just take, like we do always, just a quick snapshot of all your. So can you please put on your cameras? 1 minute for me. The faster we do, the longer the break we get.
Yeah. If you are wearing a mask for safety reasons, please do not take it off. It is perfectly all right. Okay.
Okay. So if nobody else on the screen, another 10 seconds. Jaswini Ashokan, we can't see your face.
There's an error in my camera, sir. I'm so sorry.
Oh, okay. Because it's excellent. Okay, good. More of them. Okay, I think let us not spend more time. Okay, I clicked one, but don't go away. I'm going to click another one.
Yeah. Very nice set of questions, everybody, very thoughtful.
Okay, thank you very much.
Yeah.
So what we'll do is now, it is 10:40, right? Maybe
10:50 we will start.
10:50 we will start. So 10 minutes, but please come back sharply at 10:50.
Thank you.
Satya, are you there?
Yes, sir, I'm there, sir.
So shall I try to share my
Yeah,
screen?
yeah, yes, sir. Yes, sir.
Yeah, is it visible?
Yes, it is visible. You can also move your slides.
Yeah. Yeah, okay, that has gone down. Yeah, great. Yeah.
Sir, they are fine. They are moving.
Changing? Okay.
Yes, sir. Yes, sir.
Okay.
So you can keep the first page.
Yeah.
Yeah, perfect.
I think when one goes to full screen, then there is a problem. I don't know.
You can try if you want.
I can try.
Yes.
Is working.
Yeah, they are moving fine.
Okay. Okay, good. Then I'll keep it like that.
Okay. Sir, it is 10:50. You would like to start?
Yes. Let me see how. Okay, 33 people have come back. I mean, they're there.
Yeah, yes, sir. I think maybe a few will join, but maybe we can start, sir.
Sure. We can start. Okay. So, good morning, students and faculty who are there attending this talk. I'll be talking about science at the ICHEP as well as the Pottipuram Research Center, which is the place where the INO ICAL detector will come up. I've given my email address here, so in case you have any questions, don't ask them now. These questions now, you're most welcome to write to me. Okay, so this is the plan of my talk. I will say what and why of the iron calorimeter detector at Pottipuram at the site. Then I'll talk a little bit about the mini ICAL detector at Madurai Transit Campus. Of course, some of you will be there and will actually see it in operation. And then I'll say a few things about the upcoming engineering prototype ICAL detector. Okay, so what is the science that the iron calorimetric detector can do? First of all, let me say that this is the only large magnetized neutrino detector which will study atmospheric neutrinos and antineutrinos of the muon type separately over a large range of energy, about 1 to 20 GeV or so, and a large range of lengths, namely about 10 kilometers to about 13,000 kilometers. This is something that no detector can do. I mean, all of these things that I have said, study mu and anti-mu separately over this large energy range and large distance. One of the main goals of this experiment is to understand or to determine the mass ordering of neutrinos. So we know that there are 3 mass eigenstates, and we will try to find out from this experiment whether one of those mass eigenstates is above or below the 2 close-lying mass eigenstates. Of course, there are competitors. It's not that we have a freewheeling kind of time. There is the Juno detector, which is planned to come up and which will study reactor antineutrinos. It's a 20,000-ton liquid scintillator detector, placed about 50 kilometers away in a hill, which is about, I think, 600 meters or so high. And they will run from about 2022 to 2028. Perhaps this is slipped by half a year or something, but not by much. Then there is Dune, which will start taking data in 2029, 2030, using the beam of neutrinos from Fermilab. So the Dune detector is again an underground site where they have about 60, 70 kilotons of liquid argon detectors. They're so-called time projection chambers, and they will look at accelerator-produced neutrinos and then antineutrinos in a separate run. So they have that advantage that you can switch the beams. The iron calorimeter will look at both simultaneously. The ICAL 3 sigma result for this hierarchy problem will take about 10 years, but of course there is already data from T2K and NOVA, and using that we could reduce this by about 6 years. Even if one or both get the result, a different experiment is of great value when you have an important result at stake. Okay, we will also be able to discriminate between vacuum and matter modified neutrino oscillations. Possibly only Dune and ICAL can do that because you have large matter lengths. Dune, as I said, is about a 1300 kilometer path length. ICAL has the possibility of going up to 13,000 kilometers. Of course, depending on the zenith angle of the neutrino that you're observing. We would also observe the so-called Mikhail-Smirnov-Wolfenstein resonance, and this can perhaps be only observed by ICAL because the neutrinos traverse the core of the Earth. And this is, of course, a big advantage, and so we are unique in that respect. There is also synergy with accelerator experiments for the antiparticle symmetry violation that has been actually observed probably for the first time. Of course, it is not at a very high confidence level by the T2K collaboration. And this is a very exciting result if shown to be true. And an experiment like ICAL will help, in this, it has a synergy with these accelerated experiments, because the accelerated experiments give you a signal which is dependent on both CP, possible CP violation and on the mass ordering. Whereas the ICAL is not sensitive, at least in the higher energy ranges that we are going to look at for CP. It's not sensitive to CP. So this will be synergistic with the accelerated experiments, which have a combination of both of these contributing. We will also look at the feasibility of doing tomography of the Earth using matter effects. And then, of course, there is beyond standard model physics, non-standard interactions, sterile neutrinos, a possible search for magnetic monopoles, a look at the anomalous events that were seen in the polar cold-field experiments. Since we have a detector which is 10 times larger, we should be able to see those events in a much shorter time. The polar goldfield anomalous events were seen over a period of about 20-25 years, about a handful of events, about 8-10 events. So we could do that in a much shorter time and either support the KGF anomalous events, find supporting evidence for that, or say that no, these are some artifact. And some of this, or most of it, you will find in the white paper on the physics with the ICAL detector, the iron calorimetric detector, in an issue of Pramana. Of course, I think this is also there on our INO website. Okay, so the iron calorimetric detector, again, this is repeating what Indumathi already said, that, and also what I said, the atmospheric neutrinos are basically for free. I mean, you don't, they're produced in nature, and they, as I said already, that they give you these large chunks of energy and propagation lengths for free. The measurements hitherto did not distinguish between neutrinos and antineutrinos, except in the smaller accelerator-based experiments. Whereas here, because we intend to have a magnet, and if once you know the direction of the muon that is produced in the neutrino interactions with the reactions that are shown here, the nu mu plus a neutron gives you a mu minus plus p, and then this mu minus propagates in the detector. So you know the directionality of that muon through the time sequence of detections that you have, and then you also know the curvature, because you know what is the magnetic field in your detector, so you can identify that the muon came, so you know the direction of the muon, and you can tell whether it was mu minus or a mu plus from the curvature of the track. Okay, so why do you want to make a huge magnet? As I already said, it provides you a magnetic field, and therefore you can track these charged particles. You can identify whether you had a muon with a +1 charge or a -1 charge. But also, iron provides you with the target. So the neutrinos are neutral particles. They cannot directly cause ionization. So they have to interact with matter before they produce charged particles. And we are especially interested in the muon, but also in the other pions and kaons that might be produced in this reaction at higher energies. And so the ICAL detector, which has about 50 kilotons of iron, provides the matter as well as provides the magnetic field. And this helps in the identification of mu mu and mu mu bar events. Why underground? This has again been stated many times, but I just repeat it here, that you need at least 1 kilometer of depth so as to reduce the cosmic muon background by 1 million times. And there are two choices. You can have mines or tunnels. The logistics is much, much better at a tunnel, because you can take trucks carrying huge, heavy equipment into the place where you are ultimately going to work. Okay. This has already been stated, so I won't repeat it here. Muon flux is a function of depth. We had the deepest place in the world, the polar goldfield mine, but that is now closed. And so we are somewhere here, which is close to the place where Gran Sasso is, slightly worse off than Gran Sasso, but somewhat better than the Kamioka lab in Japan. Okay, now these are diagrams which show you the access tunnel. So you come in from here, you have a roughly 2 kilometer long tunnel. So this is not to scale. The 2 kilometer would take it somewhere to the right. And you have several caverns. So you have one cavern which is about maybe a kilometer or so from the beginning, from the entry, and that is to actually maybe store materials underground so that they don't see the cosmic rays and don't become very tiny, tinily radioactive. Okay, even that matters when for very low background experiments. So this is to store radio pure materials. Okay, this is one thought that we had, and then of course you have several caverns. The biggest cavern, of course, is the one where we will put the ICAL detector. That's going to be about 130 meter long and about 26 to 30 meter wide, and similarly 26, 30 meter in height. But there are smaller caverns which will house smaller experiments, such as the dark matter experiment, the neutrino-less double beta decay experiment. So these smaller caverns where these experiments will be housed. And then, of course, there are other tunnels to move around and so on for safety purposes as well. So this the cross section of the tunnel will have a kind of D shape. It will be about 7.5 meter wide, and it will go in a down slope so that we will get an additional rock overburden cover. So this is what we are thinking of is a 1 in 13.5 kind of down slope. So by the time you end up 2 kilometers away in the cavern region, you will have gained 2000 by 13.5. So that's about 150, 160 meters additional depth. The cavern itself has about 1270 meter vertical rock cover, but in other directions, it is not as much, but it still meets the requirement that it is 1 kilometer rock cover on all sides, okay, in 2 pi. It will take about 3 years to build with the techniques that Indumathi indicated. And this is the kind of cross-sectional view of the cavern where the ICAL will be housed. This is the end-on view of the ICAL detector. So these are the coils to generate the magnetic field. And you can see the human being somewhere here, so tiny as compared to the size of this detector. Okay. So this is another view of detector. This is very schematic, but it doesn't show the coils. The coils are shown here. So these are the coils that will generate the magnetic field. This is a very different kind of magnet from the magnet that you are probably familiar with. You're probably familiar with bar magnets or with dipole magnets, where you have a gap, and so you produce a magnetic field in the gap region. This is not at all like that. The coils produce a magnetic field which is mostly in the iron plate itself. Okay, so the field starts out here, comes back on itself, okay? And this field doesn't interact with the field, or at least minimally interacts with the field in the next plate after a gap of about 40 mm, right? So this is a simulation result, a 3D finite element simulation that was done using commercial programs. And you can see that these are the coils. So the coils carry a current in the same direction or in the same sense, clockwise or anti-clockwise. I think it is clockwise in this case. And it generates an axial field here. And the field lines go on the sides where you again have iron and then come back onto itself. Of course, in this region, the field is low. So is it low in the edges of the detector. But overall, the field is about 1 Tesla for 90% or so of the volume of the iron. Okay, this is something that you have also seen in Govindo's talk yesterday. So these are the schematic of the RPCs. So we have X and Y pickup strips. So when a charged particle such as the muon passes through them, you get a signal which tells you the X and Y coordinates with a certain error because there is a finite thickness to this detector. Okay, so it gives you the X and Y positions, and then of course you know where this detector is placed, so you know the Z. So for each of these, you will get a X, Y position and Z, so you can track this charged particle. Okay, so these are some of the features of the 17 kiloton ICAL magnet. is, as I already said, is different from normal gap magnets with field between the pole pieces. Here, the field is essentially within the iron plate. So if you walk by this magnet, as you will see in mini ICAL, unless you go very close or even touch the iron plates, you will not feel the field. So if you have about 1.5 Tesla internally in the iron, if you are about 10-20 centimeters away, this will drop off to a few tens of Gauss. So that's about 1,000 times smaller than the field which is there internally. Each module is about 17 kiloton. And when put together, this magnet will be the largest iron-based electromagnet in the world. There are, of course, superconducting solenoidal magnets in Atlas, for instance. That is one of the biggest magnets, but that doesn't have, it only has iron for the return of the field. So this will be the largest iron-based electromagnet in the world. It has 150 layers, as you all probably have heard of, with dimensions about 16 meter by 16 meter, and it is tiled with the iron plates, soft iron plates manufactured in steel companies in the country. We don't know what company, but certainly there are many companies that can do this. Very low carbon steel, less than about 0.05% as compared to iron. 4 meter by 2 meter by 56 mm. And so each of these will be fairly heavy, and only a few of them will be put on a truck and carried to the inside. The gap between successive layers is about 40 mm, so we have to have the glass resistive chambers in a vertical dimension of only about 35 mm. The magnetic field will be about 1 Tesla, as I already said, for 90% of the volume of the detector, which is fine, as shown by our simulations. So the challenges and issues are that you have a large magnet, you have large copper coils. The copper coils which will power this electromagnet are of the order of 8 meter wide by 15 meter high. They will carry about 80 kiloampere, so there will be 80 kiloampere turns, and weigh about 150 tons. The assembly of this magnet is another challenge. We have assembled mini ICAL, but that's a very tiny magnet as compared to ICAL. So we will, of course, learn when we assemble the engineering module, which is about 10 times bigger than the mini ICAL. But there will be still things that we will learn from that assembly and which we will have to implement in the assembly of the ICAL. We'll have to preserve planarity of the magnet. We will, of course, have piecewise uniformity of the field, 1 Tesla, as I already said. The measurement of the interior B field, by the way, is an open problem, because the methods that we have, which are putting Hall probes in intended gaps, they only tell you about the local fields. Similarly, when you have a pickup coil, you know that when you ramp up the magnet, it will induce an EMF in that pickup coil, which runs over the whole cross section of the plate. Then it gives you a the integral field change, and therefore you know about the average field that you have produced. But measuring the interior B field, pixel wise or voxel wise, that is actually an open problem, and we have some ideas on it to use the muons that are stopped in the engineering module, at least, because that's on the surface. So we have enough muon flux. So these stopped mu plus particles sit interstitially between the iron atoms, and they have a magnetic moment, and they have a small polarization, and they will precess in this magnetic field. And we hope to actually use this precession to good effect, but this has not yet been demonstrated. And this is what we hope to try to do. And if that method succeeds, then of course we have a method of measuring the interior magnetic field. And then of course we have this issue of stability, both mechanical as well as current stability. The current stability is rather easy. 1% is not a very demanding number. Mechanical stability is something that we will learn over the course of time. The engineers tell us that although we have soft iron, the creep of this and so on is not very large over the lifetime of this detector. Of course, we will have the largest number of RPCs in the world, about 3 to 4 times the total number that we have in the world today. And so this is a challenge to make them, to test them, and to actually assemble, to put them in the place and make sure that they work. The number of channels electronics wise is not that big. In fact, it is about 4 million channels of electronics. That is not challenging. Detectors worldwide, I mean, not as challenging as compared to those big detectors. Of course, it is challenging for us because we are doing this on a scale that we have never done before in the country. Okay, now I come to the mini ICAL. Now, of course, when you want to build such a huge detector, it is absolutely necessary to build a smaller device because you have to learn how to assemble, how to put together things, and there might be mistakes which you would then like to correct when you build the big detector. So the mini ICAL detector is only a 85-ton detector. So you can see that it is almost 200 times smaller than the single module of ICAL, which is about 17 kilotons. But we thought we would get going, and this is all that we could build in the transit campus that we had. We couldn't have built a detector, for instance, 2 times bigger or 1.5 times bigger. I mean, this was the biggest detector that could house in the transit campus. So we decided to build it and learn from it. And this actually got working since about June 2018. Initially, it had only 10 RPCs at the center. Now we have, I think, close to 20, maybe 1 or 2 may not be working or may not be in the best of shape, but we have about double that number of RPCs that we had initially. So these are some old tracks. I don't think the date is there. There is some event number, but these have been taken very early on, soon after this whole detector got assembled. The cosmic muon tracks, for instance, this shows a curvature of the track in the bending plane, and in the non-bending plane, this is essentially straight. Okay? And then, of course, these are pictures which you have already probably seen of students and faculty assembling these and then putting them into the mini ICAL detector. Okay, so this is again some pictures again showing the same track. You can measure cosmic mu plus and mu minus separately from the track. These are some of the magnet components that were built by the VRC group. So, for instance, the iron plates were bought from industry, from steel making industry, low carbon, very low carbon steel from SR in Gujarat. And then these were sent to a company in somewhere in Bihar, to Bihar or Jharkhand, I don't remember. And they were machined. And this was all done by the VRC group. They oversaw that. And this was machined to specifications. And in fact, it was inspected and then put onto a truck. And these plates, as were required in the size and shapes that were required, came to Madurai. We also learned in this process that it is not just enough to inspect at the machining site, but also take care of how it is packed, because we learned that when these plates were actually assembled into mini ICAL, we found that they had acquired a small curvature, and that was because of the, we not just strongly suspect, I think we realized that it is very important to stack these plates in the truck the way they should be, and these were not done in that way, and therefore the self weight of the plates themselves caused a sag in the plates. Okay. So then these are the various spacers and pins in order to keep these various layers apart by about 45 mm. And then this is the copper spool, which is imported from, I think, Austria. And then the spool is about 35 mm square cross-section conductor with a 17 or 18 mm hole in the center to carry water, which can then cool the coil when the current passes through the conductor and heats it up to carry away the heat. And these had to be straightened out first. So most of the job which was done in the BRC central workshops was actually consisting of, straightening out the conductor before it was bent in the shapes that were required. So we had a U and a C. You can see the U here and the C, which constitute the coils that were then put together when they came to Madurai. So some preparatory work had been done. Some insulating layers were put on the ground. These are support pillars for the iron magnet, and this is how these copper conductors came in 2 pieces: the U and the C sections. And then the U section was first put. Then the iron was assembled carefully by an agency actually from Coimbatore, So these are workers from this Coimbatore company that came and helped assemble this. So the preparatory work for that, the movable crane and so on, that was ordered again from some companies in Tamil Nadu. And they assembled one piece by piece this magnet. So you can see while how this assembly went on. They had to be careful that they didn't damage the copper conductors, because otherwise then there would be a leak in that, and then you would have to fix that and so on. So this was done very carefully. And then after all the plates were assembled, 11 of them, 11 layers were all put together, then the C-section was brazed on one by one by people who had come from the central workshops in BRC. They had already tried this brazing procedure with a different technique of so-called induction brazing at BRC, and had successfully tested those brazed joints for pressure and for current and for resistance and so on. And they had qualified this welding procedure. So they came, two of them came here, and within a couple of days, they did, all the brazing that were needed. About, I think, 80 or 85 of them were needed. And they did all of that, successfully tested them again for leaks, water leaks, and there was no leaky brazing joint that was found. So this was a very, very pleasant experience, that copper coil brazing could be done in situ without any mishap and without any problem in the weld. On the other hand, as I already mentioned, we found a problem in the in the planarity of the some of the plates that had come, and that was due to not proper piling of them and support structures while they came in the truck proper. Okay. This is a cooling system that was designed by the BRC group. It is probably not the best that could be designed, but this was also a learning experience for the people who were involved from the technical services division in BRC. But they finally did a very nice job, saying, such that we could cool the coils when operating the magnet with the magnetic field. So this is a refrigerator, and the water comes in, is cooled down, and then mixes with normal temperature water in the right proportion to give you the temperature that you seek and at the flow rate that you want. So this not only cools the magnet, it also cools the power supply that is in a room adjoining this setup. It's a Dan-Physic power supply which we are using right now, and that cooled chilled water also goes to that power supply, because it cools the bank of transistors which is used in this power supply. Okay, so of course, as I already showed one simulation, we did the simulations again for the mini ICAL detector, mini ICAL magnet as well. And here we have, as I said, two ways of measuring the magnetic field: a Hall probe in intended gaps, such as these. Okay, so these are about 10 in number, and then we also have pickup coils, so which span the the sections of the magnet plates, so as to estimate what is the change in the flux that they see, and then that can be measured with electronically. That signal, DC signal, has to be amplified and then displayed and recorded. And so these are some pictures of the magnet power supply. This we got from VCC. One card was not working, so this was replaced and it got working. So VCC played an important role in getting this power supply working and transported to Madurai. But they also had the software to actually see how much current you're increasing and recording the current on a PC based system. And this Hall probe PCB strip was made according to the specification which the BRC group had given to a company in Pune, and this was delivered by them. In fact, now the improved version of that is going to be coming. Also, that same company has, I think, built the calibration magnet. That company, or maybe some other company, I don't remember. But we need to calibrate these Hall probes, and that will be done at several points. So that earlier we had only 2-point calibration. Now we will have several point calibration. up to a field which is higher than what was there before, and which is spanning the field that we will actually have in the maniacal manner. So it will be a much better measurement of the magnetic field that we will have. This will happen in probably a month or so from now. Okay, so these are some of the pictures which probably, I don't know whether you have seen them already. The glass gaps which were made in a company called Saint-Gobain in Sribabati in Tamil Nadu, and they made about 400 such gaps. Of course, we have some problems, some issues with some of these gaps, and we are trying to resolve these issues with an in-house facility for coating and so on that we have in the transit camp at Madurai. Then this is the closed loop system that was developed again in together with industry, local industry in Mumbai.
Sir,
yeah, sorry. How
sir,
much
can
time?
you speak slightly louder, sir?
Oh, speak louder. Okay, okay.
Yes.
Sorry. Okay, so these are some of the pictures which show various components of the maniacal magnet system. You know, these RPCs need a gas, and that gas has to be reused. And so this is a closed loop gas system which purifies the gas that comes out from the RPCs and then again sends it back to the RPC. These are some of the front-end electronics hybrids that were used at various stages. Initially, it was in some way we had used it for the TIFR setup, then for the Madurai setup, and finally whatever we are using now in the maniacal. This is a DOQ card. You can see this is so compact. Compare it with the pencil size here, and there's I think a 2-story card. Then there is the DC to DC high voltage card, which gives you plus or minus up to 5 kilovolt. This was designed and developed by the PRC and TIFR groups in collaboration. This is a 8-channel front-end electronics board that sits next to the RPCs in a very small space so that you don't eat up active detector space. And this is, some of the trigger electronics and other associated electronics with DAQ and so on. Okay. These are some of the cosmic muon spectra taken by one of the, and the data has been prepared by one of the PhD students of the INO GTP program. I've taken it from him. This is from Apurva Bhatt and Govinda Majumdar, of course, the faculty, project director. So they work together to generate this cosmic muon spectrum. You can see that the mu plus and mu minus spectrum, of course, in a limited range of momenta, because this detector is not very big. As I said, it's only 1/200th of the eventual detector, but still in this small region, the spectrum matches the Corsica simulation. Okay. Now I come to another, effort that we were involved in. This was part of the thesis of one of the, again, INO students, Neha. But we also started off with some of the INO GTP students. So eventually that work turned out to be quite nice enough to publish. And so the 3 INO graduate training program students are also part of that paper. Of course, Neha, the PhD student, and a few of us. So the idea was that can you enhance the, the capability of a detector, or indeed put it at a somewhat lower depth. But even if you have, let's say, an engineering module on the surface, can you put this detector around and then try to see if you can see upward going neutrinos? Of course, the count rates will be much smaller because the engineering module, although it's about 700 tons, it would still detect neutrinos probably only once in a month or so. But this idea, in order that we explore this idea, we built a small device ourselves with whatever we could lay hands on at TIFR. And the graduate students did a very nice job. Graduate students and the PhD students did a very nice job together with help from our technical people. And we managed to put together a 1 meter by 1 meter by 0.3 meter cosmic muon veto detector. So the way we did it, we put a small detector inside, and which has a 4-layer detector which or 3-layer, I think in this case. No, sorry, it's a 4-layer detector with lead in between so that you prevent gamma scattering events to give a false alarm. And so with this 4-layer detector, we could identify muons quite clearly. And then we put a hut of plastic scintillators around that. I think it was a 4-layer hut, 3-layer hut of plastic scintillators that were already there lying around in the lab. And we put them together with this, and we found, at least to my pleasant surprise, I did not expect, this close to 4 nines efficiency. I thought we would get somewhere near 2 or 3 nines, but it was a very pleasant surprise that we could get a veto efficiency of this number, 99.98%, plus minus 0.03. And this was reported, in fact, in a paper published. So this is motivated a proposal to build a cosmic muon V2 detector around mini ICAL. And some of our friends in Fermilab who have the possibility of making this liquid scintillator in their lab, they expressed, they said that we could make this scintillator for you right now. So this extruded so-called plastic scintillator was made in Fermilab, and some of our colleagues went there while this was being made, and then this was shipped free of cost. The shipping was not free of cost, but making the scintillator was very kindly agreed to by Fermilab to give it to us free of cost. And so this is the kind of detector that we had proposed. We put around mini ICAL, and I don't know whether I have a photograph of that, oh no, this is just a drawing of the scintillator veto that we plan to have. 3 sides and then 1 on top, but eventually probably we could have a moving element here as well in case that is necessary. Okay, so the assembly of this parts of this veto detector is already taking place. I have not visited this lab since lockdown, so but these young people are doing a magnificent job, as you can see. They have already assembled together such a strip or detector, which is probably about I think 4 or 5 of these 10 centimeter wide die counters. And so the idea is to put these plastic scintillators, which are actually which have 2 holes in each of those 5 centimeter extruded scintillator for the so-called wavelength shifting fiber, which is looked at by silicon photomultipliers at either end. So the wavelength shifting fiber and the silicon PMs we had to import, both from Japan. This is the Kurare fiber, and this is from Hamamatsu. And we are hoping that with this, we will get a muon efficiency greater than 3.9 efficiency, 99.9% efficiency. So this, So this shows the assembly towards the end of the detector, which will have to be put together, where the silicon photomultiplier will look at these scintillations that are transported by the wavelength shifting fiber. Okay, so this is work in progress, and I think many of you we will be happy to involve you in some of these activities at the transit camp at Madurai. Okay, so from here, where do we go? We will like to build a device which is about 10 times bigger. So instead of the 4 meter by 4 meter, we will have a 8 meter by 8 meter setup. This will actually this will simulate or give us experience on how to put these RPC detectors in one road. So 1/2 of that 16 meter detector. And this is a trolley which was already put together in a company again in, I think, Vellore. It was, inspected, and it was delivered in 2017. So that's almost 4 years ago. And this is about 8.5 meter or so high. And this can, initially we had an idea of making the engineering module to about 8 meter height. But we then settled for a smaller detector because that would also require many more RPCs and so on. And so we settled for a smaller device, 10 times bigger device. But so we can use part of this trolley to actually go up and place these detectors. There is also, okay, that is, I think, there on the next slide. So this magnetized calorimeter will be about 8 meter by 8 meter by about 2.5 meter, 2.3 meter in height with 23 layers of soft iron and 20 layers of RPCs. Those amount to about 350 or so. Okay, what will we do at ICHEP? We will build this in the on the surface. We will test the assembly of these. We will try out, at least for part of the copper coil, we will try out a different methodology with 2 Cs and one, or rather, it should be 2 Is, 2 Cs and 2 Is. And we will have, of course, a much larger LCW system, a much larger gas system. And we will also have a special, the same trolley which you saw, but only part of it will be used, about half of it or something. And we will have robotics for insertion and extraction of these RPCs in the 8-meter road. Of course, we will have much larger data than the mini ICAL. So we will test out this towards going to the full ICAL detector. E-ICAL will measure about 6,000 muons per second, and about this is the proportion, about 3.3 positive muon, just an estimate, of course, and 2.7 K of mu minus. And it will measure it at near equatorial latitude. We already have some measurements with mini ICAL, but this will do it with much better statistics from and up to with a larger energy range, 0.5 to 3 GeV, but also a slightly higher energy in case they come at angles. Okay, so this is an angle dependent upper limit that we have, and this will help hopefully sharpen atmospheric mu flux calculations. These calculations already exist. Professor Sijjad Datar from Aligarh Muslim University, in collaboration with the father of such similar flux calculations, which is Honda in Japan, they have already made calculations for this site. And in case something needs to be tuned up, these measurements will help. As I already said, we will also test the feasibility of the muon magnetic moment spin rotation in the magnetic field for information about the internal magnetic field using stopped muons. And since this has many more layers, you will have many more stopped muons. But whether this method works at all, we will know when we do the experiment at ICHEP, when we will run ICHEP. Okay, now these, how am I doing in time, Satya? Hello? Hello?
I think you have sufficient time, Datar.
I have sufficient time. Okay. So
you have 18 minutes more for the whole thing, including questions.
Oh, including questions. Okay.
Yeah.
So I should try to finish in about maybe 7 to 8 minutes. So the engineering module of the ICAL will measure both mu plus and mu minus separately, and this will complement some of the measurements, some very nice measurements that have been done not too far away in Ooty by the GRAPES 3 collaboration. For instance, the GRAPES 3 collaboration, I will come to 2 measurements that they did that were reported and also got a lot of publicity. One of the measurements they did was to try to understand natural phenomena such as geomagnetic storms. And they occur because there are strong solar storms, and then that proton wind, so to speak, comes and impacts on the Earth, and that leads to a weakening of the magnetic field, to indeed a disruption of the magnetic field. And that could also affect satellite communication and so on. And so this is quite important to understand what happens. And in some of the strongest solar storms, which will lead, of course, to strong geomagnetic storms as well, they could be quite damaging. So this one such incident was studied by the GRAPES 3 and reported in a physical review letter. As I said, it got a lot of publicity. Basically, they were counting muons in a very large array, and they found that due to the protons coming in from the sun, proton wind, so to speak, coming in from the sun and disrupting the Earth's magnetic field, they made a small hole in the Earth's magnetic field, and that led to a slight increase in the muon counting rate in their detectors. How small was this? Not very much. This was of the order of about 1.5% or so, as you can see from here. This is time axis, and this is the muon rate variation. This is hardly a 2% rise. And this is from one of the strongest solar storms. So this could be detected, and as I show, this could be simulated as well. And there's one more picture that is taken from their paper in visitor letters. So the protons are coming in, and these are, I think, the galactic cosmic rays, mainly protons. Of course, there are also alphas and so on, and they bend in the Earth's magnetic field. And when they come in, they change the magnetic field, and the cosmic muons which are coming from, let's say, if we talk about galactic cosmic rays from the Milky Way, then they're coming from mostly from the center of the galaxy. But there are also other protons coming from elsewhere, and then they actually give rise to muons by interacting with the upper atmosphere. And the engineering module of the iCal will have the ability to distinguish mu plus from mu minus. So the grapes cannot distinguish between mu plus and mu minus. It gets an integral measurement. It is an integral measurement. And so this might help in actually, having data which complements that of the grapes 3. For instance, it could change perhaps the azimuthal asymmetries and so on. But this is something that we have to still work on and do some simulations on and see what is the effect that you expect, and what is it that the engineering iCal module could add in a complementary way. Grapes 3 has also addressed electrical charge and high voltages that occur on thunderclouds. In fact, their measurements seem to indicate that the voltages that are there on thunderclouds are about 10 times higher than what was thought before. And this is another publication in 2019. And so what they see is a drop in the muon flux. So there are more mu pluses than mu minuses. So this must be coming from a drop in the mu plus flux. And this is, they theorize, because of the electric potential of up to about 1 giga electron volt on the clouds. So you have a electrical potential in the cloud. The upper layer might be positive and the lower might be negative and so on. And that might affect the muon flux that you see. And again, because we have the possibility of measuring mu plus, mu minus, we could see perhaps a change in one, but a different change in the other. Anyway, this is something that, again, needs more work, but this is a possible area where we could complement the grapes 3 measurement by our own colleagues in UT. Okay, if the CMVD is used, then eICal will allow better up-down discrimination of muons, and possibly we could even identify upgoing atmospheric neutrinos, new mu's, which are going up in the iCal detector. And if you make a very rough back of the envelope estimate, you could see up to 1 per month or something like that, or a couple of them per month. Okay, if iCal becomes possible at Pottipuram, of course, right now we are having problems, but I do hope that all the problems will be solved. Then the eICal can be used as a test bench for a large scale testing of RPCs. And this could be of the order of, let's say, 300 per week. Okay, because we need these large number to populate the 50 kiloton detector. We need 30,000 of them. And so of the order of 100 weeks will be required if this is the this is the rate at which you test them. 100 weeks is, of course, about 2 years. So this is the right time scale. The spin-off of this large-scale production of RPCs is that it could be used to do tomography of reactors, volcanoes, hillocks for archaeology, and so on. I mentioned some of these things yesterday, and anyway, I thought to be complete, I should put this here as well. And of course, very importantly, the eICal will help train a large number of students and also the scientific and technical staff, and prepare us for going to iCal. So these are the spin-offs in a little more detail, but I think I'm already short of time. So it could be used for container screening, for instance, to do tomography, as I already said. It could do tomography of the Earth, at least it could do the feasibility study of a neutrino tomography of the Earth, and this would complement seismic measurements. It could be part of a multi-messenger astronomy of violent events in the universe. And it could possibly, this is a very, very far-fetched thing, but in case somebody, one of you or one of the young people anywhere in the world has a very bright idea of producing compact, cheap and directional neutrino beams with the compact accelerators, then perhaps this could one day result in communication by neutrinos. And as you can see that if you have to communicate from one end of the Earth to the opposite end of the Earth, the way the present communication goes is that it goes via satellites. So it goes all around the Earth. And if you have neutrinos for communication, then of course they can penetrate the Earth directly And so this will be a faster way of communicating. Okay, so this is a very futuristic, but nevertheless, what appears to be futuristic today might be commonplace 20 years hence. Who imagined that mobiles will come in the 1980s? Thank you. So you may please ask any question. As I already said yesterday, however stupid you might think to be, but it's not actually stupid. As I said, there might be only stupid answers for me. So please ask if you have any doubts or even other questions. Thank you.
Yeah, thanks, sir. So any questions to Professor?
Maybe I should stop sharing.
Yes, sir. Yes, sir.
Yeah.
So please feel free to ask any questions that you have for this part.
Vivek, there is a question in the chat box.
Oh, yeah. Okay. That question is the grapes. I don't know too much about grapes, but they have a large array for looking at showers produced by cosmic rays. I don't remember the area, but it could be of the order of a kilometer square or something. But they have a smaller aerial coverage for looking at muons specifically with very high statistics. So the total coverage, I think, of that detector is about of the order of 5 times what we will have in the engineering module of ICAC. So in the engineering module, we will have about 64 square meters on. I mean, that's the cross-sectional area. I think they have something like either 250 or 300, 350 square meters coverage, where they have detectors on top, and then they have proportional counters which are subterranean. Okay, that's Satya. Thanks, Satya. Yeah, so this is the big array, but there is also this is the smaller area array where you have the proportion counters. Actually, many of those proportional counters underground are the kind of maybe what should I say, from KGF experiments, proton decay experiments. So some of them are just as they are, but some of them had to be repaired a little bit, and some of them are of course new. So these long proportional counters, I think they are 8 meters long and 10 centimeters by 10 centimeters. They are assembled in XY crisscross fashion below, and they can actually be used to track the muon and tell which direction it came from. So that was very useful when they could actually track the cloud that was moving during a thunderstorm.
Sir, the counter size is 6 meters. And
6 meter length. Okay.
Yes, sir. Yes, sir.
Okay.
There is one more.
Cross section I got right? 10 centimeters.
10 by 10, sir. 10 by 10.
10 centimeters by 10.
Sir, some more questions are there.
Yes, sure. Okay, let me. 4 questions. Very good.
Do neutrino travel faster than light?
Do neutrinos travel faster than light? Well, I think this is triggered by some work that was reported. I don't know how many years ago, maybe 7-8 years ago, or maybe a little more. I don't remember now. But faster than light neutrinos. But that turned out to be wrong. And in fact, the group that made this claim themselves found what was the problem. And it was actually due to some bad connection in an optical fiber cable. And when that was fixed, they found that neutrinos travel almost at the velocity of light, almost at the speed of light. So we don't have this. Had that, had that measurement been proven to be correct, that would have been a fantastic result. I mean, we would have to rethink relativity, but it was a false alarm.
The other question is also there, how we can detect the energy of the neutrino?
Yeah.
Whether it is higher energy or lower energy.
Okay, so the neutrino is a chargeless particle. So like the neutron, for instance, of course, neutron is very heavy and neutrino is very light, but it cannot directly cause ionization. So it has to make a reaction, or it has to scatter of something which is charged, electrically charged. So for instance, if it scatters of an electron, elastic scattering between a neutrino and an electron, then the electron recoils, and you can measure the energy of the electron. So you can get some measure of the energy of the neutrino. If you knew the direction of the neutrino, of course, you can tell what the energy of the neutrino was. If you don't know the direction, then of course you have to make some estimates. So for instance, from accelerators, you know the direction in which the neutrino is coming. So from an elastic scattering event, you can tell, because if you know the angle at which the electron comes out with respect to the direction of the beam, then you can figure out what the energy is. Okay. If it undergoes, let's say, charge current interaction, such let's say mu interacts with the nucleus, then you get a muon in the final state. And by measuring the muon energy, you can get some measure of what the original energy of the neutrino was. Okay.
Yeah.
So also, it depends very much on which energy region you're talking about and what is the detector. So it is very much dependent on what detector you use and what the source of them is, whether it's low energy, high energy, ultra high energy, and so on. But yes, you can get estimates, certainly.
Sir, Indu has typed in some more information on what you're on.
Yes.
Sorry,
Yes.
I find this chat box irresistible. So I just want to say one thing. So normally
Yes,
what
go ahead.
happens is that you don't actually directly try to measure the energy of the neutrino. What you do is that you have a distribution. You say roughly the atmospheric neutrinos that you have, that whatever energy distribution they have, results in a muon distribution, energy distribution of this kind. So what you measure are the muons, right? So then what you try to do is you don't try to go backwards from the muon energy to the neutrino energy, but you use what are called Monte Carlo simulations. So a lot of it is to do with computer programming. So those of you who are interested can look at that aspect also. What you do is that you try to fit, this energy dependence is called the spectrum. So you try to fit the spectrum of the observed muons to different spectrums which come from different possible flux distributions of the original neutrino. And then once I do this pattern matching, so to speak, then I can see, oh, this distribution of neutrino is the closest to the observed distribution of muons that I see in my detector. And therefore, you can understand what kind of spectrum you are actually measuring. So there's a lot of computer simulations involved in this. And in fact, if those of you who are interested in science and have been following this black hole detection, very, very great results that have been coming, they also do the same thing. They have patterns which they match. So instead of going backwards, you generate all the possibilities and then compare to what it is that you get in your lab.
Indu, there is one
I
more.
think I should add to, just support what she has been saying, that in this whole program of measuring neutrinos, simulations and data analysis go hand in hand. Okay, you have to know what you expect to see, and then you see, and then so there's a lot of back and forth between them. And so this is quite an involved, area, but extremely important if you want to interpret what you see in the detectors and to extract physics.
Sir, there are two more questions, one for
Yes.
you and for Indu.
I think that Vivek should take the second question first from
Which
Divakaran.
is the second question?
Yeah, I will read it out to you. Good afternoon, sir. If the size of the detector is large, is there any probability for more interaction?
No,
because
no.
it continues with
no. For the certainly, for the foreseeable energies that we can produce both in the lab and in the atmosphere, where there is no possibility of second detection. As I said,
no, not second detection. Sorry,
No, not second.
Larger detector. Does it mean that you will have more interaction?
Yeah, of course. It scales with the volume. So if you have a detector twice as large, you will get twice the number of events. Okay.
Yeah.
But this is a practical question because also the cost scales, right? Not just the cost, also the number of people involved. A much bigger detector is more difficult to service and keep up in shape, right? So it will be difficult to, it will take more time to assemble it. It will be more difficult to keep in shape. So this was something which is already, whose difficulty level is not low. It's one of the very challenging things that we have never done in the country before. And so we thought that this is something at least that we might be able to do successfully. So 50 kiloton is, of course, in the hall, we have the possibility of increasing it to 100 kilotons. But this is something that we will take a call after we have built it, after we have the experience, and if it is necessary at all.
Okay. So, Indu, can you take the question?
Yeah. So this is the question on the how much muck will be generated. So you can see that muck from blasting is 2.3 lakh cubic meters. This is the amount of, as I said, muck, we should be very clear, is actually chunks of rock. and it will be stored in this muck storage yard, which will be built to not to take all the muck that is generated, but we know that this muck belongs to the forest department, and so they will keep taking it out and selling it or using it for their own purposes. And so we will only keep that much volume available, about a factor of 2 times larger to what we estimate that they will keep taking out. So that when you store it, you are storing only temporarily, and then it is taken out and taken away by trucks to wherever the sales point or wherever else it is going to go. So the question is, where will it be stored? Yes, part of it will be stored, but as I said, continuously it will be taken out. Just within a few kilometers of the site is the state highway number 100. So there's a huge state highway on which a lot of hundreds of trucks go every day. So this also will be taken out in trucks to wherever it will need to be sold or whatever. And the last question is, during winter season, it may be difficult to store. So there are things here. Now we are in 10-degree north latitude. There is not much winter and summer here. Temperatures are constant almost during the entire year. However, there are certain seasons, especially before the rainy season, where it is windy. So there we have to be sure, and we talked about it also, we have to be sure that we have to provide a windscreen so that the powder part of the rock doesn't fly and cause air pollution. So that is what we have to take care of. It is not winter or summer as much as the windy season. There is a windy season in that place, and we have to make sure that we are wetting the muck, and therefore we can.
There is a question by Nazreen, which I think I can take.
Yeah, sure. I'm finished with this.
So she has asked, do we use pure water as the medium in Kamyokande, Japan? We use in large volumes. Why couldn't we use some other medium? So if you mean that instead of water, we use some other medium, like maybe some organic fluid or something, then the answer to that is water is a very cheap, Any organic substance will be more expensive. And the other most important point is that we wanted to make a magnetic detector involving a magnet so that we could identify mu plus and mu minus. Water Cherenkov detectors, since they're so huge, they cannot have a magnetic field built around them. That would be just prohibitively expensive, and one could not manage that at all. So all the big water Cherenkov detectors have no magnetic field. Okay, in principle, therefore you cannot identify mu plus from mu minus. There are techniques which will segregate some events and so on, but event by event you cannot do that as a magnetic detector would do. So this was one of the reasons. And iron is not a very expensive material. I mean, iron is something like of the order of let's say 50 rupees a kilo or of that order. It may go up and down depending on the demand. But even this low carbon steel is of that order. So it's not all that expensive. Okay. And most importantly, apart from the fact that it provides you with nucleons with which the neutrino can interact, it is magnetic. And there is no other cheap material which is magnetic. Nickel is magnetic, but it's much more expensive. Rare earths, some of them are magnetic, but as you can understand from the name itself, it's rare. So obviously it will be very expensive. And I should also say something else. We don't use permanent magnets because again, they're way too expensive and you cannot change the current direction and so on with permanent magnets. So that is ruled out. Now, could we have superconducting magnets? Yes, we could. But the paraphernalia that is required for that, liquid helium and so on, the cryogenics, that is humongous for such a large detector. So we considered this possibility, but we quickly threw it away because it's much more attractive to build a room temperature magnet using iron and copper. I hope that answers your question. Yeah. Nazreen?
Okay. Yeah, so the question that was asked was to Indumathi, madam, what are the computer simulation software used in this project? So as I said, I've written in the text, CERN is the place in Geneva, Switzerland, where this God particle was discovered. It is a huge particle physics lab. And CERN scientists, which also includes Indians, have developed some software which allows you to actually see these interacting particles, how the neutrino collides with the iron is a different thing, but how these interacting particles propagate through the medium of iron and RPC, how those electronic hits are found in the detector. All this is a software which is called GF. So this 4 means that it is written in C++. 3 was written in Fortran. So there's a lot of modules available which allow you to turn on and turn off electric field, magnetic field, or both. Turn on and turn off electromagnetic interactions, strong interactions. So you can actually ask, what happens if I throw a pion into the ICAL detector? What happens if I throw a muon into the ICAL detector? So how do you even construct the ICAL detector? Every component of the ICAL detector can be coded into the software. So it has a software with the proper geometry, the material type, its density, its various physics parameters. Everything is there, which is coded into this thing. Now, once you have the particles propagating through and you have the dots, which are the hits in the detector, you have to convert those hits back to information about, say, the momentum of the muon, etc. So for that, you have to write your own code. So that is also a C++ code, which is an in-house ICAL, the INO collaboration has developed. And that uses something called a Kalman filter-based algorithm to invert this curvature of the track, and from the curvature of the track come back to what is the momentum of the muon, and various things like that. So all those are the different software that is being used. It's a huge effort, actually. It is very complex and a huge effort. Many students are involved in this.
Okay, there is a question by Ajit Mohammed.
Yeah.
Let me see.
Sir, just one.
Yeah,
Yes,
yeah. Sir.
No, I was wondering if Hindu can also say a few more words about the generators.
Okay, fine. Sorry. So let me start one by one. So neutrino interacts with iron, right? Now the thing is that this particular CERN GANT4 code didn't spend too much time on neutrinos. Why? Because neutrinos don't interact. So whatever you have, big accelerator and CERN, the neutrino simply goes through all the detectors and nothing is detected. So they didn't care about the neutrinos. So specifically only for the neutrinos, you have to have a separate code which tells you how the muons are generated in the first place. That is, we know that in nature, the muon neutrinos will come, hit the ion and produce muons, right? Either charge minus or charge plus muons. So this whole thing should have been there in the GANT4 package. I hope it will come into the GANT4 package at some point. But right now it is a standalone code. And there are different generators. These are called how you generate the interaction. So they're called generators of the interaction. And there are some 3 or 4 in the market. And everybody uses their favorite one. And in fact, within the collaboration, I use my favorite one and other people use their favorite one. But at some point, these generators will be replaced with the information that you get from actually measuring the muons directly from our prototype. See, we are measuring, the prototype is on the surface, right? Whatever you will see in the labs tomorrow is on the surface. You are still seeing muons, but these are the cosmic muons. But you remember, these are the cosmic muons which are decaying to give you the neutrinos, which will be the atmospheric neutrinos of interest. So if we directly measure the flux of muons, then we can put that into our codes and we will have much better generators. So this is an ongoing process. So right now there are various groups which are actually telling you what the neutrino spectrum is like and how it interacts with the ion and generates. One of them is called Nuance, for instance. That is my favorite one, but there are so many which are there in the market. And there's a C++ code called Genie. So there are many of these things. Once you generate the final states, which is the muons and the other particles which I called, then you put it into the GANT and then propagate it through the particle, through the detector. So everything is simulated. The detector is simulated, the interactions are simulated, the final states propagating through the matter are simulated, the magnetic field is simulated. So it's a huge simulations program. Very nice to work with. Okay.
So,
is it done, Satya? Is that okay?
Yeah. We go back to
so Ajit Mohammed had this question.
Yeah. What are the major differences in the neutrino project under the sea and under the land? Okay,
yes,
so
sir.
the major difference is, of course, this volume of the active element that interacts with the neutrinos. I mean, they have something like a kilometer cubed, and they're thinking of even expanding it in upgrades to that to maybe 10 kilometer cubed or something.
No. He's asking about the water, Mediterranean, not ice.
That's right. What is the difference between under the sea and under the land? So these are huge projects. So but you can't think of having 1 kilometer cubed or 10 kilometer cubed detector built by human beings. Okay, so that is one difference. The other is, of course, that it's a and these detectors, by the way, are mainly built for looking at astrophysical processes that are going on in remote parts of the universe. Of course, the detectors that we build also will be, but they will not be that sensitive to those rare processes that go on. Okay, and secondly, you cannot have magnetic fields in in a sea, in a detector with the water in the sea. Okay? Whereas here you have much more controlled conditions. You can control the magnetic field and then you can identify things much better and so on. So, but it is much smaller. Obviously, it is much smaller than a 1 kilometer cube detector. So these are the advantages and disadvantages of these two ways of approaching detection of neutrinos. So as I said, one is mainly for very rare astrophysical events. The other is for more, more recurring events, such as from accelerators or atmospheric neutrinos and things like that. Does that answer your question, Ajit?
I hope so, sir. Okay.
He's
So,
not on Zoom. Okay. Anyway.
Yeah. Okay. Yeah. He says yes, sir.
Yeah, I think we should stop because we are running behind time,
Okay.
no?
Yeah. Okay. So it's 12 noon, in fact. So good, because there are questions. So therefore, it's always nice to end the talk with an interesting question. So, so we end this pre-lunch session at this moment. Okay. Of course, we'll thank all the speakers in the morning, but then we'll assemble back at 2 o'clock. As I said, that we will have a very young speaker talking about taking us through the spin-offs and benefits of INO project in general. Any high energy, nuclear, astro, all these experiments not only do science, but they also bring a lot of value to the people on the street. Sometimes it takes, unlike our applied science, which has its effects rather quickly because they're meant to.
Can I interrupt, Satya? There are two more questions. I think you should take them since we have little.
Other ones, it takes time, but nevertheless, there are also benefits which will come. So we will have a session on that, and also, as I said, after that it will be a session on how to improve the public interaction communication skill. And then of course at the end. Okay. So having said that, yeah, since there are questions again, okay, let us take that. Yeah. Indu, go ahead.
Okay, so Nasreen has asked, it is a large network of simulations. So in case of any faults in device, will it cause any problems environmentally? So the simulations is only to tell us an estimate of how many events we will get, what will be the distribution of the energy in the angle and things like that. Okay, so if we make a mistake, we will get wrong physics results. But please understand that there is a genuine experiment where the genuine neutrinos are coming and interacting with the iron. And as I said, of the billions and billions of neutrinos going through the iron, a few will interact and we'll get 3 events a day in the huge detector. So there cannot be any environmental problems from these neutrino interactions or even from the cosmic ray muons coming through the detector. So there are 2 kinds of particles which go through the detector. One is this background cosmic ray muons. So if the detector is not there, they will be going through the earth, which will be there instead of the detector. And if the detector is there, it will first go through the earth, and then when it reaches the detector, it will go through the detector. The only difference is that when it goes through the earth, no one observes it. When it goes through the detector, there are electronics signals to detect it. But otherwise, it is always going through. It cannot be stopped. Nothing can stop these muons or the neutrinos. So there can be no problems because right now, whatever muons are going through us or going through the earth, either in Chennai or Bombay or Madurai, wherever, it is simply going through. And the other component is the neutrinos coming in, which will again interact with the detector. Same thing, the neutrinos can also interact with the earth, except that nobody will be there to observe the final states. When it interacts inside the detector, then you will see the final states and you will try to understand the neutrino properties from it.
No,
So,
I think Indu, I think the question was probably aimed at saying that do the simulation in some way affect the devices that you're using?
Yeah. So I'm coming to that.
Short answer is no.
So I'm coming to that. So what the whole simulation does is it asks you the question, how do we understand the events distribution in energy and other parameters, right? So it will not tell you how to build this device. The RPC is not built using the simulation. How the iron plates are built is using mechanical engineering skills to make sure that the device is stable, right? Because it's a very heavy device. But that is not coming from the simulation. So I think that is Vivek's 1 second answer. The answer is no.
Okay, there is another question.
Yes, to Datar,
Ajit Muhammad. He says, what happens when there is an earthquake or a rock burst? Does it affect our drilling process? So when this tunnel building is going on, yes, there will be rock fall and so on, and that will be collected. Now, what they do is, as they go along, if there are any weak points, they think they will put concrete and they will patch it up so that it will become tied to the rest of the area of the cavern. I don't know if Indu wants to add to that, but they are quite experienced, and this is a very good rock that is there. So hopefully there will not be much of this happening. And indeed, even in the cavern, if there are some points that they think needs some concreting, they will do that, and they will put these so-called rock bolts and things to strengthen it in case they think it is necessary.
Yeah, so this is the that as Vivek said, there are two questions here. One is earthquake and one is rock burst. So rock burst happens when the stresses on the rock are very high, so that when you start drilling it, then it explodes because the stress is suddenly released and then it explodes in a burst. So this is called rock forecasting. So the geologists are actually always forecasting what rock is coming a few meters ahead, because in a day they can do some 2-3 meters of drilling only. So it is very small amount. So what is coming beyond is something that they will try to forecast, looking at the way the faults are going, and that is something that they will map and they will look at. So if they feel that a weak section of rock is coming up, as Vivek said, they will do rock bolting. They will take huge bolts and drill it directly into the side walls, and that those iron pieces will actually hold that rock together and prevent it from crumbling. This is very standard rock tunneling technology. And if the rock quality is good, there should be very few of such weak spots. But whatever spots are there, they will be mapped and they will be taken care of. So it will affect our drilling process, because there's always an engineer who's watching it and looking and making sure that they're drilling in the right way. So there's definitely something that the engineers have to take care of. The other is the earthquake. Now, actually, underground is one of the safest places to be during an earthquake. This is something even I didn't know when I started learning about geology, because it's the surface facilities which are always more effective. So in fact, the buildings on the surface will be more affected by the earthquake, whereas the structures which are deep underground are hardly affected at all. However, there are surface structures. We are going to have some residential houses. We're going to have some offices and things like that on the surface. So just like any other house that you build in Chennai or Madurai or whatever, that you're in seismic zone 2. So you have to build up to that this thing. In fact, I think the engineers have decided to build up to the next level of seismicity to make sure that the buildings are extremely stable, and that is just taken care of for the surface facilities. As I said, the underground structures are extremely safe during the earthquake.
So I should just say, Ajit, that is not a stupid question at all.
Good question. By the way, yes. In fact, I wanted to say that and I forgot. Yes.
Yeah.
Yes.
Okay.
Very nice. Actually, very nice questions are coming up. Yeah. I hope that chat boxes also are being saved so that we can write them down somewhere and we'll have a list of complete questions.
Sure.
I tried to do some screenshots, but I keep missing. So
Anyway, but also we have videos. Many of them. You are also repeating some way the questions.
Yeah. Correct. Yeah, correct. We'll have to extract it from there. Yeah, but I think there's a way in Zoom to save the chat as well. If you save it, it will be nice. Yeah.
Okay.
Thank you.
We should stop at this point because there is still an opportunity to continue this at 4:30 for these interactions. But we'll get back at 2 o'clock after lunch for the next session, which is on spin-offs. Okay. With that. So thank you. Thank you for now.
Okay. Bye, everyone.
Goodbye.
Sorry, Shotto, I missed what happened to Amol's thing.
This study of neutrinos is important and exciting because they are one of nature's fundamental particles of which we know little about. There are other mysteries in the universe that can be answered by using neutrinos as probes. Post the Higgs boson discovery, popularly known as the God particle, scientists look towards neutrino experiments for clues to understand the complexities in the universe. Many countries have taken initiatives to set up experiments to study neutrinos. The Super Kamiokande Neutrino Observatory in Japan hosts one of the prominent experiments. It was here that a neutrino oscillation was proved and was subsequently awarded the 2002 Nobel Prize. The Sudbury Neutrino Observatory in Canada is similar to the Super Kamiokande. The Gran Sasso Lab in Italy is the largest underground laboratory in the world for experiments in particle physics, particle astrophysics, and nuclear astrophysics. They run many experiments, including neutrino physics, in their underground lab. The IceCube Neutrino Observatory, or simply IceCube, is a neutrino telescope constructed in the South Pole. The detectors are optical sensors inserted deep inside the Antarctic ice. When neutrinos interact with molecules of water in ice, they produce signals which are picked up by the detectors, and these are then studied. There are still other experiments like MINOS, Diabe, etc., each one trying to understand the different aspects of neutrinos. The experimental field of neutrino physics is now moving into a phase where decisive and high-precision experiments are needed. It is in this context that an initiative began to take shape a few years ago, leading to the idea of an India-based neutrino observatory, or the INO. Now that we have a brief idea of neutrinos, let's take a look at the history of neutrino experiments.
Neutrino research is not new to Indian scientists. In fact, the first ever cosmic ray neutrino was detected in an experiment at Kolar Goldfields in a deep underground lab in 1965. However, since the neutrino field has become a very exciting area of research, the Indian scientists are thinking of starting a new laboratory, underground laboratory somewhere to study neutrinos again. This is one of the biggest high energy physics project, or you can say biggest experimental project in the country right now.
So let's understand how we can detect neutrinos at the INO.
The primary aim of the neutrino detector in INO is to study the atmospheric neutrino oscillations. It will determine the neutrino mixing parameters precisely and also address the question of neutrino mass ordering. The chief feature of this detector is that it can distinguish between neutrinos and antineutrinos. About a kilometer of rock is needed to filter away cosmic rays so that the detector can become sensitive enough to detect the neutrinos.
Only neutrinos and some very energetic muons can penetrate more than a kilometer of the Earth's rocks. So, neutrino detectors are mostly located under a mountain or in a mine, so as to filter out cosmic rays. After surveying several sites, the West Bodhi Hills in Theni district, about 110 kilometers from Madurai in Tamil Nadu, has been chosen for this project. Geological, seismic, and environmental factors all favor this place. The proposed lab is under the mountain and will have 3 interconnected caverns that will house the 3 main experiments, besides areas for services, electronics, control room, etc. A 2-kilometer long motorable tunnel will connect the caverns to the outside of the mountain.
The flagship experiment of the INO project is a massive 50 kiloton magnetized iron calorimeter, or ICAL.
The ICAL will consist of particle detectors called resistive plate chambers, that is RPC, arranged in between 56 mm thick iron slabs. The ICAL is a giant 150 layers sandwich of old iron and RPCs weighing 50,000 tons. One purpose of such a large quantity of iron is to offer densely packed iron atoms in the path of neutrinos and other particles. The detector can measure the energy of the particles, hence the name calorimeter. over 30,000 RPCs will be used in this detector. The size of the RPCs would be similar to 4 carom boards placed in a square fashion.
About 3.6 million channels or wires will carry electronic signals from the RPCs, and finally the data will be stored in a computer. A sophisticated electronics, data acquisition, trigger, monitoring and data network systems are being designed specially for this experiment.
One unique feature of the iCal will be its ability to distinguish between neutrinos and antineutrinos. For this purpose, the iCal will have the world's largest electromagnet, consisting of current-carrying coils that will magnetize the iron of the entire detector. Just as a telescope observes the sky through visible light, the iCal will observe the sky through neutrinos. Similarly, the iCal can also look towards the core of the Earth.
The magnet, which is 52,000 tons, will be the biggest in the world after it is constructed.
The weight of the iCal is the weight of about 10,000 elephants. The area of the iCal would be the area occupied by about 160 Tata Nano cars. The laboratory will also host several other experiments such as neutrino-less double beta decay, which would shed light on the nature of neutrinos. It will also host an experiment for detecting dark matter.
Neutrino-less double beta decay experiment will test the true nature of the neutrino. This experiment will be set up in the control room cavern of the INO tunnel. We will be making a detector with 124-tin nucleus. When it undergoes a double beta decay, the 2 electrons will be produced, and we are making a detector to precisely measure the energy of these 2 electrons. This bolometer detector will operate at a very low temperature, which will enable the measurement of the energy of electrons very, very precisely. At present, the group's effort is focused in developing such a low temperature bolometer in our lab at TIFR.
Dark matter experiment is also planned at the INO complex along with some more futuristic scientific programs. The INO will not only be a neutrino observatory. In the long run, it will host other experiments related to geology, biology, among others. Outside the hills, surface facilities like housing for scientists, engineers and other workers, hostel for students, labs, offices and workshops will be constructed in the available land.
So it's of a scale which is different and large and ambitious, and I think it's something that it's great to see that scientists in India, I mean, this is a national effort, of course, and it's great to see scientists in many institutions collaborating on this important scientific endeavor.
At present, there are various institutions in India which work in different areas of the experiment. At the Tata Institute of Fundamental Research, TIFR in Mumbai, a prototype stack consisting of 1 meter by 1 meter resistive plate chambers, that is RPC, has been developed and is currently recording cosmic muons continuously. The electronics required for the setup is designed and tested by scientists and students. About 30,000 RPCs of size 2 meter by 2 meter will be used in the actual experiment. These RPCs will be finally manufactured by the industry. A special lab has been set up at TIFR for developing and testing large area RPCs and characterizing them. These are done by students of the INO Graduate School as part of their coursework. They are also trained in making these RPCs. Other institutions like the Bhabha Atomic Research Center, BARC, in Mumbai and the Variable Energy Cyclotron Center, VECC, in Kolkata are involved in designing of the magnet for the experiment. Another prototype stack with the magnet is currently in operation at VECC. Apart from electronics and the detector studies, studies are also conducted on gas recirculation systems. The RPCs are filled with a gas, which helps detect particles passing through them by producing an electric signal. Thus, the gas mixture is a crucial component in the detector. The RPCs have gas inlets through which the gas enters the detector and gas outlets through which gas exits the detector. The gas that comes out can be further purified and recycled by an efficient gas recirculation system. At TIFR, various systems are being undertaken. Simulation.
We are going to build 50 kiloton of these detectors, and to build it, we have to be sure that what our physics goal, this detector will satisfy that physics goal. And to know that, we need to do the detector simulations.
Simulation studies are needed to optimize various parameters chosen for the detector. One can get a real feeling of working with the detector itself even before it is built. Simulation studies require a lot of understanding on the theoretical foundations of the subject. The groups at TIFR, HRI, IMSc and SINP are actively involved in this area. Besides these activities, extensive work on detector R&D, physics and simulation studies is being carried out at all the INO collaborating universities and IITs.
The development of human resources forms an important component in the INO project. Since 2008, we have been running the graduate program, which takes a few students every year, and trains them for their PhDs.
We hear about LHC, we hear about many other collaborations in which India is involved, but this is India's own project.
These students will be doing their PhD work on issues that are of great relevance to the INO project.
The challenge for the INO is to build a world-class science laboratory, keeping in mind the ecological and environmental concerns, especially during the construction phase, and to actively participate in ongoing conservation efforts in the region. Scientists recognize that the study of nature's innermost working need not be at loggerheads with nature herself, and have addressed most of the issues related to the impact on the environment by this project. Controlled blasting will be used during the initial phase of the construction of the tunnel. This will minimize sound and thereby prevent noise pollution. Water and power will be sourced from outside with the help of the government without inconveniencing the local people. During the normal operation phase, the laboratory will take every step to ensure environmental safety. Forests or agricultural lands will remain untouched, void of any toxic wastes and effluents, and there is no generation of hazardous radiation. Scientists will make sure that the quality of land and air is well maintained.
So the INO project will benefit the entire nation by enhancing the scientific manpower. There will also be some local benefits in terms of gainful employment, because you will have to source the services towards the maintenance of the INO facility, its laboratory buildings, and also one has to take care of the landscape around the INO laboratory site.
Efforts will also be made to improve the infrastructure and academic standards of the surrounding schools as permitted by governing rules. Exhibitions and other similar facilities will be arranged to enhance the scientific spirit of the local youngsters. The INO collaboration is very keen on scientific outreach possibilities, such as interactions with neighborhood schools and colleges, as well as with physics research and teaching groups from all over India. Small and short-term projects and other activities are envisaged to increase scientific awareness and temper and to involve students from all interested institutions. The INO will also be a catalyst for improvement in living standards in the neighborhood. Training students in these aspects would build up a technologically stronger nation. The detectors used in the INO will also find use in fields such as medical imaging. A project of this kind would strengthen research activities across various disciplines, which in turn would benefit humanity. We at the INO have one goal: to build an institute of world standards at par with the best anywhere across the globe. This will also open up the path to large scientific collaborations within India. We foresee the best minds to be attracted to the INO, further enriching it. The INO will also be a source of a steady stream of highly trained scientific manpower that will make India stand out on the world stage. Simply put, the INO will bring neutrinos to the forefront of science and will enable the advancement of society, physically and scientifically. By the time you breathe once, or you listen to each word in this sentence, a few million particles would have passed through your body and further down through the earth without leaving any trace of their path. All these particles pass through the universe at the speed of light. One of the many types of these particles are called neutrinos, meaning little neutral ones. To get an insight of neutrinos, we need to travel back to the beginning of this universe. Developing our understanding of the universe we live in has taken many years, with many twists and turns in the story. Scientists believe that this universe was created in a powerful explosion called the Big Bang about 14 billion years ago. All the particles, including neutrinos, were produced in that gigantic explosion. There were other interesting particles too, which now pervade the entire universe. We all are always curious to know about our existence. So how could neutrinos help us to understand our origin? To better understand neutrinos, we need to know what the objects around us are made of. All things that we see around us are made of atoms. An atom consists of a nucleus containing neutrons and protons. Electrons go around this nucleus. An electron is an elementary particle. By elementary, we mean that they cannot be divided further. Scientists have discovered that electrons have two cousins, similar in behavior but heavier. They are the muon and the tau. Like the electron, neutrinos too are elementary particles. But unlike the electron, which has a
Developing our understanding of the universe we live in has taken many years with many turns and twists in the story. Scientists believe that this universe was created in a powerful explosion called the Big Bang. And all the matter we see around is a result of that gigantic explosion. Particles which form the atom, like the electron, proton, and neutron, are all products in that process. There were other interesting particles too, which now pervade the entire universe. The photon, which we call as light, and the neutrino. The neutrino has peculiar properties by which we can probe and understand more about the origin of our universe and thus our own existence. The study of neutrinos is an exciting field which will change the face of our country on the science world map. All things that we see around are made of atoms. An atom consists of a nucleus containing the proton and the neutron. Electrons go around the nucleus. Electron is an elementary particle. By elementary, we mean that they cannot be divided anymore. There are two other particles similar to the electron which are slightly massive. They are the muon and the tauon. Like the electron, the neutrino too is an elementary particle. Unlike the electron, which has a negative charge, a neutrino is chargeless. There are three types of neutrinos called electron neutrino, muon neutrino, and tauon neutrino. Neutrinos are denoted by the Greek letter nu. Neutrinos travel almost at the speed of light and it hardly interacts with matter, therefore their detection is extremely difficult. They can even pass through the earth without hindrance. Neutrinos are abundantly found in nature. Many of them were produced during the Big Bang. Sun and similar stars also produce millions of neutrinos every second. Cosmic rays intersect in our atmosphere and produce neutrinos. Most of these neutrinos pass through our body and we do not realize it. Keep your hands open and approximately 12,000 billion of neutrinos will pass through them every second and you never even feel them. Neutrinos can also be made artificially. They are produced in radioactive decays, in nuclear reactors, and in particle accelerators. Neutrinos were initially thought to be massless particles, but recent experiments have discovered that neutrinos change their identity while they travel. For example, an electron neutrino can convert itself into a muon or a tauon neutrino on its flight. This is called neutrino oscillation. But these oscillations can happen only if the neutrinos have mass. The fact that neutrinos have mass has profound implications on the current understanding and the knowledge we have about the universe, and thus in sciences like particle physics, geophysics, astrophysics, cosmology. The discovery of neutrino oscillations is but a first, and there are several questions which may require several experiments spanning many decades to be resolved. The Super Kamiokande Neutrino Observatory in Japan is a huge tank filled with 50,000 tons of pure water. A neutrino interacting with the atoms in water produces a cone of light. The projection of this cone on the walls of the detector is a ring which is detected by photomultiplier tubes. By studying the patterns of these rings, the flavor of the neutrino that produced them can be determined. The 2002 Nobel Prize in Physics was awarded to experiments conducted at this observatory.
Jones, are you there? Good afternoon. We should start in just a couple of minutes. I'm waiting for the speaker. He has some network issue. We'll join very soon. Okay, Jones, you can share now.
Hello, can you hear me?
Yes, yes. Just give me a second.
Can you see my screen?
Yes.
You can still hear me, right?
One minute. One minute. Yeah, what are you saying?
You can hear my voice, right?
Yes. Please put on your video.
Okay, sorry.
Yes, we can see you as well. Yes.
Okay.
Also, wait. Now is your. So, can you please move your slides a bit? No. All right. Fantastic. Okay. So, can we start, Jones?
Okay, we can start.
Okay. So, you can go ahead. I already introduced you, so you can start.
Okay. Today I'll be talking about what benefits INO has for the people, or like what is the use of INO, except for the science part. The science part has been covered so far, like what we are studying, neutrinos and why it's important. So this is about what, other than science, how INO benefits the people. Okay. So there's an overview. So basically, these are the topics. One is the advances in engineering. So we are building a world-class detector, and how it helps in advancing the engineering itself. We are basically pushing the bounds or limits of engineering to better and more finer technologies. Second topic is economic impacts of INO. Third are the spin-offs and like side projects of INO, which in future may help in other technologies for people. And lastly, it's about science education and science outreach. So I'll start. So the best example for what INO does, or like what is the potential of INO and Pottipuram Research Center. It's mini ICAL. I think everyone will be visiting mini ICAL. Correct. So mini ICAL is a particle detector that is completely built in Madurai. It's designed by people all over India, by the different INO collaboration members, different institutes around India. That involves like engineers, professors, students, technicians, contract employees. There are many people who are involved in the construction of this detector. And we have to remember that mini ICAL it's a prototype detector. It's 600 times smaller than the actual ICAL. So if these many people work to make mini ICAL, then for the actual ICAL, it's going to employ a lot of people, not just as an employee, as in a job. It is to train people. For example, like more than 100 students from different colleges worked in the building of mini ICAL. It has been around 3 years that mini ICAL has been operational. And during the construction phase, many students from many colleges around India, and especially from near Madurai. For example, from MKU, Madurai Kamaraj University, Jayaraj Annapakyam College, Perigulam, Kalasalingam University, Virudunagar, M.V.N College, Madurai. So these colleges all participated in building this mini ICAL. And before mini ICAL, there was another stack of RPCs in the A block, which is near this building in the same complex, but in the nearby. So building that, some other colleges also participated, Arivulanandar College, American College, etc. So it's a collaborative effort where like BSc, MSc students, they get exposure to the best experiment technologies, and they get to work on in a world-class experiment. And after that, they go on to like other projects around the world. So many of the students who worked here as MSc or BSc project students or as JRFs, they went on to work in like top experiments in other parts of the world. So this is one key point. Like we are developing the human skilled people with deep knowledge in physics and engineering. Yeah. Okay. I'll move on to the next slide. So, engineering for physics. We are pushing the limits of engineering. So as this first point says, for mini ICAL, there's electronics, there's electrical engineering, mechanical engineering, civil engineering, and computer science programmers. All of them work together to make this project a success. And for this, we have to make a lot of things like in India, in-house. This is something we have to go a long way ahead. And we have already made quite some progress. For example, this board that you see in this left side, this one, I think you can't see my pointer, but the left side, that PCB, that's the DAQ board. DAQ means data acquisition. So it is a data acquisition board. So with every RPC, I'm sure you're all familiar with what RPC is by now. The resistive plate chamber, the particle detector, the M.V.N detector that we are using. At the corner of every RPC, there is this data acquisition board. So this board, it's designed in TIFR, Mumbai, in-house, and it's made in India also. It's fabricated in India also. Yes, but like we are dependent on some parts still on outside India or like other countries, you could say. For example, the black chip that you see in the middle of the detector, not on the middle, on the top left, that black square. So that is the TDC. TDC means time to digital converter. So that in this board, actually, it's a chip that is designed in CERN. So this is one key point about high energy physics, which has been told before also. Most of the things are open source, or to some extent open source, almost free, you could say. The idea is to develop technologies, develop information, and give it for the people so that people can use it for humanity. So this IC, it's designed abroad in CERN. It is called HPTDC. And in India, we are also developing. So that is designed in IIT Madras, and the paper clipping you can see on the right side, a flexible 18-channel multi-heat time to digital converter. So we are designing everything, even silicon ICs. The plan is to design everything in India so that we are self-reliant. We don't have to depend on other people, so that we train our people to have the best technologies in the world. Similarly, the first sub-point in electronics, anusparsh. So that is a low noise, fast discriminator IC. So for those of you who are familiar with electronics, discriminator IC, you could say it's similar to a comparator IC. It is used as an input stage to convert the analog signal into a digital signal, you could say so. So this is designed in BRC. So at the moment, in mini iCal, we are not using anusparsh, but in the iCal, when in future, we'll be using everything designed in-house. Yeah. So at the moment in mini iCal, instead of anusparsh, another chip from CERN is being used called INO, but it will be also changed. So this is the key area. We are developing all the technologies in-house, and that will train the people of India. This is just a little bit more points. The magnet, it was designed in BRC, Mumbai. Today, Professor Datar, he talked a lot about, he showed you pictures of everything. And magnet power supply is designed in VECC, Kolkata. Mechanical and civil engineering is being done in ICHEP Madurai, the campus. So as I said, INO collaboration, it's a very big collaboration. It's over 20 institutes from all around the country. And what it does mainly, you could think of it as a university which is training people in the best technologies around the world, so that science is advanced in our country. Okay. This is the next point. We are making in India, so we have to buy from India, sort of. And we are making in Madurai means we naturally will buy more from nearby, because it's more difficult to buy from farther. So these are just some of the examples. There's actually a lot more. I have a list, but I'm not putting everything here. So just some examples, the glasses and RPC. So as we know in iCal, the detector is RPC, resistive plate chamber. And we need around close to 30,000 RPCs. So in future, for the main iCal, we'll need that. So these RPCs are made in Saint-Gobain factory in Chennai. And here you can see the making of RPC and like testing of the RPCs, if it's up to the mark. The PCBs, printed circuit boards, the electronics, it's made in Arising Electronics. It's designed, some of it is designed in TIFR. It's made in Arising Electronics, Bengaluru. Similar, there's another company, PCB Power in Ahmedabad, where we give prototype PCBs. Gas system, it's also made in India. Chill water in Mumbai. Chill water system, it's made N-Tech Engineer in Bengaluru. Iron, we need a lot of iron. It was sourced for mini iCal, it was sourced from SRC. But for iCal, it's going to be, all of this will be different companies. We cannot predict like who will be buying from, but the key point is that we are purchasing things, we are making a world-class particle detector in India, sourcing materials from India as much as possible. Okay, so just to give an idea like how much of an impact it will be, like the budget is like 15,583 crores. This is an old budget. The budget will be revised because of the delay in the project. Based on the old budget itself, the supplies material cost. So basically, INO Project, Pottipuram Research Center will be buying this much material worth like crores, and the construction, civil, electrical, mechanical, road construction, those will also like hire people, and this is the budget allocated for it. So it will naturally create jobs. And for job creation, the construction contract, it's said in the INO FAQ that the contract will specify that local labor should be used based on the skill levels as much as possible. And this is during the construction itself. After the construction, there will not be that many jobs, not many, but for a small number of people, the second point in the second subpoint, for a small number of people, there will still be jobs in the campus, in the Pottipuram Research Center facility, in upkeep and maintenance of everything. Sorry. Okay. Then apart from this, there will also be naturally development happening because it's such a big project and it's funding 1,500 crores plus, and now with the new budget, it's going to be maybe more than 2,000 crores. So this is naturally going to, the project will require developing the infrastructure facilities, roads, etc. from nearby. And this was a plan from 2015, but you can see what the plans were back in 2015. But none of this happened because the project was delayed. And at the moment, new plans have to be made, will be made. And naturally, along with the Pottipuram Research Center coming up, there will also be infrastructure developments, road developments, and things like that. So this is Kamioka town. This is from Japan. Just look at it. It looks quite beautiful, similar to Pottipuram. The landscape, the natural part is very similar. Kamioka is famous now for Kamioka Observatory, where you must have heard already because there were talks before. It started in 1980s with an experiment called Kamioka Kande. You can see my screen, I hope. Kamioka NDE. So, sorry, Kamioka NDE. So, Kamioka is the name of the town or the village, and NDE stands for Nucleon Decay Experiment. So, this was an experiment started in 1980s. And after that, after this Kamioka Kande detector, it was used for neutrino detection, and it's a Nobel-winning experiment. Then came Super Kamioka Kande, and now they are building Hyper Kamioka Kande. It's the next generation and next generation experiments. So once you have an underground lab, as in Kamioka Observatory, it's going to be there for a while, long time, you could say, decades. And newer and newer experiments, better and better engineering technologies, it will keep coming. It will keep attracting investments, and it will naturally lead to overall development of the place. It's kind of like money is flowing in, and it will lead to employment. It will lead to better technologies and so on. So this is something like we can be like hopeful about. Sorry, that in Pottipuram Research Center, it will lead to a good township, and where there's development, overall development. It's not just a science project, but it's for the development of the area, you could say. Okay, now we move on to the other applications. Like, I know the main purpose is science, neutrino physics, to answer a particular question in neutrino physics, plus there are many other physics. But INO, the technology developed in INO, you are all familiar with RPCs, I believe. So RPCs are rescue plate chambers. So that is basically a muon detector, you could say, or a charged particle detector, rescue plate chambers. So it's a particle detector. So a particle detector can be used for other purposes also. So one of the applications is something called PET scanning. Okay. PET scanning stands for positron emission tomography. I'll briefly say what it is and how the RPCs developed in INO can be used for PET scanning and how it will help. So PET scanning, what is done is the patient is injected with a radioactive molecule, and that molecule will accumulate in parts of the patient's body where there is a particular tumor, for example. And that radioactive molecule will decay. It will emit a positron. Okay, 1 second. Yeah. So it will emit a positron. So there's a initial radioactive atom. It will emit a positron, and it will give off a neutrino, but the neutrino is not important in our case. So that positron is the antiparticle of electron. So that positron will very quickly find some electron nearby, and it will annihilate. And when an electron and a positron comes together and annihilates, there will be 2 photons produced, and those 2 photons will travel in opposite sides. So that's what's shown here. These are the photons, one photon going here, another photon going here. So the idea is that if we can detect these photons, so what we are looking for is 2 photons coming together in opposite directions. Then we can sort of draw a line like this, and by drawing like many lines. So what we do is, like you see in this rat case, around the body of the patient, there will be detectors kept, photon detectors or gamma detectors. So the idea is that if we modify the RPC with some techniques, we can use it as a very good photon detector, not in terms of efficiency, but in terms of actually timing. Why timing? Because if you can measure when the photons came, for example, if the photon came here at time, let's say t1, and here it came at time t2, by looking at the time difference between t1 and t2, we can know from which point along the line the photon came. So the idea is that if we have a good timing resolution detector, we can have better PET scanning, and this RPCs itself cannot be used. But if we make some changes and make something called multi-gap RPCs, then it is a very cheap detector that can be used for PET scanning. So this is something some of my senior students who have already graduated, they have already got their PhDs, have worked on. For example, in the first paper, Design, Development and Performance Study of 6-gap RPCs, this is a paper from 2016, authored by Munmun Devi, M.V.N. Devi, and others. So it studied the performance of this multi-gap RPC. This is not done for INO, or this is not done for INO ICAL experiment. This is done for a side project, hoping that we can make the PET scanning cheaper. There is already PET scanning available. PET scanning detectors are based on other technologies which are more expensive. And the idea is that we can make PET scanning cheaper and more affordable to people. And this work the work in the top side, it's followed up in the bottom by Mohammed Nizam. He is another senior of mine. The first paper tried to make an MRPC. Second paper tried to implement it for PET scanning in a very primitive stage. So we need more research in this field. We need more students working on this topic so that it can be realized into a final product. On the right hand side, actually, here you can see this is a schematic of MRPC. So you are all familiar with RPCs, I believe. In RPC, you basically just have 2 glasses, right, like this. Okay, the key idea is that this gap between the 2 glasses, it's millimeters, right? Forgot exactly how many. It's a couple of millimeters. So if the gap is more, the timing resolution will be poorer. So what is done in multi-gap RPCs is that instead of having one gap, it is divided into many gaps, as you can see in the above picture. And that will help in giving us smaller time resolution. So this modification is done hopefully for medical technologies such as PET scan. Okay, so moving on to another possible application, there's something called muon tomography. So the idea is that we have naturally occurring muons coming through all of us all the time. So these naturally occurring muons, it can be used to study the interior of objects. So this is already done in 2017, not by INO, by some other group. So what they did was they found a they scanned pyramids in Egypt, I think. They scanned it and they found a new void, sort of a hole in the pyramid, which was not known before. So what is done basically is you just need to keep a muon detector. And we have a muon detector, right? We have mini ICAL, which is a really good muon detector. Yeah, so basically we need a muon detector and we need to keep it at different places around the pyramid, let's say. And by looking at the flux of muons and comparing it, we can sort of scan objects. So this is a useful technology. This is also, the research is also done for scanning trucks and for like security reasons. For example, in shipping ports, when a shipment comes and there's a big shipment, to see if there is dense, heavy materials, or if there's, for example, to carry nuclear materials, and if it is shielded by lead, which is dense. So we can scan for dense materials like density, and for that we can use. So muon tomography is a very, very useful future field where directly whatever technology is made for INO, which is basically RPCs. And the advantage of RPC that INO has developed is that it is relatively cheap. For a particle detector, RPCs are relatively cheap. So this is useful technology for like commercial uses. So in INO, I don't think anyone has worked on muon tomography yet, but accidentally, one of my seniors, Dr. Peturaj, he was trying to estimate the flux of muons in Madurai. So this is the Vadapalanji ICHEP campus. Okay, so in this building over here, there was a stack of RPCs. I forgot how many layers there were. 10 or 12 layers of RPCs.
12 layers.
12.
Yeah.
Okay. So there were 12 layers of RPCs. You could think of it like this: 12 layers of RPCs. And basically, what it is doing is it is looking for muons. So muons are coming from all the sides. It's coming from here. It's coming from here. It's coming from here. It's coming from all the sides. And the objective was just to measure the number of muons and to see if it is what is expected. But unexpectedly, what happened was, from this direction, the number of muons did not match what was happening. So after a long time, he realized that it is actually because the muons that are coming from here, those muons are going through this building. This building in the neighborhood that was unintentionally scanned by the muons because of the stack of RPC detectors kept in this this building. So the idea is that this is a very, very feasible idea, but we need more people working on it. And this is going to be a technology in future. Okay, so I'm moving on. So this is just a general point. ICHEP is an institute, Inter-Institutional Center for High Energy Physics. It is the institute that is going to come in Madurai. Now there is a transit campus that you saw here. This is a transit campus of ICHEP, but nearby, just like maybe a few kilometers nearby, there's an actual campus where ICHEP is going to come. And ICHEP, once it comes, it's going to be a top institute in high energy physics, and that is going to be in Tamil Nadu, and it is going to naturally attract the best scientists in the world. It's like having the best institute, one of the best institutes in the world near your home. Just to compare, this slide you may have seen before. This is Dr. Abdul Salam, Nobel laureate, Pakistani scientist. He is visiting the Kola Goldfield lab back, I don't know which year, 1970s, 80s maybe.
81, I think.
1981. Okay. So this is the kind of environment, this is the kind of attraction that ICHEP and Pottipuram Research Center will bring to Madurai Theni region. We are expecting the best people, best scientists in the world to come here, and that will spark the knowledge, the young minds in the locality. And naturally, it's sort of a ripple effect. We cannot predict, like, we cannot quantify how much it will affect, but it is going to be a big thing. This is the biggest point of INO and Pottipuram Research Center and ICHEP. So INO has also had this INO graduate training program. So it's a PhD program, and I'm a student in this program. So already 31 students have graduated, and they are all working in top experiments around the world. There are many neutrino experiments around the world. There are several upcoming neutrino experiments as well, and existing ones. So there are people working in these experiments, as well as other experiments like dark matter detection and so on. So these students are now working there. Some of them are professors in India also. And I know GTP, there have been good representation from women also. So that's also something I know is proud of. So another thing is science outreach. This is something in this ICHEP campus, transit campus itself, I know people have been doing. So this is a recent visit, this from this year. There have been many visits, but due to this COVID, the number of visits have been reduced. This was a visit due in Feb 2021. It was a time before the second wave hit. And after that, again, we could not have more students. There are other science outreach activities such as this solar eclipse 2019. So these people came to visit. So I was not there. The glasses were provided and they had a very good time. And these are the photos from the solar eclipse taken from Madurai, from ICHEP campus. Okay, this is a point that is from very old times. This slide is from a presentation made by district collector in 2010. So that time this was proposed, and I came to know about this only a few days back, yesterday I think, that a modern science park as part of this INO. But at the moment I'm not hearing about this, but this is something that could be thought of, where we can have the best experiments that people can understand. Everybody can understand what science is, how simple or how elegant science is. So I hope that this proposed science park, back then even the site was like shortlisted. It was on paper, but sadly the project got delayed and everything, all the development that should have come along with the project also got delayed. So yeah, this is one more thing that we can look forward to. That's it. Thank you.
Thanks very much, Jones. You really touched upon many interesting areas, and I'm sure there will be, I think, nice interaction that would happen. So this is again another good opportunity for participants to interact with the speaker, who is unlike so many that you heard before. And in this particular campaign, here is a young speaker of more of your age. So you can have a maybe more one-on-one interaction. The questions meeting. So go ahead, please.
Shotto, and just before the question, I have just to add 2 points.
Yeah, please.
Okay. So, young students, you have heard this Kamiokande. In 1980s, Kamiokande that place was almost looks like what is now Pottipuram. It is a small village. Nobody knew that place. And at that time, this Kamiokande experiment and Professor Datar yesterday mentioned that Kolar Goldfield experiment. These two experiments were in competition. Every conference, when there is a conference, people used to see who are these better result presented by this Kamiokande or Kolar Goldfield. So it was that competitive environment we had, and they have the strong support from the local people and government, and they can go ahead. This Kamiokande, they received 2 Nobel Prize after that. So just keep in mind, this is how the local support or government support can flourish the scientific community. Somehow we could not match with that. Some Kolar Goldfield has to close, we have to stop our project. And okay, so this is one point. And second point, as Jones mentioned about this, those two students paper about the multi-cap RPC. One of them now in this professor in the Tezpur University, this Munmun Devi. Another one is, the Nizam. He is in the postdoc working in the California now. So this is this way we train the student. This is not for this only INO. This is for this well-trained student, and they are recognized all over the world, and they got these prestigious positions in different places. Yeah, this is a few example. And also this at the end, what he showed this many students, almost all are in some of these prestigious European institute or Indian institute they are working. Last two are the present student, and previous two just finished and they are yet to go abroad, but all remaining are went abroad, or some of them come back as a prestigious position in the institute and different institute in the India. Yeah, just that's the point I want to mention.
Okay, thanks, Professor Govinda. I think that was very nice insight to also bring the Kolar Goldfields and Kamioka together, and that is also an historical perspective. Yeah, so more questions to Jones?
I think it was not a technical talk. Okay, there is a question.
So here is the question, Jones. Can you see the? Yeah,
yes,
I
yes.
can. Okay, please go ahead.
What were the biggest challenges in doing the work? To be frank, I was not much part of mini ICAL development. So is Krishnamurthy here? Actually,
He is right now explaining the lab project to the students today. There are on campus, there are students, no, today. So he is explaining to them.
Okay, so I joined here in 2018. Okay, so when I joined, I just went to Madurai just to see what is going on. So that was around the time this mini ICAL was developed. But after that, I came to Mumbai, and then I was doing my coursework. Then I started my research work here. Then again last year I went there for a short while. So I'm not the best person to say what is the biggest challenges. There are a lot of other people who work, but they are also busy. There is Krishnamurthy, then there is Peturaj, Dr. Peturaj, Suryanarayan Mandal. So those people, sadly, they are not here at the moment. But I think there were issues like the iron bent because of the magnetic field. Actually, Satya sir, maybe you could say.
No, I think it is the question is not.
Transport.
Maybe you
It
can
was
ask.
due to the transportation, not this magnetic field.
Oh, okay.
No, another thing, iron magnet. Okay, that's the different things. When the iron was put, 7 pieces of iron were put in the and magnetized. So magnetic force, they push them. So because of this, there was some aluminum plate put on that each to smooth transfer of these our RPC tray. This aluminum was stuck on this iron, and because of the iron was shrink, aluminum was bump up, and that was create a problem. And actually that time one option was that remove all of the remove assembly, completely remove and do reassemble again. But again, this is the one of you, this one student, he has an idea how to overcome that problem. Suryanarayana, he conceptualized, he built the instrument and he solved the problem. Yeah,
yes.
Satya, you want to add?
I was just saying, I'm not sure what is the question is in terms of engineering challenges, or was it a question as a student of INO, what are the challenges in that people want to share? Maybe if Ajit Mohammed could also clarify a little bit, is this question about building the detector, or is the question of the students working in research labs? Or that will be nice, because sometimes people want to know a student perspective of working on large scale experiments.
So, okay, from a student working in this project, for my case, okay, I have challenges means in theory, things are straightforward. Like you connect, let's say I actually come from electronics engineering background. From a theory perspective, it's kind of straightforward. You just take an amplifier, you connect the input and output, you should get the output. But practically what happens is that there will be a lot of effects. And we need to sort of sit down and look at like every small thing may affect. For example, in this mini ICAL, if we mini ICAL, this data communication, there are wires. You'll see many wires connecting, like from one point to another point. For example, from the DAQ to the backside trigger board. So if the cable is not shielded properly, or if it's if it crosses some other cable, for example, it may couple noise, like noise from one line will come to the other line, and those kind of things, because it's a complicated system. It is a simple system overall, but because there are many parts here and there, everything has to be carefully designed, and sometimes it is difficult to troubleshoot. You will think that I'm doing every connections correctly, but why is the output coming garbage? But then you'll have to sit down and slowly troubleshoot everything step by step to see what is the what was the problem. So that is the real sort of engineering / research part in this.
Okay, I think this is, I just add something already in the chat. Sutran had put something, work with their hand. And okay, this is, you keep in mind my experience till my MSc, what are the electronics I learned, what is this fluid dynamics or mechanics I learned, and nothing can be directly implemented when you go to the real life experiment. And that is this, I think if you come, that will be your some kind of first shock that, oh, I read this simple amplifier circuit, okay, this simple PNP and this work. But when in the real amplifier, too many components has to add to check up many things. So those are the real, I will not say challenge, but those are a real surprise, and someone liked it and they move forward with that. So that was this. Initially, you may feel that, okay, I cannot understand, but that's the reality, and that's the challenge students are taking, and they gain the experience and they develop the things from there. Yeah.
Any other questions?
Okay.
Yeah. Is there a question, please? Okay. The question says, okay, sir, I understood it. Are there any more questions from students? This is the best chance to ask a student as a student. Is there any special opportunity in research for TENI students? Jones, you want to start, or Professor Govinda
No,
can?
I think Govinda sir should be answering that, right?
Okay. So any special, okay, yesterday in my talk, I mentioned that we have a summer program or short-term program, and certainly we like some of you come and learn the things. And again, I mentioned that this is not for you, this is actually for us. We know that if the experiment will come up, then someone has to run, and this is, we are going to train you such that in future you can run this experiment. So certainly most of the TENI or the Madurai people at present, we do not have anything in the TENI. So you have to come at our ICHEP campus to do some project. Or actually in the last few months, I visited many colleges in TENI and discussed with you people. That will certainly will continue. And also we are having some more than that, that is some call this, some experimental setup. We are trying to collaborate with these different college and the university, where we can set up few of these experiment where you will do in your BSc or MSc experimental project. So that's anyhow, irrespective of anything we will do. But you can ask us, and short-term visit, we may help you to come to our IGF and do the short-term project at Madurai at this moment. But certainly when in future IGF will come up, that time we'll have many, many more opportunity. You people to come for a short or long time project or work, or even, okay, that is it is a competition all over the India. You have to take this competition, and if you selected, then you can work like a PhD student, what Jones is talking, or this Pithu Moon like those people.
I think naturally, like, project students will be coming more from nearby because they can travel. So
Visiting the lab, this is mainly from this, we are trying to give the more opportunity to the local people, basically Theni, Madurai, and the nearby districts.
Yeah. So there is Jones, you want to answer, or maybe there's one question, maybe
yeah,
no.
so actually, I think Govinda sir, again, it's better he answers. Maybe what was the device used to overcome the iron problem?
Oh, this is the, so basically in the iron, we put on the top of the iron, we put a thin layer of aluminium. Such that iron, maybe there are 2 or 3 layers of iron, there might be little bit mismatch. So when we push the RPC tray, next week or tomorrow when you visit the lab, you will see there should not be any problem. So the screw was used to put this aluminum tray to the iron. So now the gap is only 4 centimeters in between 2 iron. And the screw is roughly about 2 meters inside. And screw is this thread screw. How to use the screwdriver there to remove the screw? So he made this small device where he used the simple, let's say, camera, mobile. This mobile camera was used just to see when you put your small head screwdriver to anti-rotate the screw to take out. He put a camera and this lever arm and also the rotational system by which he rotated these things and the screw has come out. I think Surya would have been there. He could explain it much better way.
Jones, if you unshare, I can show.
Yeah. Okay.
I want to share.
Yeah.
Okay. I hope you can see this.
Yes.
Okay. So what Professor Govinda was mentioning, let me see if I can try to recapitulate that. Here, for example, on the top, I hope you can see the cursor. So this is one layer of iron, which is 56 millimeter thick. This is another layer of iron, which is also, of course, 56 millimeters. And this gap that you find is roughly 45 millimeters between these two. If you look at this, if you go to, as you see my cursor, you find you will find this kind of aluminum sheet, which is sort of bent upwards. You can see this. This is supposed to be plain. It is supposed to be kind of stuck to the bottom plate, so that when you push a tray with the complementary cross section of this this aluminum plate, it is supposed to kind of slide the way a train moves on a rack and so on, or maybe a drawer, you pull or push from your table. But unfortunately, due to what, okay, let us not go into details, but this particular piece has come out. Now, how do you, unless you pull this plate out, or as Professor Govinda said, you have to probably dismantle the whole detector. And by that time, unfortunately or fortunately, the entire thing is kind of done already, kind of built. So what, and also remember, he said that this, from this white mark to all the way towards you from the screen is 4 meters, right? It's 4 meters, and this bend can happen anywhere in between. So how do you access it? You can't access 45 millimeters. right? And also the any inside. So what the INO student, Suryanarayan Mondal, here you can actually see this plate went well. By the way, taking these pictures itself is an innovation, right? Because you kind of tie up a small pinhole camera into mobile camera into the cap and then take it inside and get these very high quality picture. That is what made you understand. Now you can see this much better. Okay, so what he did is, this is 21 millimeters height object. This is 8.5 millimeter object. So to just give you the scale, obviously you have to find this a screw which is matching to the screws that were helped to attach the aluminum sheet to the iron plate. And what is also important is this one should be with a ratchet, in the sense I can move clockwise or anti-clockwise, it should be able to loosen or tighten, right? I mean, you know, you have seen these spanners that people use. Okay, so you first use that light and camera, align this particular spanner to each of those things, and he was effortlessly able to pull each of those bad ones and pull this in. I mean, this is how what I typed somewhere. Here you can kind of see what I was trying to say, that here in high energy physics, here INO-like experiments, the students actually not only come with a physics problem, they build their instruments, they collect the data, they analyze the data, and then, they pick up the results and so on. That's why quite often you'll find the high energy physics students not only excel in doing physics elsewhere, but they're also doing exceedingly well these days, especially on the areas where there is a good strategic connection between, or a good synergy between, let us say, technology and science, and they go ahead and join companies which actually are not so much to do with high energy physics, but their skills are extremely useful because of such nice ideas of converting ideas into implementation. Now, of course, not everyone probably will be of this of the same type, but different people have different I would say interest and so on. But anyway, so that is what Jones and Professor Majumdar was mentioning about the capabilities of our students.
So there are a couple more questions now.
Yeah, these are actually very interesting questions. Jones, be talking about. Okay, you go ahead. Maybe then others can.
Okay. The last questions that I saw is, can we get a bit more information about graduate training program? So graduate training program at the moment, I think it's not taking new students. So earlier, how we got selected, for example, I got selected, it was through the TIFR GS exam. And after that, there will be an interview.
They don't know GS and all. Please be a little bit.
Okay, so there are some exams that generally after BSc or MSc, they write for admission for integrated PhD or PhD. I think the main exams that I wrote was, one is TIFR GS exam. GS is graduate school.
It is a graduate school, and this exam, written exam, in general, it happened second Sunday of December. And the student means when the students are in this second year of MSc or third year of BSc, that year, second Sunday of December, this written test. And interview used to happen in March, February or March sometimes. But this course, the class set, everything started in August. Okay, Jones, continue.
So one exam to write is TIFR. One exam to write is TIFR GS exam. They take students to TIFR, basically. TIFR in Mumbai. So TIFR is one of the collaboration institutes, and Professor Govinda Majumdar is a professor in TIFR. So one exam to write is TIFR GS, and INO GTP students were actually taken, I think, only from TIFR GS exam, but there was a checkbox where we have to check that you also want to be considered for INO GTP program. But this year and next year, I think INO is not taking new students. So another exam to write, this is not in context of INO, is just JESP. It's also for PhD admissions. I think 1 year I know students, I know GTP took from just also. I'm not sure. So these two are the exams that come to my mind.
So far we are not taken, but yeah, it is.
Okay. Yes. Where to apply qualifications? Such all information about INO. All information about INO, it will be there in INO website. About application, everything. But at the moment, like INO GTP students are not being.
GTP student are not being taken, and last
So,
1.5 year we have not taken the summer student also because of COVID. Not much summer student last 2 years.
Are there any more questions? I thought
there's a question to Satya sir.
So Jones, here it is if you want to.
I'll read it.
Oh, you want to?
There's a question written specifically to Satya sir.
Okay, no, before that, since you mentioned about the GTP, so and you said about INO webpage, so I just put it up so you can kind of point to that. Okay. So it is on the INO webpage. If you go to graduate training program, all the information about the program is given there. Okay, so the web page is for you. Probably I will just put it on the chat window. Okay, yeah. What does it say then? Question to the, okay. For compromising the local people of any Madurai district, is there any other job preference given to them who have scientific knowledge on neutrino research? If the preference is permissible, Madurai and Theni become popular towns for doing this project all around India. In future, after 25 years, most of the students of Madurai Theni will become scientists in the project. Okay, so this is a very nice question again asked by Ajit Mohammed. So I want to answer probably Professor Govinda Majumdar, director. He might also.
Yeah. So, okay, I will just give this some indirectly the answer. Let's see. Jones has mentioned roughly more than 150 students participated in some form in the building of our IHF mini ICL detectors. And more than 80% of the students are from either from Theni or Madurai. So this is the short-term project what we are taking. We are taking mainly from these local people. That is, we are giving some preference to the local people. But on the other hand, if you go for this graduate training program, still now we did not give any specific preference. Let's say Pithuras and some other MKU student who join in the INO graduate program, they come through the standard channel, standard path. So certainly for the short-term visit or short-term, this is the, so let's say, a summer program, or now most of the college has a MSc second year in experimental project program. For all those cases, certainly we will give more preference to the student in Theni, Madurai, or the and surrounding districts. Yeah. So that's the answer I can give. Do you want any more specific things? Job preference. Okay, now on the other thing, is there any other job preference given to them? Okay, job, if you come to the job point of view, this is this, any government job, you have to follow some government protocol. And there I cannot officially say anything that I will prefer some particular people. But certainly, for example, if the Madurai center now, for example, in this our IHF campus, when you go tomorrow and day after, we have some technicians, we have some, for example, completely different way, the lab guard. We did not mention that they has to be from this Tamil Nadu or local people. but all those people are from the local. So we are not saying that we will give the preference, but for those kind of work by default, usually the local people is this. We see this in general, most of the time local people will come. So though officially we are not saying that we are giving them the preference, but that is this happening eventually. So here, so on that point, I'm saying for job matters, we are not officially making any comment that we will give the preference, but our experience, what we see, this kind of job, usually it comes from the local people. Okay.
So yeah, so thanks for that. And any more questions to Jones, or any other general questions that you want to ask? Okay, I don't see any more questions, any more raised hands. So maybe it is time to thank Jones Panicker. He really brought out a new perspective to this program, because he brought in issues which are probably not many of them are covered in the earlier. And also with his youthfulness, he also brought something close connection to most of you who are on the call today. So let us thank him. And now it is 3 o'clock on dot. So we will take a 15-minute break, and then we'll come back at 3:15 to the last session of the second campaign. So in which you will hear first from, TVV, T. Venkateswaran, a very popular figure, and then followed by the panel discussion. Thank you.
आता हे करा एक मिनिट हळू लूज करा बस मध्ये हां ले लो आता हे दुसरी राइट हैंड साइड में सब लूज होए के देखिए लूज होए खाली दाबून धरा हां दाबून धरा घुमाओ नहीं मालूम सलीम जी घुमाओ हां चल वर्किंग है थांबा इथे करता हूं नहीं इधर हे हां वेरी गुड
हां मग ते
हे लावू
90 डिग्री घ्या अगोदर नंतर घ्या रेंज करता पाहिजे
हे तिकडे थोडं डकवा हां इकडे विशाल तू तिथेच ना तिकडे बघा अलाइनमेंट होतं म्हणजे हे एकदम एजला केलंय म्हणजे तुम्ही याला
नाही ना सोडायला लागणार आहे बटन प्रेस करते
हो आपण अलाइनमेंट Lead blocks. ठीक है.
कसा इकडून
हाँ ये करो वो प्रेस करना है ना प्रेस कर
fact that we stack of things like that, and then we move to the back side. There also, of course, in the Middle wall, who is expert on this?
See, we'll just show a scratch it, then.
TVV, are you there?
I'm there. I'm there.
Hi. Do you want to?
1 second. Just 1 second. Somebody is calling.
Okay. Okay.
Yeah. Sorry. We have some more time.
Yeah. Is it okay to start now?
We can. Huh?
Yes. Yes. Let
yeah.
me.
Okay. Then I'm through. Just give me 2 minutes. I'll just organize my thing. Here, second, and then I'll.
Okay.
Yeah. Sure. Just. Yeah, I think we can start. Sorry for that small delay.
No problem. Just okay. Yeah, so we can share your slides.
Yeah, can I share my slides?
Yes.
Is it visible?
Yes, very much.
I will also just check. Is it changing? Yeah.
Yeah, changing the slides.
Yeah, good. Just a second. Sorry. I mean, people are just ringing the bell at this moment. Sorry. Yeah, we can start. Shall I begin?
Yes. There is a small message right on top of your screen. You can close that and then reopen, close.
Yeah. Right now?
Yes, now perfect.
Yeah, good. Okay.
All set.
So, friends, very happy to meet you in this program. My name is TV Venkateswaran. You can see it on the screen. I'm working with Vigyan Prasar, organization under the Department of Science and Technology. So what I propose to do is look at one question that most of us would have felt one time or other. How gullible people are. Okay, how people fall for what to many of us would look like silly arguments, right? So let's look at this deeply in relation with India-based neutrino project. Let's look at, for example, some of the fears and rumors related to India-based India-based neutrino project that's circulating in Tamil Nadu. I have not listed everything, I've selected few and then I've put them here. One is, there is a people who talk about if you are going to drill 1 kilometer tunnel, lot of dust will come. That dust will envelop the village nearby. There'll be so much of noise. So many trucks will come and clear this material. So which means that there'll be road accidents, traffic, this kind of one fear. The other fear that is commonly talked about with regard to INO is that the explosives that we use for constructing the tunnel would damage the dams, particularly the Mullaperiyar Dam, which is a very emotive issue in that region. Then there are fears related to land acquisition, whether people will be removed for 1 kilometer like it happens in nuclear power plants and so on. Then there are questions like you are going to say that you are going to put world's largest magnet here. What does it mean? Would it mean that sickle from my home, agricultural implement, will be attracted by your largest magnet? Some of you, if you have seen this movie called Yendran or Robo, it came in Hindi with the Rajinikanth starrer movie, Rajinikanth and Aishwarya Rai. So there, the Chitti, the Robo, suddenly gets electromagnetism, and then sickle, knife, and anything that is iron kinds of is attracted. Would something like that happen? When I say like this, you might be laughing in your mind. Yeah, but it is a question that people are asking. Then there are people who say that natural neutrinos are okay. When you say that, okay, neutrinos are everywhere, it's coming in atmosphere, it is in sun, okay. But then there are something called neutrino factory where you are going to produce artificial neutrinos. Are they going to be dangerous? Like natural chemicals are okay, but artificial chemicals are bad. Even you and I would talk like that, right? Yeah, so okay. Then there are this conspiracy theory that it's a bomb making project. It's associated with Fermilab. So it is some kind of a secret research. Then there are questions related to what can be called as watchdog functions, like are the rules being followed? Is the site within the tiger reserve? These are all some of the sample questions, typologies, if I can say so. Okay. So let's, when we see this kind of problems around, we think of communicating science. And whenever we think of communicating science, we think that the technical words are the key problem. People don't understand science because science is full of technical words, and that is the key problem. Really, science uses esoteric jargons. We all know it, right? I mean, of course, this is a humor, but a simple word like replication has a very, very specific meaning within genetics, right? Replication, transcription, translation have a very, very specific meaning within science. Everyday language, it means something different. Though you can find some connection, it's not same, right? So science uses technical words in a very precise manner. But is that really the problem? Look at cricket, the kind of technical word we use: bumper, bowled, no ball. What do you mean by no ball? Does it mean that there is no ball, or the ball just vanished? That's what plain English will mean, no? But that is not what is the meaning in cricket, and none of us are bothered too much because of that. We are accustomed to it, of course, because we hear about it, number one. And when people explain, first time you didn't know cricket, of course, you also don't know what no ball means, right? But once it is explained, it is not bothering you too much. You understand that in cricket, this is what it means, and that's how I should use it. There is no big deal, right? It's not only about cricket. For example, cooking. If you are going to mix some liquid and some flour, I mean, if any of you are interested in cooking, I am, okay? There are at least 4 different words which we use. Whipping, which is very different from cutting and folding, which is different from folding, and which is different from kneading. All are different. But in all cases, you are using one liquid and another let's say solid but powdery solid, and you are mixing it in making some kind of a semi-liquid or non-Newtonian liquid or whatever, right? But then there are 4 processes, and there are keyword technical words we use in cake making, baking, cooking, so many other things area. I mean, sorting, frying, shallow frying, blending, grinding. I mean, so many technical words we use in cooking, and nobody says that cooking is difficult because of the technical word. No, right? So technical words are not the big issues. So don't think technical words are big issues. Basically, if you can't explain simply, then you have not understood. If you have understood, technical words are not going to be the real challenge in communicating what we want to communicate. Let's look at another question called accuracy. We are all worried that if I tell to ordinary public in one particular way, will I be inaccurate? You look at any school textbook, elementary school textbook. I'm sure in second standard or third standard, there'll be a chapter on sun, earth and planets. And then it will be written that earth is going around sun. Earth is going around sun, or earth is orbiting sun. Usually we use a very simple plain English language. So earth is going around sun. That's what would be there. Which is to kind of contradict from our everyday experience of sun is going around the earth. Okay, so sometimes in the book you explicitly mention sun is not going around the earth. It appears to be so. It is actually earth which is going around the sun. You mention it. Okay. The way you mention it, the way you explain it is different, but you do mention it. Is it accurate? Is it not that sun and earth are going around their Berry center or common center of gravity? Physics, simple physics, right? If there are 2 objects with masses, they should be going around the common center of gravity. Okay, it's a different matter that when you are looking at earth and sun, the common center of gravity is very, very close to the center of sun. That's a different matter. So which also essentially means that the sun will wobble around that common center of gravity. But accurate, if you want to be accurate, should we not say that it goes around barycenter of sun and the earth? If it is Jupiter, the barycenter is outside the sun. But do we say that in our elementary school? So do we really say that then we are teaching bad science in elementary school? No, we understand that learning always involves learning and unlearning. Okay, you learn at one level of, let's say, approximation, and then you add some more layer and understand it better, go deeper. That's we understand. But is that the only way? I mean, if you are, I mean, most of you should be from physics. That's how this project, I mean, this workshop has been arranged. So we all know about the space-time curvature. So this whole talk about Earth going around sun is false. Earth is just, after all, going in a straight line. It's only that the space is curved. That's it, right? So are we going to introduce this in the elementary school, saying that we will have to teach accurate science? No. We do understand that in elementary school, we will go with the statement that the earth goes around the sun. Somewhere around middle school, high school, we will introduce this idea of barycenter, and then if necessary, clarify that part. And maybe a higher secondary, we will introduce space-time, and then do learning and unlearning constantly, right? I mean, more better picture of the world around us. That's what we do, right? So accuracy is a matter of context. Okay, the context of your audience, what level they already know. Okay, you are not telling lie, you are not telling false. Okay, you are not telling earth is flat, which will be false. If you are telling earth is spherical, you are not absolutely correct, but you are not false, you are not fake, right? Earth is not a perfect sphere, right? Yeah, so there is a big difference between these two. Earth is spherical is approximately true, right? So we go with approximately what is true. So accuracy is not also the big challenge in communicating science or people understanding science. That's not the big issue. Okay. So as Einstein says, everything should be made as simple as possible, but not simpler. That should be kept in mind. We should not be making it simpler, but of course, certainly simple, right? So that's a important point to note. Let's go forward. Then what are the real challenges? I rejected two most common believed challenges of science communication: technical words and accuracy. Both are not important challenges. They may pose little bit of challenge, but they are not big challenge. They are not the deep challenge. They are not the main challenge. Then what are the crucial challenges? The crucial challenges are 5 aspects of the nature of science. What are those 5 aspects? Number 1, the world of science talks about new reality domain. I'm going to explain them, all of them. So let's go with it. It explains new reality domain. Second, a large part of science is counterintuitive. Third, in the world of science, there is a world of abstractness and the world of concreteness, and we constantly shuttle between these two. Suddenly we talk abstract, suddenly we talk concrete. Then again we move to abstract, then move to concrete. There is a shift between these two. And fourth, many things that we talk about in the world of science, particularly in the modern science, are incongruous. And last, but certainly not the least, very importantly, certainly not the least, is the organized skepticism of science. This is something that terribly upsets people. In fact, many times it even upsets us. Forget about people. Okay, you get a paper with the comments, we are upset. But after all, that is part of the organized skepticism. The first thing that we think when we get a paper with the comments is that what the hell, what the heck, what does he know, right? But it's part of the organized skepticism. So we are also not immune to it. Okay, so these are the 5 key challenges. Let me explain what each of them are. Let's look at, for example, entities that we talk in science. Entities like, say, for example, metal and non-metal, noble gases. Sure, we do encounter them in all our everyday life. Yeah, you do encounter, let's say, a stainless steel vessel and perhaps a mud pot. Okay, maybe in a mud pot you have water and a stainless steel vessel in which you cook your dishes. But in our everyday life, we classify them as vessels. We look at them together as one, vessels. We are not distinguish them based on what is it made up of. Okay, so in our conscious, articulate consciousness, we don't look at them as metals and non-metals. We look at them as vessels. In comparison to, for example, let's say a hammer, which may be also a metal, right? Or a hammerhead, which is a metal, right? So in science, we look at entities which are new. For example, neutrino is not something that we consciously encounter in our everyday life, right? So there are new entities. There are also new processes as part of the new reality domain that we encounter. Of course, we all know transport, right? I mean, we move from place to place, we move from one room to another room, we take one material from one place to another place. So transport is known. But the kind of transport that we are talking about, for example, in science, like how material transfer through a cellular wall inside the cell, passive transport, active transport, within that various processes like diffusion, blah, 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 again, are not processes that we see in our everyday life. So is, for example, fossilization. Fossilization is not something that we experience or encounter, right? So there is a new reality. It's not a reality that we know by simply living. Okay, by simply living, we know we have certain experience, but these things go beyond that. Okay. Then justification, the way we justify things. For example, you have a ball and a feather and you leave them together. Okay. In normal life, you will say that, oh, ball will fall faster and weather will come slower. Oh, because heavier stuff will fall faster, lighter stuff will take time to fall off. That's how we will give explanation. That's how we will justify the act that we are seeing. But is that the way we do it in physics? No. The physics, we say something completely different, right? physics, we say that, oh, actually both of them should be falling at the same rate. The ball is falling, but the feather is being obstructed by air. So that is why it is delayed, right? So the justification that we give in physics science is different from our everyday explanation to things around us. Yeah. So in all three, whether it is entity, whether it is a process, or whether it is the way we justify or explain a thing. Justify here, I mean that explain a thing, okay? Or new, they are new realities, right? So this is one key challenge. Various entities like atoms, processes like DNA code, justification like why we are not explaining why the ball is moving. Newton first law, it should be moving or at the state of rest, which is also a kind of moving. But we are talking about stopping. When something is moving, why does it stop? There should be a force opposite to it, friction, blah, blah, blah. In everyday life, we know that the ball will stop. So we are not explaining that the ball will stop. We'll say, oh, it will stop after some time. Okay. Only when you are moving that you are giving a explanation that why it moves. Okay. So there is a unsymmetry between our everyday life experience and the new reality domain depicted by science. So this is a key challenge. This two different worlds, our everyday life world and the world of science, the divergence is a key important part. The second important part is the counterintuitive nature of science. Again, physics, so I won't explain too much on this. I presume that you will know the double slit experiment and things of that kind. Our everyday experience would expect us to see when you are using a double slit experiment, two lines, okay? But we know that what we have is because of the quantum effect, multiple lines. That is because it behaves both as particle and wave, which is very, very counterintuitive. You know, something that we don't really see from our everyday experience. How can something be same time particle and wave? You know, it's not something that we can easily resolve. Okay, many times we just put it away. We don't work it. We say that okay, forget it. I'll use the let's say Heisenberg equation, and then I'll just solve. Finish. Okay, I don't even think consciously that how is that a particle and wave are explained. Okay, sometimes I don't even want to bring them together. So there is a very deep counterintuitiveness to science. Okay. Same way, for example, evolution. Evolution is not very easy for us to understand and accept. There was a philosopher called William Paley, who lived around the 1850s. That is the time of Darwin. So when Darwin proposed a theory of evolution, Paley had a counter argument. What is that counter argument? Paley said that imagine that you are going to an uninhabited island. Okay, an island where no human being have ever gone. You see a rock. You will say that, oh, this rock might have fallen off a cliff, or maybe there always. No problem in explaining it. You don't find any surprise or mental trauma. But suppose you find a watch. I mean, wristwatch that we wear, right? The wristwatch. Okay, pocket watch, timekeeping watch. On the shores of that uninhabited island, can you say that, oh, this watch was there like a rock for always? Or can you say that like the rock fell down, I mean, this watch kind of formed on its own? No, you would say that maybe somebody had come, maybe that fellow accidentally left it here, or maybe that fellow died, and then this watch is remaining here. Something like that, you will bring in a human being, intelligence, right? So from this, the William Paley argued that if you see, for example, a complex organism like eye is a very complex organism. You know, there are multiple layers, there is a lens, there is something to wipe it constantly so that dust doesn't fall on it. So many, I mean, anyone who would have studied the structure of eye would know, even a summary structure that we study in high school, we know it's a very complex structure. So William Paley said that how could it evolve? But then we know now that I has evolved. And if you want to know more about it, because this is not the lecture for it, please read the Climbing Mount Insurmountable by Richard Dawkins, okay, where he talks specifically about evolution of I, which was given as a big challenge for evolution to explain that how actually evolution has taken place. We now have fossil evidence. We now have various kinds of evidences from which we can patch how the evolution of I took place. Today we have that knowledge, but it's not very simple. It's very, very counterintuitive. Okay, yeah. Then abstract and concrete. Okay, so when we talk about, let's say, a feather and a hammer falling, in abstract, we would say that both of them should fall at the same rate, but in concrete, they won't fall at the same rate. Okay, so which essentially means that our experience is bisected and the explanation is combination. Okay, so there is a abstract and concrete. We move from one to another constantly in modern science in explaining things, right? So this is another big challenge. So when you talk abstract, people think that only abstract. Then they say that, oh, but that's not how the reality happens. But then when you talk reality in one way, we know that that is not actually the physics, right? So this movement from concrete to abstract constantly happens in science. Same, for example, nature. Our behavior, our body structure, our phenotype, our psychological typologies. Is it nature or nurture? Is it encoded in genes? Is it because of hereditary factor? Or is it because of environmental variable? Abstract, concrete, there is a constant struggle between these two, right? So let's come to the fifth aspect, which is not fifth, I'm sorry, fourth, incongruous. When you talk about physics, I'm meaning modern physics, it's too abstract. When you talk about mathematics, modern mathematics, it's too theoretical. When you talk about prehistory, I'm not talking about only history in the history sense, but also, for example, evolution or history of anything. Okay, wherever there is a historical aspect, in science, or even geology, things of that kind. It's a remote in time. Yeah, long back when humans have not even existed. You look at cosmology, it is too remote a place. Yeah. If you look at the molecular biology, it is too infinitesimal. Genetic theory, inaccessible. Okay. So the modern science, the area of modern science that we are working on is incongruous. So it is not something that is our everyday experience at all. Last point, which is the organized skepticism. Okay. This is something that all of us are completely flabbergasted. When I generally do this lecture, I give an anecdote, a personal experience. Because it is organized by INO, I'm hesitating to give that, let's say, anecdote, but I think I should give that anecdote. Okay. I was in a place where there was a summer school happening. Of course, I was not part of that summer school. I was conducting a different workshop, but this summer school was happening, and a lot of young students from different parts of the country, from different institutions had come there to participate in that summer school. So this happened in the morning breakfast time, in the breakfast room, the lunch room, canteen. So I was sitting in one table and having my breakfast, and then in the nearby table, there were 5-6 young kids. Okay, I'm very old, so I'm calling them as kids, young students. They were all having their breakfast and then talking. So I was in the very next table, so I don't have to overhear. I was hearing because they were talking so loudly. I know that you should not overhear others' conversation, but I can't help it. It was falling on my ears. And it was very interesting, so I was listening. So one of the guy asked, so see, of the different experts who come and give a talk, they are all from different universities and different institutions. And this guy, I mean, all of them are from India. Okay, in that particular summer workshop, all of them are from India. So this guy said that, do you know, how do you identify if that guy is from TIFR, Tata Institute of Fundamental Research? This actually happened. The other guys were all fumbling. Some said that, oh, you will have a beard. He said, maybe that is not a male, it can be a female. Then the one guy said that, oh, they will have a Jolna bag. You know, all these kinds of various things are going on. Then finally, this guy answered, no. You go to that guy, go to one guy, whoever is the expert who has come to give the lecture, and tell that person, 2 + 2 is 4. If the person replies, no, 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 you are right, then that guy is from TIFR. So the first response is no. First response is you are wrong. Okay, that's organized skepticism. So whenever we do research, whenever your paper is going out for a peer review, the peer is first thinking that this should be wrong. That's how you start. You don't start by saying that, oh, it should be a very young guy, it should be a very nice guy, this guy should be from poor country, so should be right. No, you don't start like that. You start with the point that this should be wrong. That's how you start doing your peer review, right? That's organized skepticism. Of course, what I said about TIFR may be also applicable to any institution, but this actually is an incident that took place where I was there. It was a central university. Okay, so I just share it. Organized skepticism is not very easy for us to accept. You know, I mean, if you're a young mother, the child asks you, why should I drink milk? You get angry, right? You say that, I say so. I am your mother. Bloody hell, drink. We feel very, very threatened when we are questioned. But science works like this. Okay, science works like with organized skepticism. If there is no organized skepticism, why do we need so many stages in vaccine development? That's something that people don't really, people find it as difficult to stomach. There'll be a result that is coming out saying that, oh, we did a test of this vaccine in rats. It was successful. Then people will say, why not you then circulate it tomorrow? We'll say, no, 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 we should try it out in some more. Why? Because we have organized skepticism. It worked in rat, but how do you know that it will work in human being? Okay. So we would like to have more evidence. We would like to be more confident, right? That's how the science works. But people think, people don't feel the same way. Okay. So this organized skepticism is a very, very key aspect which troubles the general public, ordinary public. Okay. So when you look at how do you address this? I talked about 5 key challenges, right? So what are the 5 challenges that I said? It's a new reality domain, counterintuitiveness, abstract and concrete, incongruous, organized skepticism. So how do we address this? There are 3 golden rules. The 3 golden rules are from known to unknown. You explain by starting with what your audience know and build upon it. Second, you start with simple and go towards complex. So you explain something simple, a simple process, maybe a toy problem, and then go to the complex. You go from a particular to general. Okay, because the general is something that has to be established to your audience. For you, it is established, but not for the audience. So go from a particular to general. These are the 3 important tools that we use in science communication. And to make unfamiliar familiar, there are various strategies one can use. For example, you can use analogy. You want to teach genetics, you use analogy like a cookbook. Genes are the cookbook of life. Okay, like recipes, there are genes. Like the recipes contains the ingredients, there are amino acids, blah, blah, blah. Okay, you can use it. You can use imagistic explanation. Like if you want to explain what is adaptive immunity in mammals, in human being in particular, you use immunity as a war. Pathogens are attacking you. There are defense lines, etc., etc. Okay. School level, we would have studied a leaf as a factory, right? A leaf is a factory where the inputs are the air, water, and sunlight, and the output is glucose or starch or food of the plant, and the waste material is oxygen that comes out of it. This is how we explain, imagistic. The third tool that one can use is use real life example. Okay, real life example. Suppose if I want to measure the distance of a star, how do I do it? I can't use an inch tape. Okay, a star, nearest star is somewhere around, nearest star to the sun is somewhere around 5 light year away. So which means that if I send some light wave or let's say a radio wave or even a laser, it is going to take 5 years to reach that star, another 5 years to come back if it bounces back. So that is not the way we can do it. So what we do, we use something called as parallax. Parallax is something that we know, like if you are trying to put a thread through the needle, okay, when you are going to put a thread through the needle, you don't keep both your eyes open. You close one and open another, and etc., etc. So that with that parallax, you judge how far your needle hole is and so on, and then you put the thread, right? You thread it like that. So we use kind of the same principle, parallax, to measure nearby stellar objects. Okay, so you can explain it like that. Then there are things called as thought experiments. There is a very famous thought experiment called Hilbert's Hotel to explain about the nuances of infinity. Okay, various interesting concepts associated with the idea of infinity. I'm not going to explain what is Hilbert Hotel here. I leave it as your, let's say, homework or whatever. Just Google Hilbert Hotel mathematics infinity. You will get it. You can read it. It's very, very interesting. Okay, so I'll leave it to your self-learning. But how do people react? How do we react when we encounter something very unfamiliar? Suppose, let's say we go to a foreign country to which we have not made a trip earlier, okay? And then we are invited to a dinner, and then on the dinner table are food which are quite unfamiliar, something that you have never seen in your life. Okay, I'm not talking about non-Indian food. Even non-Indian food, for example, many of us are familiar with pizza or burger or chow mein. No, I'm not talking about. Completely different. The food looks very different. The prepared stuff is different. The way it is served is different. How do you feel when you look at that unfamiliar food? Yeah. Let's say, for example, you go to a new place, particularly in a dark. You land up in a new city, okay, where you have never been, where people speak language that you don't speak, okay. You land there and it is very dark, okay. What do you feel? How do you feel? You feel strange, okay. You feel strange. That's exactly what happens when people encounter science, when it is very unfamiliar. So when they entered into this unfamiliar world of science, there is strangeness, okay. That's the strangeness that creates various kinds of emotion. We feel threatened, right? When you are in a new place, in a dark time, you feel threatened. You think that if some foot fall is here behind you, you think that somebody is going to pounce on you. Particularly if people have scared you, saying that, oh, be careful in Barcelona, everybody is a thief, things like that, then you are more scared, right? So you feel risk. So how do you respond to risk? So how do you respond to risk depends on 4 things. There are four quadrants in that. Okay, these are called as knowledge quadrants. Okay, when our knowledge about the impact can be less or more. Our knowledge about the occurrence can be less or more. So if I take them together, there are 4 ways I can look at it. There are known unknowns. Okay, there are known knowns. Something like the capital of India is Delhi, known known. There are unknown unknowns. Okay, there are known unknown knowns. Okay, What are they? How do we respond? Let's look at it. Let's look at, for example, known knowns. How do public respond to it? These are things that we are certain of. Okay, we are certain. There is no knowledge gap. Okay, there is no knowledge problem. We know it. Okay, so in that kind of a situation, the public response is perhaps there is disagreement, but there is no fear or anxiety. The emotion associated with this is basically disagreement, not fear or anxiety. Okay, so how does it come about? For example, the disagreement can say that in a poor country like India, should we have a 1,500 crore India New to Know project? Instead of spending that much money in this so-called fundamental research, can't we not do useful research? People are dying of dengue. So can we not do research on dengue? Why research on this? These questions, there is no fear or anxiety. Remember that it's only about disagreement. This is how some public may respond. When I say public response, it doesn't mean that everybody, a section of public may respond like this. So how do we respond to it? Okay. When it is about known knowns, when it is the issue of disagreement, okay, when the emotion is essentially disagreement, first explain why science, particularly fundamental science, is important. From past history or so many things that, for example, when the electron was discovered, apparently one press asked J.J. Thomson, what is the use of electron? Apparently, J.J. Thomson scratched his head and said that, I don't know, maybe nothing, no use, right? But what do we do today? Without electronics, there is no electronics. Without electronics, even this Zoom meeting is not possible. Okay, let's look at, for example, Ramanujam's work, mathematician Ramanujam's work. His mentor apparently told that what they are doing is pure mathematics, which possibly has no application. But today, for example, some of the security applications like RSA uses Ramanujam's theory of elliptic curvature. Okay, so fundamental science is important. Today we may not see how it is useful. Only we know what it is, then we will be able to understand it. That's how we should explain. Okay. Similarly, we can show that what we make is not expenditure, but actually investment when we are talking about science. Then look at, for example, the relative spending in India and say, for example, China. We are spending something close to 0.6% GDP. China is spending close to about 2.2% GDP. Their GDP is bigger, so they are spending many times more, 10 times, 20 times more than India. I think even more than India. Okay, we have about 100, 200 scientists per million population. China has close to about 1,800 to 2,000 per million population. So what we need is more. Yes, certainly we need more research on dengue, but that does not necessarily mean at the cost of INO. We need more money. We need more scientists. That's how we can construct our argument. Okay. Compare it with socially useless expenditure. Do you know what is the amount of money spent on last Diwali on liquor in Tamil Nadu? Despite lockdown and things of that kind in last Diwali, that's close to about 4,000 crore. And the cost of INO project for 10 years is 1,500 crore. 1 year, we spend 4,000 crore on liquor. Just on Diwali, not the whole year, just on Diwali. In Tamil Nadu, not all over India. Yeah, compare. That's how you address this disagreement. The other problems could come from known unknowns. What is known unknown? We know some things, but we can't predict what is going to happen. For example, we know that someday it's going to rain, but we can't predict exactly on what day it's going to rain. Right? So this kind of happenings are there around. So some of the public response may be based on that. So if you carefully observe it, there'll be no fear, there'll be no anxiety, but there'll be worry. Okay, the emotion associated will be worry. What is the kind of worry? Maybe it will be too noisy. Maybe there will be a lot of dust that is coming out of it. Maybe there will be hampering of the movement because a lot of trucks will come and go. Basically, because we do see that around us that the construction companies many times are not responsible. The behavior is not responsible. In Delhi now, because of the law and public outcry, whenever there is a building, I mean, there is some kind of a sheets are constructed around it so that the dust doesn't go very far and so on and so forth. Many places people don't follow these things. So a worry will be there. So explain that, no, we won't allow it to do. We can control it. It's not uncontrollable. The worry can be alleviated. Similarly, some worries might come from wrong misunderstandings. Like if I use explosive here, the vibration can travel 30 kilometers and damage a dam. So you show them, no, there are physics formulas where you plug in numbers, you can get answers. Okay, so if you plug in number, just 500 meters away, the vibration level will be 1 millimeter per second, which is less than the shock wave that will be generated by clapping your hand. Okay, so explain it, you can address the worry. Okay, so this is second quadrant. So let's look at the third part, which is known unknowns. Okay, it's something that okay. Also, you explain what is the kind of measure that we are going to propose to address them. Okay, why shock waves? I mean, I think these I told you. Similarly, you can say that what kind of tunnels were built in that same area which had not caused, for example, any damage to that dam. So this kind of explanation will address that. Then comes unknown knowns, which is that others know, but I don't know. Okay, so others may know, but I don't know. That there are some areas like that, which will create anxiety. Yeah, kind of an emotion called anxiety. Okay, so the anxiety may be related to land acquisition because the people may not know. Okay, something is going to come. So when it comes, maybe my land will be taken away. Maybe there'll be some restrictions, like there is a 1 kilometer safety belt around nuclear power plant. Maybe 1 kilometer around the villages would be asked to vacate. It's not going to happen, but this fears may happen. There may be also worry that this is going to take a lot of water, so it is going to be a stress for the local resources. Okay, these are all worries, unknown. Okay, unknown to the public, but somebody else knows. Okay, maybe it's a classified research, so there'll be very strong security. So which would mean that too many security forces will be around. That will be a problem for people. Some of these kinds of things, anxieties are coming from this unknown knowns. Okay, we know it. There is the people who run the INO know it, but the public doesn't know. So how do you address them? You address them by, sorry, there is a mistake in my slide. That's okay. How do you address them? Explain them the truth. Give them the facts and figures. Explain that no tree will be cut, no inch of land will be acquired. That's not needed. Show them the water tank already constructed. Say that that's the amount of water that will be required for the project. Okay. So this way we can alleviate the anxiety. Okay. So then comes the last quadrant, which is unknown unknown. We don't know what we don't know. Okay. Again, I'm talking from the public point of view. I'm not talking from scientist point of view. From scientist point of view, these are not unknown unknowns. But from the public point of view, it's unknown unknown. In their knowledge quadrants, I mean, it's an unknown unknown from the public point of view. And this unknown unknown is what creates the emotion of fear and dread. So questions like, for example, world's largest magnet. So what will be its impact? Okay. So one of the claim that was circulated during that period was that the neutrinos will be attracted by the world's largest magnet. And in India, we know that there are constant power cuts, scheduled and unscheduled power cuts. So what will happen if the power goes off? The magnet will lose its magneticity. So what will happen to the neutrinos? Then they will all bounce to the different direction. So it can damage the groundwater, all the region around will be damaged. This is a kind of one fear, rumor that was circulating, that is circulating, that come from unknown. Okay. So when it is unknown, that is where the key role for good science communication comes in. So a good science communication will help. Explain what do you mean by biggest magnet. It is not in terms of power flux. It is in terms of size. After all, the scan missions have much more Tesla compared to this, and so on and so forth. Explain that good science communication will help. Similarly, earlier we talked about how to make unfamiliar familiar, right? Here, making that unfamiliar familiar will help a bit, because once they are familiar, this kind of fear and dread will drop down. Here, I want to tell you about a small study that I conducted in the recent past. This is about the fake news which were circulating during our coronavirus pandemic. We all have heard of it, right? A person of a particular community is licking fruit and then selling it so that the coronavirus will spread. A particular community person is spitting on food and then selling. We have heard all this kind of stuff, right? What is very interesting is, between January 1, 2020, I'm talking about last year, to July 31st, 2021, that is this year, this whole period, I counted, that is, we have a way of tracking all the fake news which are going on. That fake news collected was close to about 2,400. Okay, 2,400. 1/3 of this 2,400, 1/3, 1 in 3, occurred before March 2020. That is, immediately, it started somewhere around middle of January, and then peaked somewhere around the end of March. By April middle, 1/3 is over. 1/3 came around that time. Actual numbers in India, the coronavirus numbers in India started increasing only after July. So all this happened in earlier, all the fake news happened earlier. And this is not something very new. In 1935, there was an earthquake in Bihar, and one social scientist called Vigyan Prasar went there to Bihar to study about the rumors that spread around the earthquake. What he found, two important things. Before the earthquake, rumors were very large. After the earthquake, very low, rumors died. In a place where the earthquake took place, rumors were less. The surrounding area, the rumors were more. Why? He said that the rumors come when there is fear and anxiety. Something is going to happen. Okay? When something has happened and you have experienced it, you no longer fear it, right? So the fear and dread come when you have no experience, you are not familiar with it. So making things familiar, talking about the science, how the study would be done, how the instrument will work, in, of course, simple manner, depending on to which audience you are talking about, helps. Okay, so these are all some of the things. While we say all this, we should also be very clear that some of the questions which are asked on these projects, we should not be, we should actually welcome them as social people. Okay, there are some questions which will be asked by social movements. They may be related to legal issues, they may be related to ethical issues, they may be related to political issues, they may be issues on social justice. Suppose if somebody is asking us a question that why there is a low diversity in Indian science, very little women, very little people of various communities, and so on and so forth. It's a very well justified critique. It's a question for introspection. Okay, we should not be overtly thinking of saying that, oh, they are asking the wrong question. No, they are all very important questions. Okay. Similarly, in fulfilling the watchdog role of social movement, if somebody is asking whether the legal requirements are met, whether the INO site is falling under tiger reserves or not, asking questions is not wrong, but saying that it is falling in tiger reserve when it is not really correct is wrong. Okay, we should make that distinction. Okay, so we are not challenging asking of that question, we are challenging the fact of that question. Okay, so that a small finer issue that we should keep in mind. Such criticisms are okay. Now I talked of 5 things. Okay, 4 of them emerging from the 4 knowledge quadrant and ignorant quadrant, whichever way you can call about, or knowledge framework quadrant from public. Okay, the 5th one emerging from organized social structure called as social movements. Okay, but these are not the only challenges. That's the most important point. Okay, now comes the other kinds of challenges that are coming up before us when we are talking about INO project, or generally about science and scientific temper. What are they? One is what is promoted by industry and ideology, propaganda. What is generally in literature called as post-truth or willful ignorance. Willful ignorance. So it is not ignorance in normal sense. It's willful ignorance. I choose to remain ignorant. Okay. And what does this create? This creates aversion, animosity, which is very different from fear, anxiety, worry. Okay. They are all different. So here the emotion that is generated is aversion, animosity, polarization. I know as an enemy. Okay. So that we have to understand. Okay. So questions like, for example, natural neutrinos are okay, but neutrinos produced in neutrino factory would be danger, and Indian scientists are engaging in this dangerous pursuit. Okay, so a kind of animosity. Okay, it's a bomb-making project. They are keeping it secret. This location is chosen because it's exactly 180 degrees from familiar. No, these are all conspiracy theories. Many times this post-truth, willful ignorance will come in public domain as something like a conspiracy theory. That's how it will appear before us. Okay. What drives this conspiracy theories? What are the drivers behind this conspiracy theories? When we talked about people's perception, we looked at 4 quadrants of knowledge and the social movements. Okay, there are 5. That's one. The drivers. Okay, so those drivers. But when you are talking about this industry and ideology led propaganda, essentially what is in modern times called as post-truth, okay, willful ignorance. What are the drivers? One driver is junk science. What is this junk science? Like, for example, for a long time, people knew that smoking tobacco is related to cancer. But then what did the tobacco industry do? It hired few scientists and then made them write paper, which will question or which will give a very ambiguous statement. So now the industry started saying that there are 2 sets of scientists. One who say that it will cause cancer, the other who say that it won't cause cancer. So what should we believe in? So basically as if like the scientific opinion is divided. Same thing happens in climate change. Not so much in India today, but it is happening. Okay. In US, for example, there is a strong section who think that the climate change is not real. It is a fake thing that is projected by a group of scientists. In India, for example, vaccines, there is a group of people who think that vaccine is a conspiracy by Melinda Gates Foundation to kill people in India, to reduce India's population. Junk science. Okay, so it comes from junk science. Then the second challenge is what can be called as post-truth. Okay, where facts don't matter. Your emotion is the central part. Okay, here it's a junk science is a very conscious, intended effort to upset the science. In post-truth, you don't look at the facts at all. Your emotions are the only thing that matters. Recent in India, cows are the only animal which inhale and exhale oxygen. If they inhale and exhale oxygen, why should they even do it? It's a waste of energy, right? A mammal which does that, inhales and exhales oxygen would be more preferred than a animal which doesn't do, because it will save energy, and in evolution, I mean, this would have been completely eliminated, right? So any simple science understanding would have told you that that's not possible, or many other things. Sorry, anything, Karthikeyan?
No. Please, TVP, go ahead.
Yeah. So the post-truth is another driver of we are talking about industry and ideology propaganda. So first driver is junk science, second is a post-truth. Okay. The third is a modern fad. Many of us are also afflicted with it, deep ecology. Okay. Man, sometimes human, many times it is man, because some people believe that women are more ecological and blah, blah, blah. So it is man or sometimes human, or the people who are destroying the world. Okay. In recent times, we have seen this, right? Earth is recovering. When it was lockdown, this is a message that went around, right? Earth is recovering. Air pollution is slowing down. Water pollution is cleaning. Natural wildlife is returning home. Coronavirus is Earth's vaccine. We are the virus. That is, humans are the virus, and coronavirus is Earth's vaccine. And it had interesting pictures of river dolphin coming back to river and blah blah and blah blah and blah blah. This is the same time when if you are carefully watching the news, you would have seen that thousands, lakhs of workers were trying to go back. There was a human tragedy. That's when this was also circulated. Okay, so this back to nature. Some or other we go back to nature, everything will be solved. That is one of the principles of this deep ecology. Okay, so the deep ecology thinks that in some way the human influence should be reduced. So one way to reduce the human influence is also to reduce human beings. Okay, so one of the defenders of deep ecology very clearly said that the number of human beings in this planet should go down. Yeah, of course, go down by natural means, not by this kind of unnatural means. Okay, but is it really correct? Are the humans the virus? Is it really correct? Let's look at, for example, the global inequality. Okay, so if you look at the global inequality, 1.1% of world population, okay, 1.1% of world population owns 45.8% of wealth. 45.8% of wealth with 1.1% of world population. If you look at the bottommost 55% of the population, they own just 1.3% of the world wealth. So are these 55% the virus, or is the 1.1% the virus? So to say human as virus, to conflate between this 1.1% and 55% is terribly wrong, right? Terribly wrong, right? So if the wealth was more evenly distributed, maybe we won't be consuming so much. We won't be exhausting the natural resources so much. We won't be wasting material so much, right? So what essentially comes from the social system, we blame it on humans. So is it really true? In India, if you look at the top 1% of the richest, share 51.5% of country's wealth, and the poorest 60%, share just 4.7% of country's wealth. So can we blame, for example, the environmental problems from India on the 60%? Should the blame be equally distributed between this top 1% and the bottommost 60%? Is it really correct? Is it really justified? Simply nonsense, right? So this deep ecology is terribly flawed. It's a terribly flawed argument. Okay. So along with this, there is one more driver of this industry and propaganda mechanism, which is science denial. So what is this science denial? What are the characteristics of this science denial? So if you look at all this, that is industry and ideology propaganda, whether it is junk science, post-truth, or deep ecology, back to nature arguments, what do? They do some amount of science denial. So what kind of science denial? One, perhaps they engage fake experts. like this story about neutrinos being attracted by the largest magnet and then will be expelled when there is a power cut, was by a person from Kerala who has a PhD in English. His PhD thesis is on Shakespeare. Okay, and that's a guy who wrote, and then that's a story that was picked up and then circulated by so many people without even looking at who that guy is. That is the fake experts. Okay, so sign denial, fake experts are used. Then there are logical fallacies, many kinds of logical fallacies. Like one of the logical fallacies is that, oh, if you are going to use explosives, it will cause damage to the dam. But then the logical fallacy is that proportion. By putting, let's say, a handful of salt in sea, I'm not going to increase the saltiness of sea, right? Yeah, so logical fallacy. Okay. Then impossible expectation. So expectations like you want to assure that the future, the neutrino knowledge will not be used for any wrong purposes. How can you give that assurance? I can wish that it will not be used for any, let's say, weapons of mass destruction. That will be my wish. I will also work for it. But can I give assurance? There is no way you can give assurance, right? But that kind of impossible expectations. Cherry picking. You pick one small incident somewhere and then say that that's how. Conspiracy theories, like it's a Fermilab secret project and so on and so forth. Okay. So what do we do? Do I have another 5 minutes?
Okay, TVV.
Yeah, sorry. I think maybe I'm taking longer time, but sorry. Okay. What do we do when we encounter this kind of science denial? What we need to do is something called as debunking. So what are those debunking? One is fact check. Okay. So replace the myth with factual alternative information. That is one. Second, debunk the misconception. Point out the fallacies in the argument. What kind of fallacy is there in the argument? Like, say, for example, when we take this myth of Fermilab conspiracy to make a secret bomb, go into the website of the Fermilab Dune project. You find out collaborating countries. What are the collaborating countries? India is a collaborating country, but then Pakistan is also a collaborating country. So can we say that US, India and Pakistan are jointly developing some weapons? Doesn't seem logical, right? Okay, go in the list further. Iran is a country which is part of that Dune project. So can we say that America and Iran are sitting together and developing a weapon of mass destruction together? Well, that's what you point out the fallacy in the argument. Okay, so there are various kinds of fallacies which can be addressed. For want of time, we'll not go into it, but these are the main way we do what is called as debunking. Again, if you Google, I mean, there is a very interesting handbook by UNESCO on post-truth challenges. In that, there is a chapter on debunking. I mean, you can learn a bit on how to do that. Okay. So coming back, understand these three rules: from known to unknown, from simple to complex, particular to general in communicating science. I think I'll stop here for want of time and other things. I mean, of course, beyond a point, I think it's also not possible for us to sit and listen your talk too long. Thank you. Any questions? I'll take.
Yeah, thanks very much to you. Actually, many of these points, the way to bring into perspective about thinking in multiple ways, and every coin has two or three sides, three surfaces, I would say. So it's very important for people to kind of able to think beyond the stereotyping. And those 5-6 fallacies that you talked about is most of the time the society gets stuck. Even the educated society gets stuck with something or other. Very, very nicely to bring up what actually makes an important communication when especially dealing with topics which are sensitive to the society. And some of the examples in the recent past that you took, namely Corona and others, is startling, because we all see this happening, and our cell phones get jammed with so many such messages coming up and so on. Very nice. Thanks so much. But okay, any Any quick question to TVV? And of course, this will seamlessly now go into the next session, which is more like a panel discussion, you can say, in which again TVV is going to be there. But if you have any quick questions to him, otherwise we'll move on to the next and last session of the day.
I'm sorry, I did not time my talk because I actually changed my talk today completely, and then I was just preparing before the talk. So sorry, next time I'll be more precise.
No problem at all. It is always a pleasure to keep listening to your TVV. I'm sorry I interrupted you.
No, that's right. Yeah.
Okay, so since I don't see any immediate questions that are okay, just a minute. Yeah, there is one question seems to be TVV. Can you see this question on the chat? TVV, can you hear me?
Yeah, so there is one question which is by Ajit Mohammed. How will you manage electricity when there is power cut? Okay, the power cut point that I was making was that the claim was that the magnet will attract neutrinos. Magnet won't attract neutrinos. Neutrino is a chargeless particle. Okay, so a chargeless particle cannot be attracted by magnet, whether it is world's largest or smallest. It doesn't matter, right? So neutrinos will not be. That's a fundamental flaw in that argument. So what I was saying was that this kind of fake, false, something like cow inhales and exhales oxygen, which is fake. We know that all mammals will inhale oxygen and exhale carbon dioxide. All plants during photosynthesis, not during their respiration. Respiration, it will be again same. But during photosynthesis, will absorb carbon dioxide and release in the process oxygen. This we know, all plants. Okay, that's how the plant and animals differ fundamentally. So this claim of cow inhaling, exhaling is terribly wrong, right? Or the same way, the idea that the neutrinos will be attracted by magnet is wrong. The magnetization is for something completely different. I'm sure in the lectures they would have explained to you, right? So it is fundamentally wrong. So it doesn't matter whether there is a power cut or not. It's not going to impact. It's not going to capture neutrinos and keep it. And neutrinos cannot be captured and kept it like that at all. Yeah. So.
No, can I say something on this?
Yeah, please. Happy to meet you. Your
if
video.
Power goes, then what do you do? And so we will have diesel generators for that period in which the the power is not there, and that will generate electricity, and that will power or some of the key things. Perhaps the magnet won't be run at that time, but some of the key things like gas systems or some other systems which will need continuous power will run, high voltage systems and so on. So,
thank
does
you.
that answer your question, Mr. Ajit Mohammed?
There is one from Karthikeyan. Notice yourself in Science Monitor. Thank you for watching it. Can you share what all the resources you did to improve knowledge in the field of research? Sir, I want to say that all our work are available in YouTube. Just go to YouTube, Google Vigyan Prasar. You will get all the material that we have developed, including some videos on neutrinos. Okay, so under India-based neutrino project, all of them are available in YouTube. Vigyan Prasar has a channel, YouTube channel. In that channel, it is available for free watching. So please go and take a look at it and then use it. We also have some conversation with Vivek Datar. Okay, that's also available in the YouTube. So you can just put my name and Vivek Datar YouTube, you will get it.
So there is another question you can see.
Yeah. So the water tank is already constructed, which essentially means that is the amount of water that will be required. So it is not like people when you are not sure of how much water, then you imagine that a lot of water will be consumed. So when actually there is a water tank, you know that is the kind of water that you are going to consume. Everybody will know that there is a water tank on top of my apartment. Okay, this is the size of water tank on top of my apartment. So that's all. it's in an apartment complex, not just one apartment, one housing complex. That's the amount of water that is there. I mean, the water tank is similar to that size. So just because you have the water tank doesn't mean that you need to put water in. So that is the amount of water that will be used from the water source. So water is not. This project is not a very high consuming, water consuming project. That's what we were meaning to say. What I was saying that by showing that picture of that water tank, people will easily understand that it is not a very high consuming, water consuming project. Some project might be, but this is not.
Okay. Whatever.
I think perhaps we can go to the panel, no? Any of these questions also we can take up there, right?
Exactly. So I think now let us really just open up. I mean, just a simple matter that already it is like panel discussion. So thanks once again, TBB, for this very nice talk. So we come to the last session, namely kind of free question answer session. So whatever questions you have, because this is the last session before we close the online part of the campaign. So please feel free to ask any questions to any of the panel that you heard this morning, yesterday, and day before. So please go ahead.
Good evening, sir. I have a question. Can I ask?
Yeah, please go ahead, ma'am.
Okay, so this question is for Dr. TVV, but please feel free, anyone can answer it. So basically, whenever there is an announcement of such a big science project as this one, there's always some kind of resistance from the Indian public. What is the reason, do you think? Because I do not believe that it's because we are a third world country or whatever, because there are people who are really educated also making these conspiracy theories. And even in developed countries like the US, you've seen right now people are being very anti-vax and everything. So I don't think it's the matter of development or education at this point. So what do you think might be? Because this is not the first experiment. This is not the first project to have faced this kind of opposition, right? So what do you think should be done at the ground level for people to be more scientifically aware?
Okay, Jashwini Ashokan. Yeah, can I answer this? Or my view on this?
Yes, sir, please.
Yeah, go ahead.
Yeah, okay. See, as I was pointing out, there are three drivers or three class of drivers. First, I think we need to understand this. Number one, our own psychological makeup. Okay, what do you mean by our own psychological makeup? Let's look at, for example, if there is a risk that I'm thinking of. Okay, risk, what will happen when I retire? Okay, what will happen when I retire? How will I manage my financial resource? It's a risk. This risk will seem very remote when I was 14 years or 15 years. But this risk will loom large when, let's say, a few years before my retirement. I'm just telling you that, giving you an example to say that how within ourselves, certain emotional state called fear, risk feeling, these things emerge. But in the objective sense, is there a difference in the risk when I was 15 years and when I'm in, let's say, 55 years? No. Objective sense, there is no change. It's the same thing, right? But my feeling of it changes. So one is the psychological reaction of human beings to known risk and unknown risk. Okay, the fears create fears or anxiety, emotions created with known and unknown risk, psychological. So that's one driver that is usual. All of us, normal human beings. The second driver is what I call as the industry ideology propaganda. So if you look at the industry ideology propaganda, there is industry-based groups which fan certain false stories. There is propaganda groups which, because they strongly believe in certain ideology, like say, for example, they may think that human beings are virus. So some or other they should bring back the nature into central focus, etc., etc. So there'll be a propaganda-based fear throwing. That is second aspect. The third that is coming up is social groups watchdog role. Okay, so we should not conflate between all the three. The social groups watchdog role sometimes may be done in a wrong way. Rather than only being a watchdog, it may be it may start judging. Then it will be a problem. You can be as a watchdog. You can ask a question: is it in Tiger Reserve or not? But if you just, you make a preconceived opinion that it is, then there is no dialogue, right? So that may happen in social movement also. But there are three kinds of challenges that come from three driving forces. So once we understand these three driving forces, we will know that it is not only in so-called third world countries, but it will be there everywhere where the human beings are, and everywhere where, let's say, the motivated groups are there. Okay, so the motivation may come from different ideological ground, but it will be there. Okay, and it has to be, we have to face it.
Okay, thanks, AVB. Any other questions to the panel? Anybody? No questions at all?
And it is very surprising. We are expecting 1 hour, it should not finish.
You can ask any question of not necessarily only connected with physics. But if you have anything about career, any question.
As Professor Shutra and Dr. Shutra mentioned, you can ask any science. This is not that what we have discussed in last 3 days. Any science matter, anything you have in your doubt, just ask. We will try to give you answer. But I'm not sure we can give all the answer, but we will try our best to give you the answer. Yeah, someone is talking.
You can also make some suggestions. For example, if you felt that a particular topic or something is to be included in a future such outreach program, or or you want the way you want to conduct and so on. So this is one kind of session which is all inclusive. Okay, one of you can take this. What is the dream of our project? What is the dream of our project in future? Is there any other possible sites in India for the neutrino project? This again came from Ajit Mohammed. So Govindo or Vivek, Datar, Amol, maybe you want to take?
Okay, Amol, maybe.
Okay, so let me first give a slightly global view. So what is the aim of studying neutrinos? So it's not just we who are studying neutrinos. Neutrinos are being studied worldwide by, I don't know, maybe about of the order of 1,000 scientists. What everybody is doing, they're trying to look at neutrinos from different angles. Okay? So INO, for example, tried to focus on atmospheric neutrinos. And as you perhaps learned, the aim is to try to focus on this property called as mass ordering or mass hierarchy, which neutrinos have. However, perhaps you learned in, I don't know, perhaps Professor Agarwala gave this talk about neutrinos, that there are many, many unknown questions and people try to study them in their own ways. Now, depending on what property you want to study, you will have a different kind of detector. Okay? Because you wanted to study, for example, mass ordering, we said that we will have a detector which is ion calorimeter. On the other hand, if you want to look at neutrinos from the sun, for example, you would have a detector which is, for example, a water Cherenkov detector like super Kamiokite. If you want to study very high energy neutrinos which are coming from from cosmology, from outside our galaxy, you will perhaps want to have a detector like Ice Cube, which is a detector at the South Pole, the biggest one that we have currently. If you specifically want to look at some particular lines from the spectrum of solar neutrinos, you will have some detector made up of particular material. So neutrino itself has many unknowns, and therefore, when we talk about the future of neutrino physics, what experiment would you like to do in future after INO? It will depend on what are the questions open at that point of time, and which of the questions we can address easily, given our resources and so on. So, for example, there is another experiment that people are trying to do, which is the experiment on neutrino double beta decay. Okay? That's a slightly smaller size experiment that looks at the nature of neutrino masses, whether they are Dirac or Majorana. Okay, so the kind of experiment that we will do in future is not limited. And depending on different experiments, you will perhaps need different surroundings. I know, for example, it's a big experiment. It needs a very huge cable. Another smaller experiment might need a small cable. Okay? So it depends on that. However, what is common to any experiment in neutrino that we want to do in future is that it will have to be really underground, deep underground. So therefore, it is important for us to be able to create facilities for underground experiments. Okay? And then as time goes, you can figure out which are the most important problems to do where such caverns can be useful. Okay? So in that sense, I think that the future of neutrino physics is connected to the future of underground physics. So remember that underground physics not just for neutrinos. People can do experiments with which involve geology, some kind of biology, some kind of things. Anything where you want to get rid of these cosmic muons that interrupt you, you can do those experiments in those caverns. So, so I guess it's slightly different from the question that was asked. But my answer would be that as scientists, when we try to think of a new experiment, we think of what are the open questions now, and then which of them is important enough for us to take up. So all this needs training, and experiment like I know about which you have learned in the last 3 days provides you with the training about how to design experiments, how to work with your hands. Many of you will get to see when you come to Madurai, the actual experiment that we and our own students have built. That training helps you in building any kind of future experiments of a similar variety. So do not think of INO as one experiment. It is a basis on which we built our sort of base, based on which we will build experiments 10 years in future, 20 years in future. So there is no limit. The limit is your imagination. Thanks.
Very nice.
Maybe I can add to what Amol says. He mentioned, of course, the neutrino's double beta decay experiment, in addition to the ICAL atmospheric neutrino experiment. But there are others, like, for instance, measuring very, very tiny cross sections, where you might get a count when you run a milliampere beam on a target and in a month or something like that. And these are experiments related to nuclear astrophysics. What goes on in stars, not just the sun, but anywhere else in the universe, and involving heavier and heavier elements. So this is an area which requires to be experiments to be done underground, because ultimately in all these very low counting rate experiments, low event rate experiments, you have to go underground. The cosmic ray background is the one which is the most difficult to handle on the surface. So you have to go underground. So there are many such things. And so the deep underground lab, for instance, just imagine if we had this lab maybe around 2000, we would have completed an experiment, because that is the kind of time scale that it takes to make such a detector and get data and analyze it and present the result. So this is a facility. Of course, you have to have a flagship experiment in order to justify a large amount of money that you are using. It's after all public money that you're using. So you have to have a plan. But quite often, it turns out, as happened in Kamioka, as happened in many other cases, that you start off with a certain plan, you get a result, but then very often during the course of that study, you branch off and there is something else which is much more interesting. And that is exactly what happened in the Kolar goldfields. The atmospheric neutrinos were discovered, but then they found that this low background, there was a proposal, of course, of the proton decay, and they found that they could quickly put together an experiment. And if they had been lucky, had Pati and Salam been correct in their, had that theory been correct, they would have found proton decay. And who knows, somebody might have got a Nobel Prize from India. It didn't happen that way. Nature didn't, like this thing. So, and then the gold mine closed down. So we lost an opportunity. But at that point of time, it was an exciting thing to look for, proton decay. And even to this day, detectors which are 100 times bigger, or at least, about 100 times bigger, 100, 200 times bigger, have not found it. And people are building another detector which is 10 times bigger than that to try to see if you can measure proton decay. So this quest goes on. Goals might change a little bit. And of course, we are looking for surprises. So we should be aware that there might be surprising things in store, and pick up that opportunity when it comes.
Okay. I think Murthy want to comment, or Murthy, please go ahead. And there is a question that we will take it up after you finish. Murthy?
Possible, okay. In future, is there any other possible sites in India for neutrino project? That is what the second part of that question by Ajit Mohammed is. Correct? So yes, I just want to make a comment on it. Yes, it is possible to have more than one underground facility for neutrino physics in India. But in identifying, as you may have heard, as you have heard before, in identifying the Bodhi-Westhill site, it is not just that 1,000 meters cover that we were looking for. We were looking for various other things like compact rock, very stable rock, and a short distance for the tunnel, which was in fact 1.9 kilometers, about the shortest that we found. So, but if you just think in terms of mountains and going under the mountains deep, then there are many other possible sites. But then the tunnel length will be much, much longer, and rock conditions may be very different. It is only in Western Ghats that the rock conditions are extremely good, and Western Ghats being a hotspot for ecological diversity, you have to choose a place where the ecological and environmental impact will be either minimum or even close to zero. And that is how we arrived at the present location. However, in future, it may be possible because there are large number of tunnel projects that are going on in the country, both in Himalayas and in other areas. There are many highway projects, many railway projects, and many projects which are being built for hydropower station. If these projects are located in Himalayas, then it is not possible to construct a large cavern like something that we propose to host ICAL. ICAL is very big. Such a large cavern cannot be built in Himalayas. However, if you have a small experiment, we don't know, as Amol was saying, that imagination is very important here, and based on the science knowledge, we might come up with many suggestions in future. So one may be able to build a small lab along with these road projects under, tall mountains, and have a very deep lab. It is possible. So that depends on the kind of proposal that one comes across. So the answer is that it is possible that there may be more than one, a few underground projects in India. But when you build any for something like iron calorimeter, which is large, you also want to have future in mind because you're building a large cavern under the mountain. So you make provision for many smaller experiments, and that is what already has been done in the proposal for underground project in Bodhi West Hills near Pottipuram. Thanks.
Okay, Murthy, there are a few more questions, but before that, I think TVV has some other commitments, so he has to leave. So we'd like to thank him for being today here and
thanks,
sharing his
TVV.
value.
That was a very nice talk.
Okay, so bye TVV. And so we'll continue with the further questions. One question that I see is from Dinakaran A. Is studying neutrinos and then behaviors will lead to discovery of our evolution, that is from Big Bang itself and some mysterious concepts of universe. So Amol, do you want to take this or want to pass on to Murthy or Vivek?
I can take this.
Yeah. Okay.
So let me see the question. Okay, so this is about Big Bang and evolution of universe and so on. So let me tell you two interesting facts about this. So we can go and explore. Okay. So one is, of course, neutrinos are produced with everything else at the time of Big Bang. And I don't know if it was mentioned in some of the talks given, but you perhaps have heard of the cosmic microwave background radiation. These three Kelvin photons that are there everywhere in the universe. Just like that, there is also expected to be a cosmic neutrino background radiation. Okay, it will have a temperature not 3 Kelvin but about 2 Kelvin, and we know that this should exist everywhere in the universe. Okay, this has not yet been detected. In fact, one of the future aims of neutrino experiment is to look for this. And just like understanding of the cosmic background radiation is called CMBR or CMB, has told us so much about evolution of our universe right from the beginning. Okay? The observation of cosmic neutrino radiation would also tell us something about it. In fact, the cosmic microwave background radiation tells you about the universe when it was about 300,000 years old. But if you look at the cosmic neutrino radiation, it will tell us about the universe as it was at about when it was about, I think, 2 seconds old, if I'm not wrong. Okay? So you can really go very close to the Big Bang and get some information about it if we can detect the neutrinos from this cosmic neutrino background. So that is one part of the answer. Second part of answer is among the sources of neutrinos, one of the major sources is actually a supernova explosion. And perhaps you know that it is quite likely that all the elements on Earth, all the heavy elements, were actually produced first in the core of a supernova, which later exploded. Okay, so this means that everything that we see around us and everything that we are made of actually came from a supernova explosion, which was triggered by neutrinos. So we know that supernova explosions happen because of neutrinos. Okay? And in that sense, we can also learn about evolution of heavy elements that came about around us by trying to understand how a supernova explodes and how neutrinos play a part in that. That also happens to be an open question which has not been solved yet, and it's waiting for an answer. It's going to take many decades to get an answer. So you might actually be involved when that actually happens. So in short, both for Big Bang neutrinos and neutrinos from supernova are two sources from which we can learn a lot about our origin. Okay?
Thanks. So another question here, it says that is there anything known about the antiparticle of a neutrino? Are neutrinos their own antiparticles? So maybe Professor Datar.
Maybe Murthy can answer this question. I can take it, of course, but
yeah, go ahead, one of you, Murthy.
Okay. Murthy, would you like to answer?
You go ahead.
Okay.
Yeah.
Okay. So the answer to this question we actually do not know. Although the neutrino was proposed in 1930, we still do not know the answer to this question. is the neutrino its own antiparticle? So if it is, the jargon is that we call it a Majorana particle. It's a simpler description of neutrinos, a two-component description. Whereas if it is not its own antiparticle, then it's called a Dirac particle. So then it requires a four-component description, which means that it obeys the Dirac equation, and this has four components. Okay, so this question can be answered, or at least many people are attempting to answer this through the so-called neutrino-less double beta decay experiment. So if we do observe neutrino-less double beta decay, then it will tell us that it's a Majorana particle. We do observe 2 beta 2 neutrino decay, and this is a very rare process, but this has already been observed in about a dozen or so cases in nature. Very nice experiments have been devised to do that, but that is a more or less a kind of garden variety process, in the sense that it doesn't lead to anything fundamental. Whereas if we observe the 2 beta 0 neutrino decay, then it will tell us that the neutrino is a Majorana particle. Of course, there are other ideas as well as of probing the Majorana versus Dirac nature of neutrinos. In fact, Professor Murthy has proposed one such idea, and I don't know if Murthy wants to talk about it now, or maybe.
No, that would be somewhat detailed.
Idea,
but one additional comment I want to make for this about your this thing is that if in the standard model, as you have heard before in all the introductory talks, neutrinos are considered to be massless. Okay, so if the neutrinos are massless, this question doesn't arise. Okay, neutrinos and anti-neutrinos will be very different, and we know that both of them are there. Okay, so the question of neutrino being Dirac or Majorana is important only if the neutrino mass is non-zero. Now, this is a question beyond standard model now, because we know that the neutrinos are massive. At least out of the 3 active neutrinos, 2 neutrinos have to have non-zero mass. So then the question arises, that is what you are asking, can the neutrino be its own antiparticle? Because the mass is non-zero for at least 2 of the active neutrinos, this question now makes sense. Within the standard model, this question cannot be asked, but this is a question beyond standard model, that is neutrino its own antiparticle, because they are found to be massive. We don't know what the masses are, but we know that there are at least 2 of them should have non-zero mass, most likely all the 3. So if that is the case, then can a neutrino be its own antiparticle? So if it is its own antiparticle, it's called as the Majorana neutrino. If it is not, then it's called as the Dirac neutrino. That is like electron and other particles. Okay, so that question cannot be answered now. We don't have an answer yet. There are experiments going on, as Vivek mentioned, this double beta decay experiments. And in future, there are many other experiments that have been proposed also. So hopefully we will know the answer to this question, maybe 10 years or 20 years from now. There is also a proposal, and R&D is going on by a group of people in India to do this neutrino-less double beta decay experiment using tin. The experiment is called tin. And they are doing the R&D. So when the INO is built, this is one of the smaller experiments that will go along with the iron calorimeter detector. Thank you.
Okay. Before we take Srini, I see here. Yes, Amol.
Yeah, so I had a comment. Of course, Professor Datar and Murthy answered the second question very efficiently. Are neutrinos their own antiparticles? I'd like to answer the first question, which is, I want to take a simple answer. The question was just, is anything known about antiparticle? So indeed, this part we know for sure. Okay, antineutrinos exist. In fact, we know that the neutrinos that come from the sun are electron neutrinos, but neutrinos that get produced in the reactors are electron antineutrinos. So we have seen antineutrinos. When we see atmospheric neutrinos, we see both neutrinos and antineutrinos. So it is not in doubt that there are neutrinos and antineutrinos. Both of them exist. What is complicated is if there are their own antiparticles. This is just the simple part of the answer that I wanted to mention. Yeah, that's all. You can go ahead.
Satya, there are many questions.
I think I can answer this is fairly simple. Ajit Mohammed has asked a question: why the neutrino particles are called as ghost particles?
No, I think you are jumping the.
Oh, there are some questions before that.
Yeah. So here is a question: among all the three varieties of neutrinos, which one is the predominant in nature? Asking about probability. Amol?
Yeah. So the answer is none. In fact, the maximum number of neutrinos are available in what I mentioned earlier as the cosmic background radiation neutrinos. And in that radiation, all the neutrinos are there with equal probabilities. Apart from that, of course, as you said, stars generate new electron neutrinos, so on, but that's a very tiny number. So if you go by probability, it is very, very close to 1/3 of all neutrinos. If you want to count neutrino and antineutrino separately, it's almost 1/6 of everything. Very, very close to that.
Yeah. But on the surface of the Earth, you don't have that many nu taus compared to nu mu, right?
So in atmosphere,
because of the atmosphere.
So now if you ask me a question about the neutrinos in the whole universe, this was my answer. Everything is the same.
Correct.
But now if you ask me in solar neutrinos, I will say, well, everything is nu and maybe oscillations give nu mu and nu tau. You ask me atmospheric neutrinos, I will have a different answer. I will say, yes, they are nu mu, nu tau. And
that's right. So
the answer will depend on what you want to.
Question is in nature, so your first answer is the correct one. Yeah. So the next question is, does INO project make any nuclear waste? Yeah. I think.
I was just saying,
Santoshan. Answer is a very clear no, because it has nothing to do with nuclear waste.
Okay. So let me go to Ajit Mohammed again. Why the neutrino particles are called as ghost particles? Maybe if Govinda, are you there?
No, Vivek has started answering this, so you can ask.
No, it's okay. Govinda answers, no problem.
Okay, Datar, you continue.
Okay. So it's called a ghost particle because it moves through matter freely. I don't know if some of you have seen these comics where there is a ghost called Casper or something that freely goes through walls and things just merrily. So it's the same thing with the neutrino. The neutrino can go through the whole of the Earth without any attenuation. Well, the attenuation is to the level of 10 to the -8 or something of that order. So practically without any attenuation. That's what makes it hard to detect. And so this ghost particle is really hard to detect. So we have to put together a 50 kiloton detector and then have only 3 events per day from atmospheric neutrinos. So that is the reason why it's called a ghost particle, because its interaction probability with matter, which is only through the weak interactions, is very, very tiny. Of course, this interaction probability increases with energy. So if you have, let's say, M.V.N neutrinos and compare it to the cross-section or the interaction probability of G.V neutrinos, the G.V neutrinos are more interacting than the M.V.N neutrinos. Similarly, the TeV neutrinos interact with a larger probability. So at low energy, the interaction probability goes like E squared or MeV or tens of MeV energies. At GeV and so on, it goes like E. So that's the way it is. So I hope I've answered your question.
Yes, sir. We'll move forward. Next question from Dinakaran A. Assume that a neutrino propagating in space, will it be affected by gravitational wave or space-time curvature? Maybe gravitational field, maybe. Anyway, so who will answer this?
No, answer is yes. Like any other particle which has energy, it couples to the gravitational field and it will be affected by the gravitational, space-time curvature. This is like, you know, you remember studying light bends in gravitational field. Similarly, neutrinos also get affected by the gravitational field. So the answer is yes.
Okay.
Everything couples to gravity. Everything that has energy couples to gravity.
Okay, I think we answered all the questions right now. What are there on the chat? If there are any further questions, please feel free to. I'm just seeing if there are any questions on YouTube. I don't find any. Okay, nice. We had nice. Initially, it was all silent, so I was worried, but we had nice set of questions. Are there any more questions, please?
Actually, I want to ask a question to, as a sort of survey kind of questions to people who have come here. Did you? There is this confusion often between a neutrino and a neutron, and that's what sometimes makes people scared of neutrinos, because they hear of neutron radiation, and when they think of neutrino, it somehow brings to their mind, oh, this is like neutron, and people don't really appreciate that neutrinos are very, very different from neutrons. So the question I had for you is, did you at some point of time have this confusion, or did you know, or do you know people around you who are likely to have this confusion? Because I think it is one of our duties to remove this basic confusion of people's mind, because it's just a language question. No, the two words are very, very similar, but the two objects are very, very different. So maybe, I don't know, is there a yes or no people can give, or is there a hand that they can raise if they think they know somebody who might have such a confusion, which now they can remove?
Yeah, I mean, they can use chat in case, I mean, some answers can come, definitely. I don't have a poll enabled for this, but it's fine if they type in the chat box.
They can put up their hand.
Yeah, or I mean, even writing on chat is okay.
Which is of course great if you knew the difference anyway, which is very good. But I think from what I see around us, at least people who are not in science often have this misconception that there are neutrons and there are neutrons. So when you talk to people, very often the first thing that you have to tell them that these are not neutrons, but these are neutrinos, which are very good.
Yeah, true. Okay. Does it mean that we are now run off any more questions from the audience? Okay.
All been tired after listening to the talks.
Okay, that's fair enough. You still have one more opportunity, one full day you are going to spend in the IHF campus. So I just want to, before we leave, I want to just flash that one slide. So you can see that I'm sure all of you are here today on this call. So the one that I highlighted, namely about 15 of them, actually these two may not be there. 15 of you probably are there today on the call. We'll be visiting the IHF lab tomorrow. And you are all local, you are not from any or other areas. So you please, I will send once again a reminder to all of you, but please make sure as per my previous mail, you should come to IHF campus at least by 10 o'clock so that the rest of the program goes quite well. And so I'll also send you in that mail reminder, I'll also send you the Google link and address and so on of this place. Okay. And the other batch, which you will see below, of course, from these what I highlighted, you will be visiting on September 11th, that is the coming Saturday. For that, of course, we will have a trip to Theni. We'll pick you up from Theni and then bring you, and the rest of the program will remain the same. In any case, both for the batch tomorrow as well as for the batch on September 11th, I'm going to send you a reminder. Okay, so that is.
There is one comment by Nazreen, but that's not a question, that's just a comment.
It is clear, sir, there is not going to be any issues with environment or surroundings, right, sir? Okay, so Govinda should once confirm this, sir.
Which question?
It is Nasreen, sorry.
Yeah,
the question
so it
is
clear, sir, there is not going to be any issues, environment or surrounding, right? Okay. So I think yesterday Professor Indumathi had mentioned, when you make the cavern, certainly there is a blast. We cannot say that it is that equivalent to that there is no blast. But the point is that this effect will be very, very minimal. Surrounding village people will not able to notice it. So this effect will be the very, very minimal effect, which does not change this in environment or make any effect in the surrounding. That should be the, I would say, the correct response.
Govinda, one more comment on that. That even the small effect during the construction time is only during the construction time, which lasts only about 3 years. And all this vibration and other things you are talking about, which Indumathi talked yesterday, whatever that minimal thing is, is only for that period. When the observatory is functioning, it is operational, there is no disturbance to anyone, either the people or to the surroundings. So we must distinguish between these two periods, the construction period for minimal disturbance, totally minimal, and operation time when there is zero disturbance.
Okay, so if you finish, I have just one final comment maybe.
Oh, yeah, sure. So I also shared here in the chat box, please copy paste in case you need the venue, I mean the lab address as well as the Google map. So it's very simple to find out. It's near Madurai Kamaraj University. Okay, so yeah, so Nasreen replied saying thank you for confirmation, sir. That is Govinda's your answer. Yeah, we are all done, Govinda.
Yeah, so this is okay. One of the final remark, before final remark, just to mention at the very beginning, people who are talking about the making the lab or the facility. So sometimes it was mentioned that there is a lab. This is the Gran Sasso at Italy. The lab was made, and then continuously last 3-4 decades, one after other experiment is going on in that lab. So this is the facility is built up, and then one by one experiment is going on. And one of the main goal of this project is also that, means we start with this ICL experiment, but the main thing is that we will make an underground facility such that in future, as Professor Dighe mentioned, what is the important physics, we will start that physics program at that underground lab. Okay, so that's this continuation of the research. And now as a final point, as a project directors, thank you all of you to joining here. And next 2, 3, 4th or 11th, you will come again to our lab for more interactions. And my request to you people, if you have any more doubt, you contact us. I will try to give you the response to whatever this query you have. And with that response, you go to your college, your local area, tell others people what you learned here today, and just propagate our information to the local, your friend, family member, or other people. Yeah, thanks. And hopefully the tomorrow and 11th, you will again get the much more information. Okay.
Okay, so with that, I think we come to close to today's session and also the second leg of this campaign. And you will be, of course, visiting tomorrow and 11th for the in-campus, on-campus lab visit. So today we had, for example, about 28 of the participants came to the campus, and then They were taken to 2 of the labs as they were mentioned, and so they just left some ago, and I think they had a good time here, almost spending about 6-7 hours, and everything went very smooth. So we are looking forward to having you tomorrow. So with that, the time to close, and we should also thank all the speakers and experts who cleared all your doubts and also took the session. So thank you very much once again. See you, some of you tomorrow on campus.